Welcome everybody. So this is a bonus lecture and one of many bonus lectures that we're going to have. This is the first bonus lecture. So I'm going to kind of explain what's going on here. So if you've already taken the class and gone through all of the lectures, then you're going to have a really good idea of how to design electronics, build printed circuit boards, etc. So the bonus lectures are going to be kind of a potpourri, just random things. It might be something that one of you suggested that you wanted to learn about in a single lecture. It might be something cool that I want to show you in a single lecture. And it might be something not completely related to electronics. It may be something more compute related or microcontroller related, something higher, maybe retro computing or gaming, something like that. And then we'll learn about something, tear something apart, do something, build something, but we'll try and keep these in one lecture. So anyway, I've got many ideas, a big long list, and there's no real order how I'm going to do this. But the first one, what I thought, I was just sitting here and I just finished a medical product a while ago. And one of the things that we need to do in this medical product was sense force. And there's lots of different kinds of force sensors, but many of them are very expensive and many of them are very large. So we had to kind of find something that was very small, and there are a number of manufacturers that make what are called force sensing resistors. And if you take a look on the screen here, one of these companies is called Interlink Electronics, and you can see some of their products here. And so what these things are, basically they are a laminated series of materials that when you press on it, it changes its resistance. And so there's a certain construction to these, and we're going to take a look at them in a second. But you can see here, there's these different sizes, and this one right here is maybe the size of a dime. This one right here is maybe the size of a quarter. And then it's really simple. It's basically a resistor that as you squeeze and press on it, and apply a force, the resistance changes. And then we can take that value of resistance and put it into a circuit, an analog to digital converter, or an op amp, something like that, and control something directly. Who knows? The whole thing is they're super cool, they're relatively cheap, and it's a fun sensor to be able to play with. Now, so what I'm thinking is let's take one of these sensors, which I have over here on the bench. Let's build a basic circuit with the sensor with an op amp. And in the course, we didn't really talk about op amps, so I'm going to briefly talk about it. But op amps are a massive subject. In fact, in college, if you get an EE degree, op amps are usually 1 semester, sometimes they're 2 semesters. So when I took EE, it was actually 2 semesters, beginning and advanced op amp design. So a whole year just to learn op amps and everything that they do. So obviously we can't learn op amps in a 30 to 60 minute lecture. But I'm going to kind of give you a quick and dirty overview of what they do, and then we're going to use it in the circuit. All right, so we're going to need a force sensing resistor sensor, which I have many of them. We're going to need an op amp, and we're going to just build up a little circuit. We're going to basically convert force into a voltage, and then we're going to plot it on an oscilloscope, and then we're going to maybe we could use it to control an LED, and then maybe talk about some other things we could do with it. Maybe use a comparator, an analog comparator, and compare the voltage of something, and when the force exceeds something, it could turn something on, something like that. So we'll talk about that, and we'll see what we're going to build. So before we get into all that, let's do our homework. All right, so the first thing is I wanted to show you this website, Interlink Electronics. And like I said, there are a couple companies that make these sensors. So let's take a look here. Here's another company. This one's called TechScan, and this company makes some of the smallest sensors I've ever seen. And again, you can see here 3.81 millimeters, 9 millimeters, 9 millimeters. So this diameter of this little sensor is, about 4 millimeters. That's pretty small. All right. And then they have these kind of mechanical little protrusions or contacts that you have to mechanically connect to. Usually you don't want to solder to these because you'll melt the plastic here. All right. So TechScan and then the other company, Interlink Electronics. The technologies are very similar, so we're just going to kind of look at these. The TechScan parts are very expensive, actually. So unless you need something really small and Interlink doesn't have it, I would just avoid the TechScan at first because they are expensive. Unless you can probably find them on eBay. Someone's bought 1,000 of them or something. All right, so let's go ahead and let's take a look here. So depending on what you're doing, you might need something the size of a quarter, and then you might need long leads or short leads, long leads or something the size of a dime. So they have these variations of it so that you can kind of use what you need for whatever it is you're building, and you don't have to fabricate too much, all right? Now what I have, I believe, over here is I have the FSR 400 and I have the FSR I believe I have the short also. So the FSR 400 is what I have over here, which kind of has this smaller sensing pad. All right, so let's just click on that. All right, and then you can kind of read about it. And now they make these sensors with different sensing capabilities. So their range is different. So some of them can sense a larger range or a higher amount of force, and some of them are for a lower amount of force. So you kind of have to read and figure out what you want and order what you want exactly. All right, now the other thing is when we're talking about, so let's back up here. So if it's been a while since you've done, high school physics or whatever, so these are measured in newtons. How much force you can apply is measured in newtons, right? And you apply this force over the surface area of this little sensor. So 0.1 newton, so forces as low as 0.1 newton and a sensitivity range of 20 newtons. Now, for example, if you're in the United States, most people don't know what a Newton is. They've heard it before, but unless you're an engineering student or something, you're not going to be familiar with these. So the one thing is just being able to convert these to get an idea. So I think I have, let's see, a Google, yeah. So we look at a Newton here. So 1 Newton is about 0.22 pounds of force, right? Or another way, if we say 1 pound of force is about 4.44 newtons. So that kind of gives you an idea. So 1 pound is about 4.44 newtons, all right? And again, 1 newton is about 0.22 pounds. So that kind of gives you an idea. So in the case of that other sensor, it just said that it can measure from 0.1 newtons and a sensitivity up to 20 newtons. So 0.1 to 20. So let's take a look at that. So 0.1, all right, so that's, 0.02 pounds, right, and up to 20 newtons, right? That's 4.4 pounds, about 4.5 pounds. So that's a good amount of force. Now, you're going to be applying this force with your typically, maybe it's a sensor you're going to press on it with a finger or something like that, or it could be you could have a mechanism, a mechanical mechanism, where you have maybe an actuator and the actuator is pushing down on the sensor, something like that, right? So anyway, if it's something you're going to press with your hands, believe me, 2 or 3 pounds of force is quite a bit for your fingers to be pushing down, or 5 pounds is quite a bit, so that'll suffice. But if you need something that can measure a higher amount of force, you can still use these, but you can adjust the electronics and the sensing so that you can kind of get a larger scale, all right? So anyway, so that's that. Now, on the Interlink page itself, there's a datasheet, integration guide, and a bunch of other things here. Unfortunately, they make you kind of fill things out. So if you want the integration guide, you got to fill this out and, put your name and all that just to get the information. However, on a couple different websites, I was able to find this SparkFun for one of them. So SparkFun has the same product and it's for sale here, and this is exactly what we're looking for. And you can see here there's kind of a size, and so like I said, this one's very small. It's like the size of a dime, and then the bigger one's about the size of a quarter. All right, now if we go ahead and crack open a couple of things, we can get the data sheet here. So again, showing the diameter. So this one's 5 millimeters, and this one's 13, and so on, depending on what you want. So this would, for example, this large 38 millimeter square one, maybe you want to sense when a vehicle drives over something, a bicycle, a car, whatever. You could put an array of these, or you could put one, and you could put a pressure plate, and then you could sense what's going on there. All right, and then it shows various different parameters and so forth, and then application information. So this is kind of this is one of the things I wanted to show you. In addition, there's what's called if we go here, there's what's called an integration guide, and I want you to read that as well. You're going to download that and read that if I can find it. Yeah. So here's a force sensing integration guide, and what this is, it's 26 pages. This is kind of a quick and dirty explanation of how this technology works, right? So, I've read it, you should read it cover to cover so you know. And then it kind of talks how this thing works. So it's got kind of this flexible substrate here, which is this, kind of plastic polymer material. And then it's got this little spacer here. Now the spacer is just mils thick, so there's open air here. Then there's this resistor here, and then the whole idea is as you press down on this, you start making contact and shorting these little resistive elements together. And as you do that, the resistance changes, and then the signal is sensed with these two conductors here. It's as simple as that. Except it's made the construction is very, very accurate and precise and repeatable, so these sensors work very well. So these sensors actually work very, very well. Now, one of the problems with them, let me see if there's a chart here, is, yeah, so you can see here the chart. So we've got this conductance here, right? And conductance is the opposite of resistance. So here's resistance here. And you can see clearly this is nonlinear, right? So this is a curved chart here. And now it's linear in small pieces, right? So if you want to sense from here to here, it's linear, here to here, it's linear, here to here, it's linear. But if you want to go all the way from here to here, it's nonlinear. But this is no big deal. So what you do is you simply build your sensor, and then you basically apply a force, a known force, 1 Newton, 2 Newton, 3 Newton, 4 Newton, 5 Newton, etc., up to 20 Newtons or 100 Newtons. You measure the final voltage out of your system, right? We put that in a table, and then we use a curve fitting algorithms, or like a least squared algorithm, and then we could figure out what the force is very accurately, because we can basically, this is clearly a second order curve, third order at most, but a second order curve would fit through here nicely. It's clearly parabolic. And that way we could use a lookup table to figure out what the force is very, very accurately. All right, so don't worry about the nonlinearity. If it's too non-linear for you, then you're just going to use a microcontroller. You'll, through experimentation, run the system, put a Newton of force, 2, 3, 4, 5, etc. Then you will measure with a third-party measuring device. So you're going to need something to measure force, so you know what force you're actually applying. You're going to correlate that with the voltage, create a table, or the resistance, create a table, and then you can use that lookup table to figure out, so I've applied, so I'm reading whatever the voltage is. Now, of course, this is conductance and resistance, which is going to result in a voltage, because we're going to basically create an amplifier, and we'll have a voltage, and then we'll know what the force is to each one of these things, right? Whatever the gram force is or the Newton force is, right? Okay, so that is that. And let me see, is there anything else here I wanted to show you? Yeah, and this is just, so again, do's and don'ts, how to mess with this stuff, be careful of it. And when we go on the bench, I'm going to show you how I fabricated some of these things to connect to them. They're mechanical, so you can't be soldering to them, you'll melt them. So you've got to kind of use mechanical connectors, right? And then it's got some suggested interfaces for basic sensing. So we see this symbol right here, and this is an op-amp, or operational amplifier. And I've probably mentioned this in the course if you've already been through the entire course, or you've probably heard this word before. An operational amplifier is a kind of an idealized amplifier. And inside of this little triangle are many dozens, if not hundreds, of components to try and create this perfect amplifier. Now, of course, nothing is perfect, but it's perfect within reason. So basically what an op-amp allows us to do is things like amplification, filtering, mathematical operations, addition, subtraction, multiplication, logarithms, all crazy, crazy stuff. Op-amps are crazy. And like I said, it's basically a semester or good year course to dig into op-amps. Now, there are hundreds, if not thousands, of books on op-amps. I'm going to show you a couple. But an op-amp is an amplifier. And in this case right here, what's going on is the force sensing resistor is here. It's being used as a variable resistor. Then we've got a fixed resistor here. So we've got a voltage divider going on here. Then this op-amp is just being used as a simple non-inverting buffer. That's all it's doing, it's buffering it. So basically, we want to sense the voltage at the node, but we don't want any current to be drawn out of here, because as we draw current out of here, we would change the resistance, and the system would change and be inaccurate. So that's another property of op-amps, ideally. No current flows into these or flows out of these two terminals, called the non-inverting and inverting terminal. And we're going to take a look at this just real quick. I'm going to kind of give you a crash course in op-amps just for a few minutes to kind of get your feet wet in it. But anyway, we can use the properties of op-amps to create this, basically it's a buffer, and it's an analog buffer. So whatever voltage is here, we're going to see here, but when we sense this voltage, the system basically will draw no current from it magically. But on the output here, we can actually drive a lot of current. So for example, this output is going to follow this input here. So we're going to be able to track what this force sensing resistor is doing. And then say the voltage is 1 volt, 2 volt, 3 volts, and I want to pull like 30, 40, 50 milliamps out of here. Depending on the op amp, I can do that. And it will have zero effect on the circuit. Because it has zero effect on this, it won't change the voltage and thus change the reading. So remember, when you're doing sensing, ideally when you're talking to your sensors, you don't want to modify or disrupt the sensor itself as you're sensing from it, right? You want to basically look at it without it knowing you're looking at it. Okay, so this is one possible configuration here. And then it's showing you that V out equals V plus, whatever this V plus is here, divided by 1 plus, RFSR, which is this right here, and divided by RM. So that's the equation that you would get. So that would tell you what the V out would be. All right, and it's just saying some op amps that you can use to try out. All right, and then here's another one, so adjustable buffers. So again, it's going to show you a bunch of different designs, all based on op amps here, and this gives you different offsets and different things. So you can read through all this to kind of figure this out. What we're going to start with is just this one right here. We're just going to basically use this as a voltage divider. We're going to basically get an output of it. And we're going to use that output to drive an oscilloscope and maybe something else so you can kind of see this thing working. All right, but again, I'd like you to read all this so you can kind of get an idea here. And then, of course, you're going to be, and then showing some other, cool ideas here. Like driving a relay, for example. So when this thing, so here, threshold relay switch. So when this op amp, when the output hits a certain voltage, it's basically going to turn this thing on, and this relay is going to turn on. That was just what I was saying, using a certain force to turn something on, right? So anyway, read some of this, and then there are these kind of samples here. So if you have a 1.5K or 4.7 or 7.5K, it's going to kind of give you an idea of the different forces you could apply, right? And remember, 1 kilogram is 1 Newton. These different forces you could apply, and then what these curves are looking like with these circuits. So if you use this feedback resistor of 7.5, 4.7, or 1.5 in a simple circuit, these are the kind of curves you're going to get. So for example, you see here, if you use this 1.5K resistor, we get this initial nonlinearity, and then this thing settles into this nice line, right? And then we can basically read from 200 to 1,000, but the voltage doesn't change much. Now, if we go ahead and we use like this red resistor, which is a 4.7K, now what happens is, again, we get this nonlinearity, and it happens a little bit longer maybe, right? A little bit longer. Then it's linear, but now we get kind of from 1.5 to 5 volts. We get more of a dynamic range. So it's a give and a take, right? So it's either you get more dynamic range, you get more nonlinearity, or you get linearity, less dynamic range, etc. So you play with this stuff and just figure out what you want to do, okay? All right, so that's that. So that's the force sensing resistor. We're going to use one from Interlink, and let's see here. I believe, yeah. So this is basically what we're using, and let's make this a little bit bigger for you guys. So this is a DigiKey right here, and I've kind of looked this up, the FSR 400 series, right? And the FSR 400, if we back up here, is this series of the small one and the big one, right? And let's go back here. So you can just order these right now. And again, these things are not cheap. $7, $8. These things are not at 1,000. They're $385. This is not a cheap little device. So, but if you want to sense force accurately, this is a way to do it. Now, other force sensors, really complicated, advanced ones, could be 100, 200, 300. They're $1,000, $10,000 force sensors actually. So if you want absolute accuracy, but these are usually good enough for the kind of applications we're going to be doing in sensing if something's coming, going, robotics, etc. All right. So you can order a few of these. Now, they are expensive, so what I do suggest is maybe look on Amazon.com or maybe look on eBay, whatever, and see if you can, Alibaba, Banggood, see if you can find some of these things cheaper, maybe a bundle of 10 or something on eBay for $5 if you want to play with them, because they break pretty easily. And let me go back to that SparkFun. So you see right here this connection. So these things are basically crimped. These are little crimps here, and they're just crimped. Can I make this bigger? Just crimped on here. And if you apply any force, it just snaps off. So the first thing that I do when I want to play with one of these is I put a couple little connectors on here, and we've seen that stuff before, and I fabricate a little cable, and then I put some heat shrinking around this to protect it and give it some strain relief. So as I bend it around and stuff, it doesn't break. All right. So that's kind of how you have to work with these things, and you will break them as you play with them. All right. So we've seen the data sheet here. So here's the FS400 data sheet. So you're going to download that from Interlink Electronics, which if we go back to the website here, is just interlinkelectronics.com. And then the other thing that we are interested in is this guy right here, which is this integration guide, force sensing resistor integration guide and evaluation parts catalog. So you can get this from Interlink, or you can just get it on SparkFun very easily. All right. And then, okay, now let's go and let's talk about, so what we're going to do is we're going to build a circuit. What circuit are we going to build? We're going to basically build this circuit right here. And let me find that again. It should be right about here. Down a little bit. And here we go. So we're just going to build, something like this. Very simple circuit right here. And as a matter of fact, I think if I go, there's even a simpler one. Here's one here, and yeah, there might have been another one. Let me see here. Let me scroll through here. There's kind of a couple good ones to start with. All right, so here we go. And basically it's just a variable resistor, and we're just going to put it through an op amp, and we're going to use an op amp as an amplifier, which we haven't learned in the course how op amps work, but I'm going to show you real briefly. And let me see if there's, no, not really. There's another circuit that I like. Another circuit that I like here, but it's not in here, I don't think. Yeah, and these are current to voltage converters. That's why there's this feedback resistor and there's no more voltage divider. That would be hard for you to even to see though if you're not familiar with op amps. All right, so anyway, we're going to build the first simple circuit, which will go back to any of these, and it just looks like this. We're basically just an op amp, resistor, and our force sensing resistor, and that's it. Okay, now let's switch gears to op amps. All right, so let's talk about op amps. So operational amplifiers. So where do we even begin with that? All right, so the first thing is there are about 1 billion operational amplifiers. Inside of each operational amplifier is many dozens of components that create kind of this virtual amplifier. Now, what I'd like you to do is, again, always lots of homework with me. You know that if you've taken the class already. All right, so there's a couple books that are easily available online. One of them is called the Handbook of Operational Amplifier Applications, and it's written by Texas Instruments, which of course make operational amplifiers. So I want you just to search for this, and then just, it's SBOAO092B.pdf. If you just search for that, you can probably find it. But anyway, Handbook of Operational Amplifier Applications, it's 100 pages. I would just like you to read it, all right? And it's going to start to show you how these things work, what they look like, what their models are, and so forth. So this is one example, one good book. There's another book, and let me see if I can find it here. I think I already downloaded it as well. And let me see. This one. Again, another Texas Instruments book for free. Op Amps for Everyone by Ron Mancini is the editor-in-chief. So I believe this is like and there's different versions of this. Yeah, 2002. So this is very new. So as far as op amps go, this is brand new, right? It's like transistors. This stuff changes, but what we're going to be using, this is, as far as we're concerned, state of the art. Okay, so I want to kind of use op amps for everyone as our reference. Now, let's go through here. And what I want to do is I want to show you kind of the model of an op amp and just a couple circuits. All right, and then again, you're going to have to read this. Because this subject is very, very large, and then this is kind of circuit review, which you would have already learned in the class, but what we want is section 3 or chapter 3, I believe. Yeah, is the development of the ideal op amp equations. All right, so you read this right here, and what it's going to talk about is an op amp is this ideal amplifier, and it was designed and architected to have certain properties. Now, nothing is ever ideal, so it's close to ideal, as long as you use it in a certain domain and you don't exceed that domain, right? As long as you play by the rules, it will act like this ideal amplifier for all intent purposes. It'll be perfect. If you break the rules, it will not work anymore. All right. So what I want you to look at here is kind of this model of an ideal operational amplifier. And so let's look at what's going on here. So it says things like we've got IB equals 0. We've got IB equals 0. So this current going in this direction and this current going in this direction are both 0. Then it's saying the voltage across these two terminals, VE, is also 0. Okay. Then it's saying its input impedance, ZI, is infinity. So it's infinite input impedance. All right, great. And now what's going on here is basically this is an amplifier, right? And it's going to amplify. And so now we see this output, this A, so it can actually source infinite current. All right, so it's infinite current supply. And here's another, I wish this was true. The output impedance is 0. So it has 0 output impedance, it can source infinite current, it has infinite input impedance, and it draws no current. So basically this thing is completely ideal. So if you look up here, it kind of talks about all these things, right? Now in reality, these things aren't going to be true. So maybe it can output an amp or 100 milliamps. Maybe its output impedance is 10 ohms or 50 ohms. Maybe its input impedance is 100K or a megohm or 10 megohms. Maybe the input currents, these input currents that come in here are maybe microamps or picoamps. And maybe this voltage difference between the minus, which is called the inverting, and the positive non-inverting terminals, maybe the differential voltage is millivolts or nanovolts, maybe picovolts. I think there's some picovolt ones, operational amplifiers. Okay, so anyway, that's what we're looking for. And here's the rule. The more ideal the device, the more expensive it costs. So if you're building, for example, military grade, medical grade hardware that's dealing with very small signals, and noise is very important, where basically you're going to deal with very tiny little voltages, and you have to have these things operate so that there's no noise and all that. You're going to be using very expensive op amps, and by very expensive I mean you could spend transistors a penny, 2 pennies, 5 pennies. An op amp could be 20 bucks, 50 bucks. I never like to say never, but I've never seen an op amp that's $1,000, but I bet you there is one. But there's op amps that are tens of dollars easily. So we're going to use op amps that are $1, $2, $3, 50 cents, right? With certain properties, okay? So that's what we're going to pick. Now, picking op amps is like picking transistors and field effect transistors. There are just too many of them. So what you do is you have to pick a company that you like, a TI, a Fairchild, a this, or that, whatever, and kind of, get the part from them, whatever the company is that you like. And otherwise, you just be overwhelmed. So I'm going to just pick one for you, and then we're going to build something with it. All right. Now, all right, so that's kind of the model of the op amp. And then what happens here is it's going to start showing these different circuits. All right, so let's go ahead and let's take a look at some of these circuits. All right, so when you start off with op amps, you're going to probably be building 2 circuits a lot. One is called the non-inverting amplifier, and one's called the inverting amplifier. The non-inverting amplifier is nice because it doesn't invert anything. In other words, if you put a voltage in, say V, you get something times that voltage V out. The inverting version, you get minus V out, right? So it inverts the signal somehow times some gain or some other transfer function. All right, so let's just take a look at this. And now, again, you're going to have to read through this because it's going to derive the equations. All right, it's going to derive what's going on here. All right, but in a nutshell, and here's another thing. So now, when you want to derive the equation of an op amp, you can actually do it, and it's actually kind of fun. It's a fun exercise, and of course, if you take an EE course in this, you'll derive all of these yourself. You're not going to be given them, you're going to have to derive them and figure it out. But how do we derive it? Well, we derive it based on the laws of the op amp. So we assume that the guy who made the op amp, or girl, created this idealized version of it. So we know that the gain is infinite. We know that the output impedance is 0. We know that the input impedance is infinite. We know that the current into the inverting and non-inverting terminals is 0, and so on and so forth. We have all these rules. So then what we can do is we basically can put components on the op amp, and then using nodal analysis or mesh analysis, whatever you want to do, circuit analysis, we can constrain the circuit such that we can start to write formulas or a set of equations, and out of those sets of equations will emerge or pop out the transfer function for the op amp. And if you put capacitors and inductors and you have the proper formulas for them, you can get very complex filters and all kinds of cool things. Anyway, in this case, he's just starting off very simply, and he's saying, all right, we've got two resistors here. One's I'm going to call RF for feedback, and the other one I'm going to call RG, I assume, for it's going to ground. So the idea is we're going to have a voltage here, and the voltage is just going to be on this single input, Vin. All right, and that's all we know. We got V in, we got V out, we got these two resistors. My question to you, his question to us, and all that is, what is V out? What's V out? Well, he goes through this explanation here, kind of explaining why it's like that. And then he comes down, and he says, hey, here's the deal. V out over Vn equals 1 plus Rf over Rg. So 1 plus Rf over Rg. That means that V out, so if we take V in and move it over here, V out equals the input times this. So that's the transfer function right there. So basically, it's going to have a gain of at least 1 plus the ratio of these two resistors. So for example, say if you wanted to have a gain of 1, then we would make this feedback resistor 0. So if we make this feedback resistor 0, right, then basically it's going to have a gain of 1. Then if we make this RG infinite, we could make it infinite, right? It wouldn't notice it. Then we would still have this gain of 1. So basically, if you just tie the output to the input, you create this non-inverting amplifier that just the input follows the output because the gain is 1. All right. If you leave these resistors in here, then the gain is whatever this is. So for example, say we put RF as 100K. Then say we put RG as 1K. So 100 over 1 is 100, plus 1 is 101. So the amplification would be 101 times the input voltage. Now wait a minute, you say, wait a minute, what if I put 5 volts in here? So you're telling me I'm going to get 505 volts out of here? No, of course not, because that would break all the laws of physics. You can't get something you don't have. But within the, so say that the op amp is powered. Now we have to power these things. It's an active device, all right? We're going to power it, which is not shown here, with a positive and a negative supply. So say the positive supply was 10 volts and the negative supply was minus 10 volts. So when we try to do this amplification, so we said the amplifier is going to amplify 101 times. Let's call it 100, all right? 100 times. So if we put in a little voltage, say 0.1 volts, right? 0.1 volts times 100, right, would be 10 volts. So it would take the 0.1 and we would get 10 out. But the moment we put 0.2 volts in, right, that would be 20 volts out, it's still going to stay at 10 volts. It's not going to generate some miraculous voltage. So again, the op amp will only operate within, the realms of reality, but it will attempt to be ideal. It will attempt to do these things, all right? So it's never going to generate more voltage than you give it for the rails, for the power supply rails, which we're going to see where you hook that up. And again, it's never going to give you more current than the data sheet says that it can give. So even though you try to pull more current out of it, it's just not going to give it. If its op amp is rated for 100 milliamps and you put a load on it of 1 ohm, right? And so we put, say for example, we put out 10 volts and we put 1 ohm, right? So we got 10 volts, we got 1 ohm, so that's 10 amps. No, 10 amps is not going to come out of the, is not going to be sourced by the op amp unless it can source 10 amps. It's probably going to put out 50, 100, 20 milliamperes, whatever it's designed to do. So you can't break the rules, but as long as you stay within the rules and usually stay away from the barriers, away from the envelope. So you don't want to use this thing all the way to the envelope because then it's going to start to act nonlinear. So in other words, if you know that the op amp has a and we're going to talk about some other things. Say we know that the op amp it can source 500 milliamps. I'm probably not going to push more than 300 or 400 out of it. I'm surely not going to take it all the way to 500 because it's probably going to start acting weird, right? So if I want 500, I'm going to get an op amp that puts out an amp, right? Remember, always over-design everything so that when things go sideways or things happen that you don't anticipate, nothing breaks. Okay, so this is the non-inverting amplifier. And we see the equation right here. It's V out over Vin equals 1 plus R feedback over RG. And these resistors will typically be called R1 and R2 in a lot of other books, R2, R1, all right? And then what I just said when I was just kind of saying, if RG becomes very, very large, right, and or RF becomes very, very small, right, then this whole thing reduces to V out equals 1, right? All right, times Vn if Vn is 1. Okay. Okay, so let's keep looking here. Now, the inverting op amp. So this is kind of what you're going to see more often. And the reason why is because this is a little bit more, having the 1 plus term is kind of a little unsettling as an electrical engineer. I don't like the 1 plus because it's 1 plus something. And that something is never ever really going to be 0. It's 1 plus it. So we kind of like no 1 plus. We just like input voltage times something, done. This is what this does. Now take a look here. So V out over V in equals minus RF over RG. Now look at the architecture of this one. This one has the feedback resistor going back from the output back to the input. And here's another little comment is op amps they operate with feedback. If they didn't, they would just be open loop and they would just they would saturate, they would go crazy. So we take some of the output and we feed it back to the input and create this feedback loop, and that makes them well behaved, all right? Anyway, so we take this output, we feed it back here through the feedback resistor, then again we have this G, which is not our ground, it's just RG, which I'm sure it says what he likes to call RG. But anyway, typically this would be R2 and R1, right? R or RF and R1 or RN, right? Anyway, either way, he goes through the rules of the op amp, and then he drives what this equation has to be. It just has to be. And then it's V out equals V in times minus RF over RG. So what is this thing doing? It's inverting the minus sign. And what's the amplification factor? It's RF over RG. Super simple. So let's say we wanted to make an amplifier that multiplied the input voltage by -1. That's all I wanted to do, by -1. All right, that's it. So I'm going to make RF and RG the same. Now, also there are rules for RFs and RGs. You don't want to make them too big or too small. So make them usually in K, right? So don't make them 1 ohm and 2 ohm, make them in K. Don't make them in hundreds of K usually, make them in tens of K, make them in K. So I'm going to probably make RF and RG both 10K. All right, 10K over 10K is 1. So V out over Vn equals -1. Boom. So my output voltage will be my input voltage inverted. Now, wait a minute, this is cool. So I can put in a positive voltage and get out of negative voltage, but my power supply is only positive. No, you can't, unless you have a negative power supply. So to get the inverting op amp to work, when we power this thing, we're going to put a plus V and a minus V on it, a plus 5 volts and a minus 5 volts, a plus 12 volts and a minus 12 volts. So whatever we force it to do, it will do if it can do it. So if you don't have a negative power supply on here, you're not going to get a negative voltage out of it. You'll get the closest to negative that you can, which is 0. So again, you can't violate the laws of the op amp, and you can't violate whatever you have in your circuit. It's not going to work. But if you don't violate it, it will work. So for example, if we had a plus and a minus 12 volt supply, and we put in 1 volt, we'd get out -1 volt. If we put in 5 volts, we get out -5 volts, et cetera, et cetera. So we just basically did mathematical inversion, right? And if you wanted to gain it a little bit, say we wanted to multiply, so say we wanted to multiply the input by the output by -2. Then I would make RF 20K and I'd make RG 10K. So now my gain is 2, and with the minus sign is -2. Done. So I just made an amplifier and it multiplies by 2, but what kind of 2? A -2. It's an inverting amplifier. Okay? All right. So that's that. So that's my quick and dirty op amp introduction here. And we're about 40 minutes in here, so I want to finish the rest of the time and kind of do some circuitry here. But this is going to be painful, but I want you to read this whole book and at least skim it. So the first few chapters are 1, 2, 3, 4 are understandable. Then after that, it gets fairly advanced. But just eyeball it for me, all right? Unless you're comfortable with the mathematics and so forth. But you'll see a lot of really interesting things in here, all right? But the first few chapters are doable. Okay, now. All right, so let's find an op amp. All right, so let's find an op amp. So I like to use many op amps, but one that I prefer is, let's see where it went. Let's go back here. It's called the LMV 796. All right. And again, I could spend many lectures just explaining what all the parameters of an op amp do and what they mean. But I'll tell you right now, this, and you can see this is not a cheap op amp. It's $1.50. It's not cheap, right? And at 500, it's 88 cents. So it's, it's a dollar op amp at 100, right? It's not cheap, which means it's pretty good, and it's going to do a lot for you, and it'll get what you need done. Now, let's again, I hate just showing you stuff without kind of telling some of the things. All right, so first it's a general purpose op amp. That means it's not been optimized for some special application, maybe high speed, maybe low noise, maybe 100 other things, all right? It's just general purpose. Okay. Next, it says how many circuits. Well, there's just one op amp per package. Many times, there's many op amps per package just because it's convenient, but also so they're thermally related to each other. If they're in the same package, as the temperature of one changes, the temperature of the other one changes. So if you're using these op amps to amplify or do some signal processing, you want to make them all thermally the same, and that's why they're in the same package. So that's what's important. You want to have, so if you want two op amps, don't put one op amp in one package, another op amp in another package. Put them in the same package if you care that they're thermally connected. All right. Next, slew rate. What is this? All right. So the slew rate, what this is, it says slew is the rate of change. So the slew rate is 11.5 volts per microsecond. Let's take a quick look at that. I just want to graphically show you that. All right, so what this is talking about here is this. So let's get on our little graph here. All right, so this is time down here, and this is voltage here. All right, and so what this is saying is that, and let's put some little tick marks here. All right, and if we go back, this is saying it's 11.5 volts per microsecond. All right, so if each one of these was 1 microsecond, so 1 microsecond, there's 2 microseconds, 3 microseconds, 4 microseconds, 5, 6, 7, 8, etc., right? And then up here, let's put some voltages. Let's say that this is 10 volts, 20 volts, 30 volts, 40 volts, etc. What this is saying is this. It is saying, and let's pick this color, every 11.5, every microsecond, it can go from basically where it was 11.5 volts higher. So it can go from 0 to 11.5 volts in 1 microsecond. So here's 1 microsecond. So in 1 microsecond, it can go to about here. All right, that color's no good. Let's use yellow. That's better. So it can go like this. So here is the slew rate. So this is the slew rate. What this means is, this is how fast this op amp can adjust to signals. So if you're forcing the op amp for really high gain and high amplification and really fast changing signals, it may not be able to keep up if it can't maintain, if it's over the slew rate, right? It's not going to be able to keep up with the signal. So if the op amp is, say, getting a signal on the input that's going at 100 megahertz and the voltage is changing radically, it's going from 100 volts to 0 volts. If you take those two things together, the slew rate is going to be way too fast for this thing to keep up. So you have to make sure that whatever happens, whatever signal you're trying to amplify or process, it will be within this slew rate or within this rate of change that this particular op amp is capable of doing. Okay, that's what slew rate is, and that's what it is related to op amps. Now, what's this other thing? Gain bandwidth product, GPB, GBP. So what this is, it's the gain times the bandwidth. All right, so what that means is this. If you want to amplify a signal by, say, just a factor of 1, then that means the highest signal that you can process is 17 megahertz. Now, if you want to play with a signal that is 1 megahertz, right, 1 megahertz, then the highest you can amplify it is 17 times, because no matter what, the gain times the bandwidth can't exceed 17 megahertz. So that's called the gain bandwidth product. All right. Typically, we want these to be very, very high. Now, this op amp would be nearly useless for a signal processing of very fast signals, of, say, radio signals or things like that. But for audio signals in the kilohertz range, it'll be more than fine. And that's what I typically use it for. All right. Now, what are these two things? input bias. What this is, remember the inverting and non-inverting inputs, the inverting and non-inverting inputs, right? Inverting and not inverting, those two inputs right there. So what that has to do with is, and where did it go? That's how much current is pulled into those or pushed out of those inputs. Typically we want that to be 0, right? But it's 0.1 picoamps. That is practically 0 as far as I'm concerned. That is very, very small. It's a 0.1, it's a tenth of a trillionth of an amp, right? A very, very small. And then what is the input offset? 100 microvolts. Remember, that's the plus and the minus inputs. What is the differential voltage between the two? All right, that should be 0 ideally, but here it's 100 microvolts. Not bad, not bad, right? I'd like it to be down to 2 or 3 microvolts would make me really happy, but 100 is fine. Okay, and then current supply just means how much you need to supply to make this thing work. And then rail to rail means it can go all the way positive and all the way negative, right? So it's a rail to rail op amp. Some of them are single rail. They can only go to a plus to 0 to a positive voltage. So this is a really good op amps. Now let's look at the data sheet. All right, so here's the data sheet for the LMV 796 and 797. All right, you can kind of read through here. And then here is kind of a little example use of it. And you can see you've got the inverting, got the non-inverting, got the output, got the input. Now, where is the power? Where does the power go? Let's take a look. So we go here, and here we go. So here is the SOT23 version, right? And you can see here's the output at pin 1. Pin 2 is V minus. You can't see that well. Uh-oh, end of the world. Let's rotate clockwise. You can't see that very well, but there it is. There's the V minus at pin 2, V plus at pin 5. The input plus is at pin 3, and the input minus at pin 4. Now, I'm going to tell you this. I want you to be really, really careful. I've done this about 1 billion times, all right? And I've blown something out. In my rush to build things, I look at the schematic and I see in plus and in minus, and I think that means the power supply in plus and in minus, right? And then I put power supply here, and then I put the signal here, and I blow the thing out. Be very careful. Always look at the plus and the minus. These are the inputs, and then the wires coming off kind of the sides of the triangular symbol, those are the power supplies. So pin 5 is V plus. We're going to hook that to 5 volts. Then we're going to hook V minus to 0 volts. We're not going to put it to a negative voltage because we don't need a negative voltage, because we're going to use this in the non-inverting configuration for our force sensing resistor. Okay, so what do we have? We have our LM796 here. We've got its 1, 2, 3, 4, 5 pins. I've already got it mounted on a surface mount board. All we have to do is kind of hook this circuit up. So what I'm going to do is I'm going to toggle back and forth between the drawing program here, and we're going to kind of draw what we're going to do. Okay, so let's go ahead and draw the circuit that we're going to build, all right? So we're going to have our op amp here, and then what I'm going to do is I'm going to draw the power supply. So this is going to be V plus here, and then this is going to be V minus here. This is going to go to plus 5 volts. Here is going to be our output. I'm going to take our output right here. All right, so I'm going to call this V out right here. Then we have our 2 inputs here. Here's one and here's the other. And then we will call this one, let's go ahead and we'll call this one the non-inverting and the inverting. Now let's go back and let's take a look at our pinouts here. So the positive V plus is 5 and the V minus is 2. So 5 and 2. So let's go put that in. So this is pin 5 and this is pin 2. The output, where's our output, is pin 1. And, you know, be careful of this. And then non-inverting is right here, is pin 3. Pin 3. All right. And then the other one is pin 4. All right. Okay, so this is kind of what we want to build here. Now, we know, let's go back to our little FSR diagram here. And if we can find that circuit again, it's in a lot of different versions of these. Here it is right here. So it's very simple. We have our FSR here, and then what we want is to create a voltage divider, and we're just going to put that center node into the plus, and we're going to take the output and feed it right back to the input. So basically we're doing a non-inverting amplifier with gain 1. all right, as far as this is concerned. Then this resistor network is going to control what the output voltage is. Okay, so all we're going to do is copy this, all right, so very simple. Okay, so now what we're going to do here is we're going to take this output here, and we're going to, and as a matter of fact, yeah, we can do this with this color. So I'm going to take this like this, and I'm going to very carefully jump over that so you can see that. And that goes right there. Okay, and then here's our input. So this is where everything's going to happen. So now let's go ahead and let's use a different color here. Let's use green. So now what we're going to do is we're going to say plus 5 volts again, and then we're going to put our FSR in here. And now remember, this is not a potentiometer, so there's like different ways of drawing it. So see how they kind of draw it with this line through and this kind of thing here. We'll just use their convention. All right, and this is our FSR. And then this is our resistor here, which sets kind of the gain here, or sets this kind of voltage divider ratio. And they call this thing RM. And I'm going to tell you right now, we're going to use either 10K or 100K in our examples. And if we look here, so here's 10K is the purple, it's this one. So with these forces right here from like 200 to 1,000 grams, we're getting these voltages from like 1 volt to 3 volts. But then if we put it up to 100K, now I want you to be careful here. This blue line starts all the way down here. It's just being occluded. So it starts all the way from 0 and it goes up to almost 5 volts here. So we get the whole range, but look, we have this really, really bad nonlinearity here. It's got to get up to about 200 before it turns linear. So we can either use it in this little tiny region here or use it over here, but this will give us the full range. So the 10K kind of gives us a good dynamic range, right? Kind of reasonable. It's from here to here-ish, that vertical range right there. And it's fairly linear this whole time. But the blue one gives us the whole range from 0 volts all the way up to 5 volts, but it's absolutely nonlinear. It's like, woo, this curve down here, right? And this curve right here is definitely not a second order curve. This is probably a third or fifth order curve to get this to fit here exactly, but at least a third order, maybe a fourth order to get good fit. But this one, this purple curve, that we can get away with a second order fit on that one right there if we want to use their lookup table and all that. But we're just going to put in 10K and 100K for these forces. And now, again, even though there's this table here, this table means nothing to us. We can't correlate this with anything. We have to actually measure things to create our own table to know what we're doing. All right. So this is what we're going to build. We're going to build this right here. We're going to build this exact circuit right here. So let's go ahead and go over to the bench, and we're going to just build this and then play with it. All right, so I'll meet you over at the bench. All right, everybody. So we're back here on the bench, and I've got everything kind of set up here. So here is one of these force sensing resistors. All right, right there. You can see that, and that's what it looks like. All right, and then of course I've created this cable. Let's zoom in just a little bit here. We'll zoom in just a teeny tiny sconce, which I've heard someone say before. There we go there. So there's our force sensing resistor. It looks exactly like we think, and then you can see I made this cable here and kind of connected all this together. Now, here are some that I got from DigiKey. All right, now these things, you saw how expensive these were, right? No joke. So check this out. So I ordered 3 of them from DigiKey. I ordered 3, and look, they gave me 3 bags, and in each bag there's like 25 of them. These things are like $7 each, right? So it's like hundreds of dollars of sensors right here. So anyway, this is what they look like. Let's go ahead and take one out here. This is the smaller one, the little shorter one, and I'm going to be very careful here. Camera. Okay, let's move this for now. There we go, and then I'll just pop one of these things out carefully, or not. Let me try this one. Nothing ever wants to cooperate. Okay, so it's getting caught. There we go. All right. Be very careful of these things. Kink these up. All right, so there it is there. So the whole idea is that when you make your cable for this, you're going to mechanically connect onto these 2 things, because if you try to solder, I guarantee this thing will melt. Now, what you can do is mechanically connect onto both these with a couple of little clips with wires on it, and that's what I did here, just same idea. Then what I did was I just really quickly did some soldering, solder, and then I went ahead and individually wrapped them in heat shrinking, and then the whole thing in heat shrinking. So that's pretty good, and I'm not going to bend this, but it's pretty strong in there. This is actually pretty strong. That's pretty strong. All right, but that's what it looked like, and then I had to make this out of it so that we have our little resistor here. Now remember, this thing is not polarized. It works in either direction. So anyway, no real difference. You can put it either way, but I would just come up with a convention so that, you know, from the top and call one side minus, call one side plus, and that way you kind of do things the same mechanically and electrically and all that. Okay, so let's move these things away over here and let's get our circuit down here. So as you can see, I've already built the circuit. And basically this mimics what we did. Now, if you've already taken the course, then there's a few things in here. So one, we've got our power coming in up here. So our power is going to come in here or come in here. And then I've got a bypass and filtering capacitor. I've got a 10 microfarad and a 0.1, and then I pop it over to the other rail here, 10 and 0.1. Of course, these are tantalum capacitors, and this is a ceramic capacitor, monolithic. So both of my rails are good to go. Then I've got my rails connected here, rails connected here. You can see these wires, because remember, they don't jump over with this particular board. This is open here, so you got to jump it over. All right, so here is our LM796, LMB796 op amp. You can see it's pin 5, 1, 2, 3, 4, the way that this thing is worked out. And let me see if we can zoom in just a little bit more for you without losing focus. Yeah, okay. And now I've basically just mimicked that circuit. I've just mimicked the circuit. So here comes power. Now what's going on here? So I've got power, and then I've got my, this is a ferrite bead because I want it really, really quiet. And then I've got a capacitor to ground. Let's go back over to the screen, take a quick look at that. So back over here on the screen, one thing we kind of left out that I put in the design there was a couple added little features. And one of those is coming through here, there is a ferrite bead. So that's a ferrite bead, right? And that is for noise. So high frequency noise is going to get squashed by that. And then what else did I add? From the same node here, I put a capacitor, right, to ground, and this one is 0.1 microfarad. So this has a bypass capacitor, and it also can be used as a current source if this thing desires a lot of current, it'll have something to get it from. Now, on that topic, if this thing is going to be pulling a lot of current, maybe we want a 0.1 in parallel with a 10 microfarad so we can get some current so it doesn't have to run all the way back to the power supply, right? And remember, in the course, you're going to learn about that. If you haven't watched all the course, you're just skipping to here. We want to have both a capacitor for filtering, and we want to have one also for a local current source, okay? If we're going to be drawing a lot of current. All right, so anyway, those are those two additions. Now, another addition you're going to see over here is we basically need to put a load here. So when this thing's not doing anything, I just put, I think it's 100K just to ground. So we just put a 100K load here just so that this thing is just not kind of open loop, closed loop. We just put something to ground, and that's what we're going to put there. And then we're going to take this output and do whatever we want with it, all right? We're going to put it to a probe, the oscilloscope, that kind of thing, all right? So let's go back, and there would be the oscilloscope, and we just put a probe there, and then we would connect the grounds, and we'd be able to see the signal here. All right, let's go back. Okay, so we're back here. So basically, there's our filter. Filtering ferrite bead, which is basically an inductor. There's our little capacitor, little bypass capacitor. Then we've got our ground there. And then here's this is that RM resistor. Right now it's 100K. All right, that's 100K. And then this little capacitor right here, don't worry too much about this. This is for high frequency noise to go over the resistor. So it's a bypass over the resistor so that there's an AC path and then there's a DC path, and this is kind of an op amp thing. Don't worry about that, but it'll work fine without it, but I like putting that on there. Again, that's a 0.1 right over that resistor. And then here's the output. And then you can see the output goes back to the input there. There's our output. There's that 100K I talked about, just to give it a load. And we're going to take the output here, and then there's ground right there, right? Okay, so I think that's it. So let's power this thing up and see what goes on here. All right, so I've got my handy dandy power cable. And again, if you haven't taken this course, I'm going to be saying a lot of things that are going to make no sense. You have no context, so you shouldn't be watching the bonus lectures, right? But if you so desire, then you can. Let's put this in here. And again, this is where mistakes are made. It's really easy, putting things in the wrong way and all that. So just be careful of stuff, put stuff in the right way. All right, so that's hooked up and good to go. Now what I want to do is I'm going to take our oscilloscope, which is on the other screen, which you can't see yet, and I am going to hook a probe up. And again, you know that dealing with the oscilloscope is just a nightmare. So we're going to hook the oscilloscope up here so these cables just get everywhere. All right, good. Okay, now we're missing one thing. What are we missing? We're missing the force sensing resistor. So the force sensing resistor, where does the force sensing resistor go? Back on the other screen there, which I'm not going to switch screens, it needs to go to the plus rail, so the +5 rail. So here's our input right here. So here's our input right here. And this is filtered, so I want to take the filtered one. And then it goes to that resistor. So it goes to the top node of that resistor. So it goes right there on pin 3, that non-inverting input. There it is. Okay, now what I'm going to do is I'm going to back this out a little. I'm going to zoom out here. So we're going to do this all simultaneously a little bit here. All right, and there we go. Okay, now I've got my force sensing resistor here. I've got my oscilloscope over there. All right, so ready? I'm going to push this. All right, and then now there's the oscilloscope, so you can see it. It's already kind of set, and the range is set. So we're going to push on this, and nothing happens. Why not? Anyone? We didn't turn the power on, right? So let's go turn the power on. All right, so you're going to hear it turn on. Okay, there goes the power. And let me get this back so you can see it. Sure enough, there it goes. So I am sensing force. Now the oscilloscope, because this is like a very slow DC signal, this oscilloscope does not like this. It likes fast signals and all that. So don't worry about it looking like it's hanging and glitching. It's really not. If we were to hook up a analog oscilloscope, it would just be very smooth as butter. But the oscilloscope kind of sputters and puts, and this is like one of the things this Handtech does, kind of annoying. All right, so anyway, I'm going to kind of tell you, I'm putting right now barely touching this thing. And now I'm pushing harder, I'm pushing quite hard, and you can see the voltage on the oscilloscope there is 4.4, 4 point, and I'm not going to be able to get it to get all the way up because of that voltage divider, but I got it close, 4.6, 4.6-ish volts all the way there. All right, so I mean, I had to press really, really hard to get it to there. Now, let's go ahead and let's change that RM resistor. So that RM resistor, and let's change what that scale is. So let's get our 10K, and it's always a challenge looking through everything. All right, so there's not a lot of power going on in here, so I'm just going to undo this in real time, and hopefully nothing will explode. All right, I'm not going to turn anything off. I'm just going to grab that 100K right out of there. And I've got a 10K. What's 10K? Brown, black, orange. What's the 100K? Brown, black, yellow, right? All right, let's hook this up, and this is just going to go back to ground. Ideally, if I can get my fingers in there. Okay, good. All right, so we got this back, we got this back. Okay, so everyone take a look at that oscilloscope. Now remember, if you remember the other chart, with the 100K, the voltage went all the way from 0 to 5, but it was extremely nonlinear. But with this one, we're going to have to apply a certain amount of force, then we're going to have a dynamic range only a couple volts, right? So watch. So now I'm applying a good amount of force. Now it's getting kind of linear. Now I'm pushing. I'm pushing really hard now. I mean super hard. I'm busting my finger. You can see my finger turning white. So we went up to 3 volts and 0 to 3. So you can see, remember, it's exactly what we said. You have a less dynamic range, but it's got a much linear range in here in that smaller dynamic range, right? So that's where we'd want to work this thing. So if this was a sensor and it was working in this force amount of force, which I'm feeling like is I don't know, a quarter pound, a couple pounds of force I'm pushing down here, this would be the resistor that we want to use. Okay, so that's that. Now let's do something else here. So let's first, I want to put that other resistor back because I like it going all the way to 5 volts, even if it's nonlinear. All right, now let's have some fun because that's what life is about. Let's add a LED. Let's add a LED. So we're going to take an LED here, and we're going to put the LED here, just like this, right at this output. And then we're just going to put a 100 ohm. I want to limit the current because I won't be able to pull that much current through that LED. So we'll put 100 ohm, and that'll limit the current so we don't mess up the op amp. All right. Okay. So now this 100K is going to be irrelevant. It's not going to really affect the circuit. It's just there to keep the circuit kind of stable as we take things, connect things and disconnect things. Okay, so here we go. So now I'm going to go ahead and I'm going to apply force here. You can see on the oscilloscope, which is still there, that we've got 0 volts on the oscilloscope. So as I press this, it's going to go all the way up to 4.6 volts, and we should see that LED turn on in a nice, semi-linear fashion, as smooth as I can apply force. So I'm applying force, and you can see the LED getting bright, getting this bright. Woo, how cool is that? So I'm just kind of pulsing the force with my finger. It's not turning, there, and I can just control it. All right. Now, hey, So right now you do that and see it just kind of staying on there. Let's smooth that, right? So let's smooth that. Let's go ahead and let's put a 22 microfarad, which I just happen to have here. Let's put a 22 microfarad and let's make a filter, and this will charge. So this is basically going to it's going to charge each time and it's going to slowly discharge, right? So we're going to put that right here at this node. If I can get it in here, let me see. What we'll do is we will go like this, never enough room. We'll make some. There we go to ground. Okay. Now, check it out. And then, eh, hard to tell. Hard to tell. Yeah. It's discharging. It's also discharging into the op amp. So it's not having it's smoothing it a little bit. Smoothing it a little bit. All right. Okay, so that's that. Now, let's see. Okay, what was the other thing that I wanted to talk about? So, for example, we've got this voltage here, right? And then what we could do is we could use another op amp, what's called a comparator, and then we could basically, when this voltage hits something, say like right there, so if you look at the oscilloscope, right there, it's 3 volts, right? So we could set a comparator, which is another analog device. It's based on op amps. Or you can make a comparator out of an op amp, and at 3 volts it would snap on and turn its output on. So then we basically have a threshold, and at 3 volts, which is some certain force, right, then it would turn something on. Maybe it would say, hey, you know the load is too much for the elevator, or whatever. All right, now the last thing that I want to show you is this. So we're sitting here and we're going, this is super cool. As I press on this thing, I get, a voltage out of it, and I've got those charts in the data sheet. But I mean, I want to make this really accurate because I want to make a scale. I want to measure. I want to know exactly how much force you're applying here so I can convert it to a weight or whatever. How do you do that? So how do you measure that? Well, what you need is you need equipment, and you need equipment to measure this stuff. So let me show you a piece of equipment. This baby is basically it's a force sensing tool. Let me open it up here so you can see it. There it is. So there it is right there. So this and the power supply, and it's got a serial port so you can log onto the computer. So this is a piece of equipment, and what this equipment does, and it's got these different attachments here, so you can attach it onto the head so you can push things, pull things, poke things, do all kinds of things. So we are just going to use like this one. All right. All right. So I'm going to close this up and move this. And it's been a while since I've used this. So anyway, you basically attach this on here. And this guy is called it's the HF50. There's many, many models, HF50, HF500. This will do 50 newtons, I believe. All right. Okay, so now let's see here. And this thing is kind of upside down. All right, so I'm just gonna hold it here, and then I think you can see it. So let's go ahead, let's turn it on. All right, and I think you can see, yeah, that display is good. So the battery's been sitting in a box a while. All right, it's stabilized and it's calibrated itself. Now it's in newtons right now. Can you see that little N there? All right, so let's just put in something we're all a little bit more familiar with. Kilograms, pounds. All right, and kilograms are not force, kilograms are mass, right? But on a planet with gravity, you can say that they're a force based on the gravity. Okay, so we have the force sensor on here. All right, and then we're in LB mode here. Okay, so now let's go ahead and push against this. And as we push against this, see we're getting a negative force, right? Because this direction just happens to be the negative direction. If I pull on it, we'll get a positive force. All right, so now, again, it's like, you think like a few pounds is not a lot, but it is. I mean, I'm pushing quite a bit right now. There's 3 pounds, there's 4 pounds, 5 pounds with my thumb. And I can go more, 7, 8, 9, 10, and I just exceeded it. Same thing on pulling. So now what we can do is, okay, so let's put it back in Newton mode. All right, put it back in. Does it have a scale? No, just Newton mode. All right, so now what we're going to do is this. So again, let's make sure we can read this. There's 3 newtons, negative 5, whatever. Okay, so I can push and pull, whatever. Now let's take this back here. So now I'm going to show you the whole setup. So now what we got here is we got this. On the oscilloscope, we've got our voltage, so we can see our voltage, right? So I'm gonna push this over here, so we can kind of put everything. As a matter of fact, yeah, I'm gonna put this over here because I know that the oscilloscope is over there, and it's gonna kind of be occluded. Yeah, we'll put it up in the corner. That's what I'll do. Okay, so there we go. All right, so here we go. So now what I'm gonna do is I'm gonna push on this, And now, let me see that so you can see that number good. So we see the voltage moving on the oscilloscope. We see the force moving here. So then what you would do is you would basically test the test force. So there's 3.7 newtons, and there's the voltage for it. And then I let off. There's 1.5 newtons, and there's the voltage for it, and so forth. So we would actually calibrate this and manually do this, create a table. Now I'm sitting here with my fingers on this doing it, but we would put actual loads on it, and 1 Newton, 2 Newton, 3 Newton, 4 Newton, and you can actually get loads, pre-made weights of an exact weight, and then that way you could apply it here to create that curve, and then we know what our voltage is, and then that's how we create our lookup table, and we can create our perfect scale. All right, so that is using the force sensing resistor. Cool little device. You just need an op amp, a couple parts. Maybe you want to calibrate it, or you can just kind of eyeball it and do it yourself and figure out what the forces are, but that's that. And that's all there is to it. Let's take a quick look. I just want to show you this right here in case you're interested in buying one of these. All right, so back here, let's go back here and let's go to, I already found this on Amazon. So if you just search for HF50 force meter, they'll start coming up here, and they're not cheap. 130, 115, so about $100, $150 to get one of these. And that's it. That's exactly what I just showed you. And then again, they have them. This one's a 500 Newton, mine is a 50 Newton. Now, the higher, so again, depending on the price, if it's 500 Newtons, it'll be less accurate. If it's 50 Newtons, it'll be more accurate, usually for the same amount of money. Or you can get a 500 Newton that's just as accurate as a 50 Newton, but it's going to be a little bit more. All right. So that is it for our force sensing resistor bonus lecture. So I hope that you like that, and you can use these sensors to make something cool. I don't know. To check, one thing might be cool is use the sensor on a little cat door, dog door. It opens up the door, closes the door, something like that. Or you could put one behind a wall and just push on a wall and no one would ever know. And it, flips a switch or does something or turns a light on or closes a door, secret passageway. Anyway, so that's it. So I will see you in the next bonus lecture. Bye. Welcome everybody to Crash Course Electronics and PCB Design. This is another bonus lecture. So every month, for those of you that are new students, we're going to have a bonus lecture, usually on something electronic based, right? It's an electronics class. However, it could be on software or firmware or something more advanced or less advanced. It might even be on something mechanical or 3D printing, gaming or retro related. It's just kind of dealer's choice, whatever I kind of feel like would be cool to talk about. So this month, I had a project all set up that I was going to do, which now I can't remember. However, I was talking to a friend of mine, and he was talking about solderless breadboard power supplies. So these are these power supplies that you can plug into a solderless breadboard. So we've got, one of these right here, solderless breadboard, and a lot of you may even actually have one of these. You can plug them in to the breadboard and power it off USB or something else, a wall wart or a wall adapter, and then you kind of have a 5 volt, maybe a 3.3 volt power supply. So you can get these things on Amazon or eBay or Banggood or whatever or wherever you shop at. However, there's a pervasive problem with all of these products, at least the great majority of them. And that problem is they don't work. They are broken. They are poorly designed and do not do what they're supposed to do. So in this lecture, not only are we going to design what you see on the screen right here, which is a power supply, a solderless breadboard power supply. We're going to design this. Now we're not going to go lay this whole thing out because it would take hours and hours, but we're going to look at the schematic, we're going to go through all the parts, and we're going to go through the thought process I had as I laid this out. And of course, you're going to learn to do all this in section 8 of the course as you go through PCB design. So if you haven't gone through any of the course and you're just skipping and looking at a bonus lecture, you're still going to get a lot out of this. All right, so just follow along. All right, so anyway, what we're going to do is we're going to kind of go through taking a look at some of these other products. We're going to go on the bench, and I'm going to prove to you that USB ports do something that these power supplies do not compensate for. And then we're going to come back and we're going to work on this PCB, we're going to look at the schematic, we're going to look at the layout, then we're going to get it ready for manufacturing, and we're going to, go manufacture it. All right, so that is the plan. All right, so let's start. Let's see here. Before we start, a couple things. So everyone knows I'm a game developer, a gamer, a retro gamer. I build game consoles. I used to write video games, so it's a big part of my interests. And even though I'm not currently developing video games, I still am very interested in it, and I always get the itch to make one. Anyway, I like to keep up my reading with different things, and so a couple things just came out, which is kind of cool. So this right here, if you can see this, yeah. So this is the Stella Programmer's Guide, and Stella was the chip inside of the Atari 2600. So this is a very, very cool book. So this is, I think this was written in like 1979 was the original date. Yeah, 1979. So this was by Steve Wright, and this, I read this back in 1979, if you can believe that. And yeah, I mean, it's only like 50 pages or so. Yeah, it's like literally 50 pages long is the end of the book, 50 pages. But this was all we had to kind of program the Atari 2600. It was very hard to get your hands on. Anyway, it's been kind of reconstructed and cleaned up, and you can get that online if you just kind of, I think it's on Amazon. I think that's where I got it. So anyway, the Stella Programmer's Guide, if you're a retro game fan and kind of want to understand how the Atari 2600 worked, which is a really interesting model of hardware, I highly recommend that book. It's like, the classic book, 1979, long, long time ago, right? And then, so there's another student, I'm sure there's many students in this course that are into retro game development and hardware and so forth. And one of the students, his name is Derek Morris, and he just wrote this book, and I thought I would put it up here. So this is his new book here, all right? And it's just called Retro Game Dev by Derek Morris, and it's about the Commodore 64, which is an awesome 8-bit computer from the 80s. And depending on who you listen to, it was the best-selling computer of all time, and it sold, I don't know, somewhere, depending on, again, where you get your information, it's 15 to 20 million units, crazy number of units. Anyway, the Commodore is a great machine to do graphics on. It has sprites and you can do tile graphics, you can do bitmap graphics. It has a very advanced sound processor for the time. Anyway, this book, which you can kind of go online and find on Amazon, or you can get it in other places, Retro Game Dev by Derek Morris, it takes you through and kind of teaches you a little bit of 6502 assembly language and kind of how to get sprites on the screen, and he makes a couple games in here, a space game and a platformer. So very cool. It's a pretty short read. It's about, I think it's 120 pages maybe. Yeah, about 120 pages. So you can read it at night. I read it in one night, and I was very happy with it. It's very, very well done. So, check out that book if you're interested in that. So those are a couple things. That's why I said these lectures are going to kind of be all over the place with them. Was there anything else I wanted to show you guys? There was one other thing. So I've been working on a new game console, which I can't say what it is. But anyway, so here's the first PCB of it. And so this is much larger than it. It's very small, but this is kind of how I evaluate it. So I'll put this together and check it out and see if it works. And then if it does, then I'll continue shrinking it. So anyway, so that's kind of cool. All right, so let's go to Amazon here, and let's see what I am talking about. So if you type into Amazon, solderless breadboard power supply. So a lot of you are on a budget, and a desktop power supply or a bench power supply, can cost anywhere from $50 to $5,000. So my power supplies are a couple $100, $150, and then that one's about $300. And then I've got another one over here, a Rigol, which is about $800 or $900. So they're not cheap. And that's because they have to be very low noise, very precise. They have to be able to regulate the line, regulate the load, and be noiseless, all those kinds of things, right? And again, during the class, you'll learn a lot about this because we do power supply stuff inside of the course. But anyway, if you just want to get a power supply to kind of plug into your solderless breadboard to make some of the projects, even in this class, and you just want your 5 volt and 3.3 volt supply, then you can get these little products, which are pretty cool, but there's a big problem with all of them. So if we scroll down here, we see there's kind of this product here, there's this other product here, and there's different variants. So let's take a look here. We'll take a look at this one right here, JBEC, and they're all the same thing, right? So you take a look at this product right here, all right, and you can see it kind of plugs in on the solderless breadboard there and there, right? And then there's a jumper, and the jumper basically, so there's 2 regulators on here. One's a 3.3 and one's a 5 volt regulator. And then on each one of these rails, you can either pull the jumper off and not have any voltage, or you can move the jumper and select either 5 volts or 3.3. So it allows you to put 3.3 and 5 on either rail or nothing. All right, so that's cool. Then there's an on and off switch. Then it takes, this particular version takes a USB connector. All right, and then it also takes a 2.1 millimeter wall adapter power supply, and then it's got a little green LED. All right, so we're going to get into why this is such a bad design, but just starting off, we can see we've got these 2 regulators. These are linear regulators, right? And again, if you don't know anything about electronics yet, so there's two different classes of these regulators. So one is called a linear regulator, and basically the linear regulator, if you put in a higher voltage and you want a lower voltage out, it basically burns that voltage through resistance. So it controls a feedback loop, and it basically applies a larger, smaller resistor, and then it reduces that voltage so that on the output of the regulator, you get your desired voltage, and no matter what's happening to the input, it will maintain that. Also, no matter what happens to the load, as you increase or decrease the load, the voltage will stay the same. Linear regulators are fine, but they're very inefficient, and they burn a lot of energy, and they get very hot. There's also another problem with a linear regulator. If you're trying to regulate a voltage, let's say you want 5 volts, typically you need a voltage higher than the 5 volts as the input. And depending on the quality of the regulator, like if it's old 7805, you may need a couple volts. So if you want to regulate 5 volts, you need 7 volts always or higher to maintain the regulation. Now, we have what are called modern LDO, or low dropout regulators, and these regulators require anywhere from 0.2, 0.3, or 0.4, maybe 0.5 volts and higher, but the whole idea is they require a lower voltage over the regulated voltage. So say if you're trying to regulate to 5, you could probably find an LDO regulator that could maintain that 5 volt regulation even with an input that would drop down to say as low as 5.2 or 5.3 volts, but it still has to be higher, and it has to be higher by a large enough margin so the electronics can work in there. Okay, so we'll circle back, but there's a big problem because these linear regulators on here, these 117 AMS 1117. There's a 5.0. You can see the 5.0, and you can see the 3.3. Let me see. Can I click this? Yeah. And 5.0 and 3.3. So we can look this up, and we can look the specs up of this. All right, and we will. All right. So let's go back. All right. So that was one. There's another one, and there was another. There's another like smaller one. Let me see if here we go. So here's another one. And you can see they all kind of follow the same thing. And then this is a common theme. What happens is someone sees an idea and they copy the idea, and they just keep copying the bad idea over and over and over. And this happens a lot. So you can look, it's still got that same exact chip, AMS 1117, AMS 1117, 3.3, 5.0 volts. It's almost an identical design. It's got a couple switches this time, which is cool. All right. And then this time it's got a mini USB connector, so mini B USB connector, and it's got a couple capacitors on there, LED. Things are moved around a little bit, and then this component here, this looks like a fuse, a polyfuse, but it's the same design again. All right, exactly the same, and it's not compensating for the problem I'm going to tell you about. All right, and let's see, is there anything else? That one, and looking around. And of course, there's hundreds of these. You can just go online and find all kinds of crazy variations of them. All right. So anyway, what I did was I looked through all of these, and I looked at some of the design elements they had, and then said, let's build a better one within reason, within time and space here, because we don't have, forever. We've already used up like 12 minutes or whatever of video just talking, kind of explain. All right, so what I want to do now is let's talk about the design of something like this. So we know we want this to plug into a solderless breadboard. So we have a number of things that we need to consider, right? And one of those things is how big is a solderless breadboard? So we're going to go over to the bench at some point, and we're going to start mucking around and measuring stuff. So we got to worry about how big is the solderless breadboard. For example, this thing has got to kind of plug into these two areas right here, and then kind of wrap around this, right? So the question is, what's the distance between there? Interestingly, it's not standardized. So what is standardized is the middle here, in the middle, from one side to the other. This is 0.3 inches always, because ICs, standard DIP packages, dual inline package, they have 0.3 inches between them. So this is 0.3. So, one hole from the top to the bottom is 0.3. We know that. But from here to here, there's no real standard, so it varies. All right. Anyway, so I had to measure this with calipers under a microscope because I literally couldn't find this, and I figured out it's about, I think it's a 42 millimeters from the two inner rails and then 47 to the outer rails. But we know that if you can measure one rail to one rail, the other rail is 0.1 inch. So one thing is true, it's always 0.1 inch between these rails. So anyway, we need to make that line up. All right, so that's important. Okay, now the big problem that we said about these kinds of power supplies is that they're based on two different kinds of inputs. All right, so let's go back real quick here and let's pop one back on the screen. This one. All right, so we can get the input from this adapter, this DC adapter in. Now, if we do that, depending on their design, and we're assuming that they're doing what I'm saying they're doing, and they are, let's click this. What's happening is this DC supply is coming in here, which could be very high voltage. It could be 9 to 12 volts DC or 6 to 12 volts, someplace in there, right? And that higher voltage is then going to go into each one of these linear regulators. Now, if it's a really poor design, what they're going to do is they're going to put the DC voltage into the 5-volt regulator first. They may regulate it down and then put that into the 3.3 volt regulator and then regulate that down. That is a big, big, big no-no. Typically, you don't want to do that. The reason you don't want to do that is because, say the 5 volt can support 500 milliamps, right? Okay, so it can support 500 milliamps of current. You take its output, then you feed it into the 3.3. Let's say it can support 500 milliamps of current, right? Well, wait a minute. The 5.0 is feeding the 3.3. So let's say the 3.3 wants to pull 400 milliamps. Well, that leaves the 5.0 with only 100 milliamps left to supply other 5-volt devices. So that 3.3 is kind of artificially sucking away current from it. You don't want to do that. So what you want to do is when you have a DC input, you want to separately send it to all of your different regulators, unless one of your regulators is a very small regulator and it's not using a lot of current. So in other words, if we kind of go here real quick on our drawing program, and we go here and say here's our DC, and then let's say this is 6 to 12 volts, right? All right, so there's our DC line, right? Say this is plus, and then we've got and we're just going to do this as a block diagram here. Let's say that this is a 5-volt regulator here. All right, so then we're going to get this nice 5 volts out, right? And then let's say that we have this 3.3 regulator here, right? And then out of here, we're going to get this nice 3.3 volts. Okay, what we don't want to do is this. We don't want to take this and put this into here. All right, you could, there's nothing wrong with it, but you siphon current away from the 5 volt. So now the 5 volt going to other devices is going to have a reduced current output. Bad, bad, bad. So what we want to do is let's put that V back on there. What we want to do is take this and go like that, just in parallel. And then if you had more regulators down here, more regulators, say another regulator for 1.8 volts or something like that, again, we just go like that. All right, and we just do all these in parallel. Okay, that's how we want to do this. And then additionally, if we have them all in parallel, say if the 5 volt got noisy for some reason, right? Well, if the 5 volt was over here feeding the 3.3, and then the 3.3 was over here feeding the 1.8. Well, that noise is going to then go here, and then it's going to go here, and then it's going to go here, and then it's going to go here. You're going to have noise everywhere, right? But if these things are all separate, right, if they're separate, if there's noise there, then the 3.3 doesn't notice it, the 1.8 doesn't notice it, and so forth. So that's how we want to design these power supplies, okay? All right, so let's go back here. Okay, so now what I want to do is I want to go on to the bench, and we are going to quickly, I'm going to prove to you a problem. And the problem is this. So if we have the wall adapter powering this with 6 to 12 volts, that will be enough voltage to maintain the 5 volt supply. The 5 volt is the problem. The 3.3 volt, if we have 5 volts or 4 volts, it'll probably be okay. It'll maintain regulation depending on these regulators, this AMS 1117, which we're going to look up in a second. But the 5 volt is going to be a problem. Let me tell you why it's a problem. If you look up the USB specification, the USB port specification is something like the voltage has to be 4.7 to 5.2 volts, and this and that and so forth. No one follows it, maintains it, whatever. So a lot of these USB ports could be 4.7, they could be 5.1, they could be 4.8, they could be this and that all over the place. That's if they are, say, a computer port, right? Then they could be on a powered hub, or they could just be a charger, right? A USB charger. All of these are supposed to be dead on like 5 volts, but a lot of times they're higher than 5 volts. And the reason why they're higher than 5 volts is because a lot of times you have to go over a cable, and that cable is going to have a big voltage drop over it, 0.2, 0.3, 0.4 volts. You'd be surprised what a cable drops when you're dragging an amp of current or 2 amps of current through it for, say, a pad that you're charging, an iPad or an Android pad. A lot of current gets sucked through there. So they compensate by making the voltage higher. And then typically these are going into charging systems. But the voltage is not regulated. It's going to be all over the place. So depending on what the load does, right, that voltage, that 5 volts, is going to keep dropping and dropping and dropping. So here's the problem. If this regulator, this 5 volt regulator, requires, say, 1 volt above 5 volts to maintain regulation, well, already that's not going to work because the USB input, maybe if we're lucky, is 5.1 volts. So there's no way it can regulate because it would need to be 6 volts for that regulator to regulate. So the problem is that the moment we plug anything into this, the regulator basically is not going to be used. It's not going to regulate anything. So as we connect our electronics up to the 5 volt supply, when this is in USB mode, when a USB cable is plugged in, either a power supply or a powered hub or a computer, that voltage is going to be less than 5 volts when we apply loads to it, and it's not going to be regulated at all. So you have a completely unregulated power supply for the 5 volt. Every single one of these has this problem. So how do we fix this? Well, we fix this with a proper power supply. We put what's called a boost converter, which is a switching power supply, on that 5 volt line, so that as that 5 volts goes down or goes up, right, we can put what's called a boost buck converter, so it can compensate if the voltage goes lower or goes higher. No matter what the input is, the output will always stay at 5 volts. So as the input goes like this, the output will stay at 5 volts, and that's what we want. So that's what our system's going to have. But I want to show this to you because a lot of engineers make this mistake. A lot of I know engineers that have been doing it 20, 30 years. They make the assumption that the USB is a regulated 5 volt supply, and it is not, right? And then if you try and use that in a digital system, maybe you're getting 4.7 out, maybe you're getting 4.9, maybe you're getting 4.6 as the load in your system changes. But one thing is for certain, if you have a regulator like this little solderless breadboard, it is not regulating. That chip, you might as well take that 5 volt out because it is not doing anything. That 5 volt regulator, that AMS 1117 in this particular case. Okay. So I want you to meet me over at the bench, and we're going to do some quick experiments, and I'm going to prove this to you and show this to you, all right? So I'll see you over there. Okay, so we're over here on the bench, and oh yeah, this is from Jiu-Jitsu, so that's a mat burn, so excuse that, sorry. So anyway, we're over here on the bench, and we've got a solderless breadboard here. We've got another one here, for example. You can see they're almost identical. All right, so the one thing that I had to do, like I said, was take a pair of calipers, right? And these are called calipers, and they work in, these particular ones are millimeter or inch, all right? And then you basically measure, so if you put it in millimeter mode, and then we sit here and we measure this, right? and we want to go to the outside, say the outside to the outside, and make it exactly. And of course I did this under a microscope before, so it's roughly 47 millimeters, right? And then we know that from this point to this point is 0.1, and from here to here is 0.1 on the other side, right? So that's how you can kind of figure this out. So when we're doing our mechanical design, we're going to kind of do this kind of thing, this kind of thing, this kind of thing, this kind of thing. That's where I got those numbers from, all right? Okay, so what I want to do, let's zoom in a little bit so we can see what we're doing here. And this is going to be super cool. All right, so this is going to be cool. All right, so I've got this little board here. Let's forget about that for a second. And what I want to show you is I've just got 3 random power supplies here. Here's an HTC. This, of course, is an Apple. This is a real Apple power supply. This is a 1 amp. Now, if you look on here, what's interesting, all right, and of course, they write this totally small, absolutely miniaturized writing. This one's supposed to be 5 volts at 1 amp. 5 volts at 1 amp. All right, fine. This one is supposed to be 5 volts at 1.5 amps. Okay. And this one I already know is 5 volts at 2 amps. This one's a 10 watt. All right. So that's what they say. Okay, so that we have that kind of thing. All right, so we're going to kind of test a couple of these, or maybe we'll try and do all 3 if I can go fast here. And we're always up against time because I have to do this in one lecture. Now here's another little device that I suggest everybody have. These are like $5 on Amazon. And this is basically an inline power monitor. So it measures the voltage on the USB port and the current flowing. This is very, very helpful. So the second that you power this up, this display will turn on. You can kind of tell what's going on, right? So this is a very useful device. These are like $5. And this particular one is called Power Jive. Power Jive. Cool. All right. So what are we going to do? What we're going to do is we're going to create a test circuit, and to create a test circuit we are going to need a USB cable. So we're going to need a USB cable, which is right there, and we are going to then create a cable, and in the course I create many cables, and I show you how to do this. But basically, this has been cut open and then been soldered on here, and then this is shrink tubing so I can see everything, and I've exposed +5 and ground. So typical standard USB cable has 5 volts ground, which is called V-bus is the 5 volts ground, and then it has data plus, data minus, and it also has a couple other pins depending on the version. There's an ID pin, but all we care about is +5 and ground. All right, so we need a way to contact this so we can measure this voltage, right? So then that's what that connector is for. Then I've got this little right angle connector right there. So I'm just going to put this in here carefully, always carefully. Everything is careful. All right, so keep that right there. All right, then I'm going to just kind of safely wrap this cable here. Now what I'm going to do is I'm going to go plug this cable in to, let's take the little Apple one. All right, so now we're doing, basically chargers. All right, just USB dumb chargers, not even a PC port. Okay, now we're going to get our meter. All right, so here's the meter. And then what I'm going to do is, as usual, I'm always fighting to try and fit things on the screen here. Oh, that's not bad. Okay, so we'll put that right there. Now we're going to put this meter into voltage mode. All right, good enough. And there are the probe leads. And now what I'm going to do is I'm going to connect this over here. All right, so this is going to allow us to measure the voltage. So basically we've got the +5 and ground, and now I'm measuring the voltage. So this is the no load voltage. There's no load on here, right? And here's the 5 volts from the USB. And so what we're going to do is we're going to put a load here, all right? We're going to put something on there that's going to drop the voltage, and we're going to drive some current through it. And the question is, how is this voltage going to change? So right now it's 5 volts, all right? And remember, we're going over this cable. This 3-foot cable, all right? So there's going to be a voltage drop over the cable, all right? So I'm going to grab some resistors here. Okay, so right now we've got 5 volts here. So my problem is that if we were to put this into a linear regulator, I guarantee that linear regulator can't regulate this, okay? So at best, it would pass this, and we would get this 5 volts out. So we basically, we're using one of the solder breadboard power supplies. We hook it into our system, and the regulator on there is not doing anything, so we're going to get this voltage out of there. Okay, fine. So we put, say, a 1K resistor, okay, brown, black, red. All right, and we put that on there. All right, and then we're going to get a little current through there. How much current are we going to get? V equals I times R, right? V equals I times R. Okay, so I equals V over R, right? So what do we got? We got 5 divided by 1,000, all right? And so that equals, right, 5 milliamps, right? 5 milliamps. Okay, so that's 5 milliamps. 5 milliamps, nothing's happening. Okay, that 5.07, you know, went back up to 5.08. Okay, let's get a little more brutal. Here is a brown, black, brown. So what's that? That's 100 ohms. So that's going to be 10 times more current, right? So that's going to be 50 milliamps. Now look at that. We dropped to 5.02. Still tolerable. I'm okay with that. I'm okay, right? But our regulator is definitely not regulating on that solderless breadboard we bought, right? If we were to buy one off Amazon, it does not work. This one is brown, black, black. This is 10 ohms. So now we're going to have 10 times more current, or 500 milliamps, all right? Okay, now let's see what goes on here. Oh, look at that. 4.5. So we surely don't have 5 volts in our digital system. So if we had a analog digital, digital analog, if we had whatever, we're definitely not getting 5 volts. If we had a processor that we're running really hard, like a microcontroller that requires 5 volts for a certain clock rate, we're probably not going to be able to maintain that clock rate with that voltage. And as we're changing this load, this thing is not regulating at all, and that's got pretty hot because there's no regulator. Again, the solderless breadboard that we got off Amazon, if we got one of those, since its voltage is too low, it can't regulate. So at best, we're going to have whatever this voltage is as this changes. And we just saw it went from 5.08 all the way down to like 4.6 as we changed our load. And that's exactly what an electronic circuit does. A load's constantly changing, and this voltage is all over the place. Wow, no good, all right? So that's that. Now what I'm going to do is so all these power supplies basically do the same thing, okay? So now what I'm going to do is I'm going to plug in this cable and do a couple other quick things. So now I'm going to put it into a powered hub, which you can't see. All right, so I've got my powered hub. Now look at this. Now the powered hub is interesting. Over the same cable, now it's at 5.25 volts. So this is compensated for the voltage drop over the cable and given a higher voltage. Well, if you're looking for 5 volts, guess what? We just got 5.25 volts. And again, our regulator probably can't regulate, especially if it's a linear regulator and not an LDO regulator. 0.25 or 250 millivolts is still very hard. That's right at the edge of what a LDO is capable of. They need usually 0.3 volts or higher as the voltage to maintain regulation. But let's see how this acts. So maybe we could regulate that with an LDO. But let's go here. Let's just skip to the 100. There's 100. Uh-oh, we just lost regulation. So now at best, we're getting this voltage, and then let's go ahead and let's put this other load, this 10 ohm load, all right? And look at that, we're at a beautiful 4.5 volts. Okay, and then let me show you this. So now, that's with this one little cable, and then let's just say we had a longer cable, okay? So what I'm going to do is I'm going to get a 10-foot extension cable. So again, you might, have to, so here's a 10-foot extension cable, USB extension. Maybe you have to power something, from across the room, I don't know, but you put a long cable in and you don't really think about it. Wait a minute, this cable has got, 22 or 24 gauge wire. There's not a lot of conductivity in such a small piece of wire, so the resistance is fairly high at these high currents, and now things are going to get even worse. Okay. So now we're at 5.2. We were at 5.25 unloaded, right? Okay, so let's put our 100 ohm in there. Let's look at the damage done. So 100 ohm, we went down to 5.1. That's pretty ouchy. And remember last time we were down to like 4.5. What are we going to go down to now with our 10 ohm load? Oh, 4.3. Now we're nowhere near 5 volts. We are out of 5 volts. We cannot call that 5 volts. We're going to call that 4 volts at best, right? Okay, so the point is if you want to build a power supply that's going to be powered potentially off USB, you must consider the 5-volt USB line is not going to be 5, it'll be higher, it'll be lower, it won't be regulated, it won't be regulated well, the cable drops, so you have to have a buck boost converter on there. So that's number one design. On the 3.3, you can definitely get away with just a linear LDO regulator because the voltage is going to be usually around 4.5 to 5 volts, and you'll be okay with that. So that's one important thing. So number one thing I want you to take away, don't make assumptions, measure everything, test things. See, I got just 3 of these out here. If I was building a product, I'd have literally, well, I do have about 100 of these supplies, about 100 of them. I have about 20 different hubs. I have at least 100 different kinds of manufacturers of USB cables. So when I make a charging system for someone or a power supply for a company, I test all of this. So I don't play around. You have to test things and not make assumptions. All right, so I think, let's see, is there anything else here that I wanted to mess with? I'm trying to think, is there anything else? I just wanted to show you that. I think we're good. I think we're good. So let's jump back over to the computer and let's finish our work over there. All right. Okay, so we're back on the computer. The first thing let's do is let's go and take a look back at that power supply. So it's using this AMS 1117 regulator series. Okay, so let's go take a look at that. All right, so AMS 1117, and this is a great company, AMS. I use a lot of their parts, and if it is AMS, and let's just do a general search, AMS 11117, we'll just say regulator. Here we go, Advanced Monolithic Systems. All right, and here's the data sheet for it, for this AMS 1117 series. And if you can't find it on DigiKey, typically you can find it on Mouser, which, let's see, these are all Mouser. Let's crack open another Mouser here, and let's type in AMS 1117. And then also for those of you in other countries, a lot of times there's Element 14, Newark, and so this is not coming up here either. All right, so let's just go back to the data sheet that we found. All right, let me make this a little bit big so you guys can see it. All right, so what do we got? So 1 amp low dropout voltage regulator. Okay, so this AMS 117 is a low dropout or an LDO, and 5 volts to 3.3. So they've got all these different voltages, or it's adjustable. All right, now let's go look at what that dropout voltage is. All right, that's what we're concerned about. So we're going to go look at the 3.3 volts here, and 3.3 volts, and this is, well, this is saying if VN is 4.8 volts, here's what these voltages are. So 3.32, 3.3, 3.349. That's kind of showing you the variation there. And then here's the line regulation. So it's the line voltage changes. What are the percent changes? And then load regulation is as the load changes, how does that change too? So these are kind of the specifics of the regulator, but we're looking for this dropout voltage, all right? So you gotta parse through these data sheets. And again, if you're just jumping here and looking around, this probably looks like complete alien Klingon to you. However, you'll learn all this inside of the course. Here it is right here. So dropout voltage for all of these things is saying it is about for any of these, for 1% and I out at 0.8. Okay, so they're basically saying if you're pulling like a lot of current out of here, you're going to need at least 1.1 volts, and 1.3 is the most you'll need. All right, so the bottom line is for the 3.3 volt regulator to regulate, you need to have 3.3 plus 1.1, and at worst case 1.3. So 3.3 plus 1.3 is 4.3 is 4.6. You need 4.6 volts to maintain that so that things will work. So the 3.3 would actually work, but will the 5 volt work, right? Well, the 5 volt, 5 plus 1.3 is 6.3. The USB is nowhere near 6.3, so it won't work. So all of these designs are flawed. They're flawed when you have the USB plugged in, and it won't work. It will not regulate, and you will not have 5 volts. The 3.3 will probably work and probably be okay, but the 5 volt will not. Okay, so I just wanted to prove that to you. Now let's move on, and let's go back to our design. All right, so this is kind of the final product here, and so we're in Circuit Maker right here. Again, if you haven't taken the course, you don't know what Circuit Maker is yet, but this is the CAD tool that we're going to learn. Let's look at a couple features of this just from the graphical perspective. So ours has the barrel connector, so you can put a wall adapter in here. Then we've got a USB mini B connector, and I like these. These are much more hardy than the micro ones. The micro ones are just horrible. They strip after a while, and they're just no good. So I like sticking with this one right here. Everyone has those cables. We've got a on and off switch. You got a little LED here. Then we have switches here. We've got switches. So you can turn and switch from 3.3 to 5 volts, 3.3 to 5 volts, and then these go on each one of these rails. And then one thing you got to be careful of is the rails, the way that these are oriented on the solderless breadboard usually is it's plus, plus, minus, minus in this orientation. So whatever you do, you'll always have plus and minus, and if you look at one of these boards, and I'm going to get the orientation here correctly. Yeah, so if you look at one of these boards, from this side, as the numbers count 1 through whatever, typically that's the way you're going to put the board. You're going to, people count from the left to the right. So then we would put the power supply here. So if we put the power supply here, it looks like the bottom rail and the bottom rail are the plus rails, and that's exactly how this board is designed. The bottom rail and the bottom rail would be the pluses. Okay, now, and remember, I've actually had a student ask about this. This is just wire in here, right? You could put plus or minus here, you could put plus plus, you can do anything you want. These are just wires. So there's a wire in here connected all the way across that row, and then on the next row there's a wire connected all the way across the other one. So they're horizontally connected. Then here they're vertically connected, right? That's how those work. And again, we're going to learn all of that if you don't know that. Okay, so here's our 3.3 regulator, and this one is an LDO regulator. And you can see there's a lot of capacitors here. There's this FB1, this is a ferrite bead for filtering, and this is a low dropout, so this will work no matter what. Then here is our 5-volt regulator. Now this right here is a buck boost converter. So if the voltage goes higher or lower than 5 volts, it will maintain that 5 volt no matter what. So this is a little bit more advanced, and this is an inductor. And you can see there's a lot of components around here. These are mostly just for good design that I put in. Both of these can work with less components, but we want to make it very noise-free, a quiet power supply. It can tolerate voltage spikes and noise and all kinds of stuff. So that's what we're going to go look at in the design. And then let me turn this over. There's another feature here. So I threw on a couple of these terminal blocks, are called, and I put the grounds next to each other, and then here's 5 and here's 3.3. So say you don't want to plug this into anything, you just want to use this standalone, you could plug it in with the wall adapter or the USB connector, and then you can just run wires off here. All right, and then notice there's no mounting holes. I don't want to make this thing any bigger, and I didn't just want to put random holes in here to kind of support it. I prefer to put rubber feet, so you could just stick rubber feet under here, under here, under here, under here, and this thing would sit up on top of the height of a solderless breadboard. Let's flip to the other side. All right, here we go. There we go. So there it is, the Raptor power supply eliminator, Raptor PSX power supply, Terminator Eliminator X, Crash Course Electronics PCB design. So this is a two-layer printed circuit board, and it's got top and bottom text. Normally that would cost a little bit more, but these days you can get the overlay on the top and bottom, and it doesn't cost anything, so I always put it now. All right, so that's it. And we're going to go back to this, but right now I want to go to the design. So we're going to switch here to this view here. All right. And I want to try and do this course and get this lecture within an hour, hour and 15 minutes. So we got about another 20-30 minutes, and we're just going to drive right through this baby. All right. So let's just stay here, and we're not going to go anywhere, and we're going to do this. Okay. Let's go to the design. All right. So we got the design here. All right. So the way I design everything is like in blocks, and that way I can reuse blocks. So what's cool is if I need another 3.3 power supply, boop, there it is. I just take it. I need another 5 volt, boop, I just take it. Right. And so very object-oriented kind of electrical engineering design, and that's a good way to do things if the specification, features, and behavior of these particular power supplies meet your needs for whatever else it is that you're building. All right, let's start from over here. So here's the input, and so as I design this, we always have lots of parts that we can choose from, like the barrel connector, for example, right? So why did I pick this one? Well, typically I'm driven by cost, all right? So I'm driven by cost, performance, availability, ease of use, technical documentation. I have a number of these metrics that I use as I design things. Additionally, we need to make sure that the tool Circuit Maker has a library part in its library of this component. If it doesn't, that means I have to make it. So I'm trying to avoid doing a lot of work. And if I have a part that it doesn't have in Circuit Maker, if I can find another part that's similar, its footprint, its mechanical footprint is similar, then what I'll do is I'll use that part in Circuit Maker, but then I'll put a note and say, I really want to put this part here to myself, okay? All right, so this is the component right here. Shows some of the mechanical stuff, this and that. And then, you know, if you look at the price, it's 87 cents, and at 100, it's 70 cents. I kind of design around the 100 and 1,000 point, usually when I'm pricing things out. That kind of gives me an idea. So it's a very cheap component, but it's not a $2 component. That's too much. And again, I've been doing this 30 years, 35 years, so I have a really good idea of how much things should cost, right? If they're cheap and reasonable. All right, so that's that part. And this is a 2.1 millimeter tip positive, barrel negative, and very common. And that's it. So that's what we're going to use. And it can withstand up to 5 amps. So we know we're good with whatever current. All right, then we come in here. And now this is going to come from a wall adapter, which could be either a regulated wall adapter, right? Or it could just be like a switching mode power supply like the Apple one, or it could be a real cheap one, like a big wall adapter. Let's grab one. So here is a wall adapter, and this is everyone's got about 100 of these. This is a 9-volt, I think. Yep, 9 volts at 500 milliamps. So what's in here? If you took the class, you already know there's just a transformer in here and a bridge rectifier and maybe a capacitor, probably a small one because they're cheap and they don't want to give us a good 2000 or 4700 microfarad capacitor to smooth out the ripples. So the voltage, 9 volts at 500 milliamperes, is not regulated. What that specification means, if you pull 500 milliamperes DC, you're going to drop the voltage to about 9 volts, but unloaded, that'll probably be 12 volts. And really loaded, it'll go down to like 6 volts. So the point is that 9 volts at 500 just means that 500 milliamps, it'll be about 9 volts. You can actually pull more current if you're willing to tolerate it dropping down to 6 volts, for example. Point is that voltage is going to be noisy and it's going to vary. So we're going to put a smoothing capacitor right here, a small one. I'd prefer to put a bigger one, but it's big and bulky, so we'll get away with the 220 microfarad. You could put 1,000 on there or 2,200, and you can actually find them in the same size. This one's 3.5 millimeter spacing between the leads, and this is a 6 to 10 millimeter diameter. This is just a generic capacitor. Just make sure it's got a big enough voltage, high enough voltage to tolerate whatever input voltage is times 2. Make everything times 2 or times 3 or stuff will blow up. All right, so there's our input power. Now, here's our mini USB. This is another thing that people have trouble selecting, right? They're like, you know, there's 1,000 USB connectors. What should I do? Well, you gotta go look through them, and you got to decide what you're doing. What are you building? This and that. How much money do you want to spend? So here you can see it's 54 cents for quantity 1, and a quantity 1,000, it's 32 cents. All right, and then this is what the connector looks like. What I like about it is you see it's got Kapton tape on it, that yellow tape, that's heat resistant tape. So this can be soldered on there with a reflow oven or hot air, and it'll survive. You can pull that tape off, so that's real nice. And then it's got those 4 mounts. So this is a surface mount device, right? And then we look at what can it tolerate for current. A lot of times it might have that. So current rated is 1 amp, cool. And mating cycles, how many times can I plug it in and out? 1,500, cool. All that's good. And that's a pretty cheap part. Again, if you don't know what you're doing, you'll just find some expensive part. You can find a $3 USB connector if you like, right? Bad. So anyway, again, that is a part that I like. I like this company EDAC, and Circuit Maker obviously had the component. So there it is. So we aren't using the USB as a USB. We're just using it as a power supply. So we have the positive comes here from VBus, and then all these are grounds. Now, here's the ground, and then MTN 1, 2, 3, 4, those are the 4 mounting points. Bing, 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 and we want to ground all those as well. That's what's going on here. Now, what's all this, this AK? This is obviously a diode if you've taken the class, and this is a Schottky diode. And what we want to do here is, if you've got this one in or this one in, I don't want one of these feeding the other one. I don't want one of them feeding the other one. So these diodes protect the current. The current can only flow from left to right, left to right. It can't go back inside of here. So for example, say if I plug both of these in and one of them had a higher voltage, you could possibly backfeed the other one, but not with these diodes. So this is called a wire or power connection. So current will only flow out, only flow out, and then depending on the impedance of either one of these sources, one will be a source or one will not be a source. If you happen to plug them both in, no damage will occur. So you can plug either or whatever, and everything will be fine. So this is just, again, another diode, and very important, check this out, all right? Let me blow your mind some more. And again, we got to compensate and think about all these things. So to make this power supply safe and robust for these different inputs, which the other guys didn't do, right? I don't think they did. But if they did, then here's another problem. Here's another problem we're going to have. Check this out. So we've got those diodes in front of that USB power, right? Okay, so this is a Schottky diode, all right, again, 36 cents at 1 and it's 6 cents at 3,000. I like it, all right, it can handle 2 amps, it can tolerate a 45 volt reverse voltage, that's all good. Forward voltage, ooh, look at this. So at 2 amps, if you put 2 amps through here, 650 millivolts of drop is going to happen. So wait a minute, with the diode in the circuit, so we didn't even have a diode in that test we just did, a protection diode, we didn't have that. So you're telling me if I drag 2 amps, I'm going to lose 0.65 volts, maybe 0.3 volts if I drag 1 amp. So there goes another 250, 350, 450 millivolts of voltage I've lost. So there's no way I can regulate because I've went from 5 point whatever down to 4.5. Now I'm down to 4.2 on that USB. So you see, it's all smoke and mirrors. It's fairy tales and unicorns. That power supply on Amazon, all of them don't work in the 5-volt mode. All right, unless you plug in a wall adapter and that's running at 6, 7, 8, 9 volts, then that linear regulator, that AMS 1117 5 volt, will have that 1.1 to 1.3 voltage it needs above the regulation voltage. But in USB mode, not going to happen. All right, so that's that part. Say, moving on, we've got a switch here. And so this switch is a micro switch EG1271. And I like using small switches. I just wanted something small on here. If you go here again, and we'll go back in 3D mode. So I wanted something kind of fit here and fit here and fit here. Now, in the best world, I would want the switch to be able to handle more current. So these switches can handle 300 milliamperes per pole, I believe. So we're going to tie the both poles together. Oops. And now we're who knows where. You hit something on Windows, you know how that is. Let's go here. Okay, so in this case, we've got our circuit here, and we're just switching the power from the input here, either input, through this first switch into V sub CC in. Okay, all right. Once we've switched that in, then we've got a little power indicator here to let us know that power is on. We pick a 470 ohm resistor so that if it's being powered from the wall adapter over here, and maybe that voltage is higher, and maybe this voltage is lower, we don't burn out that LED. So 470 should be fine. So even if the input was 12 volts, so we take our calculator and we say, hey, if we had 12 volts as an input and a 470 current limiter, what's kind of our worst case scenario? It's 25 milliamps. That LED will be okay with 25 milliamps, and it won't even be 25 milliamps because the LED is going to drop a couple of volts, so it's going to be even less, maybe 20 milliamps. So that's okay. It'll be really bright in this mode. But anyway, you could play with that. All right, so let's back off a little bit. So now we've got our V sub C in here, and then here it is here, and here it is here. And now what we want to do is we want to put this into each one of these power supplies. All right, so let's start off with the linear one. All right, so again, there's a bazillion different kinds of linear regulators from all kinds of companies. And again, you got to pick what you like and your cost and what company you like working with. So I like working with Macrel parts, and Macrel was purchased by Microchip, I think last year. Anyway, so here it is right here, and here's all this tariff stuff, which is going on with a trade. So tariff applied, so that's good. All right, so anyway, one of them is $1.44 and 2,500 is $1. So it's $1, which is a good price. And again, you could have an input of up to 16 volts, so that's good. And then our dropout is 0.63 at 1 amp. So that means that you take 3.3 volts at 0.63, about 4 volts. So that input better be 4 volts or higher, and we know it'll be with the USB. It'll definitely be like 4.2, 4.3. or higher even with that protection diode, and this thing can output 1 amp. So we're good to go. So we got an amp right there, all right, and that's the part that we're going to use. And sorry, this is, you know, Windows is, it never does what it's supposed to do. All right, there we go. Okay, so that's that, and then if we were to go, as a matter of fact, let's go back here. Let's go back to the data sheet here. Go back to the data sheet, and we'll just click that. They all have the same data sheet, and I believe I already have this one open. Yeah, here it is here. So what you would do is you get the data sheet, and you kind of look through here, and you kind of read, this is the one that we're going to use right here, and you look at what the minimum design is. Okay, so this is a very poor design. A lot of data sheets, honestly, are written by interns at companies, or they're the bare minimum so that the marketing department can say, hey, just with a 10 microfarad tantalum capacitor, this will work, right? Yeah, it may, but it's not going to work very well, and it's surely not going to protect noise and spikes and all kinds of stuff. This is a bare minimum. You need to do more than this, all right? You need to do more. All right, so in my design, power comes in here. We already know we've kind of smoothed things through this one with this capacitor here, but in this case, there's nothing here. We're just going to take that power straight through here. Then we have this ferrite bead, which is going to filter high frequency noise. Then we've got a nice 22 microfarad and a 0.1 microfarad. Now, this whole design is surface mount. These are all 0805 size, so those are what we're dealing with. And they're all generic. So say this 22 microfarad, whatever the voltage is, and you got to be careful of this, whatever the voltages we anticipate, say on this power input, you got to be careful. So I'm going to just say put in 5 to 9 here. Actually, that should probably be, well, 5 to 9 would actually work, but not many wall warts are 5 volts, usually 6 to 9 or 12 volts. Anyway, if you put 12 here, that's kind of pushing it, 12 volts. And the reason why is if this capacitor is such a small component, the higher the voltage, the more expensive it is. So typically you can find 6.3 volts, you can find 10 volts, you can find 16 volt, 25 volt, 50 volt, and so forth. We really would like the voltage tolerance of this capacitor to be twice the input. So if we say from 5 to 9, so that's 9 volts, so it should be 18 volts. Is the worst case scenario this thing has to tolerate. So we'd like to pick something maybe 25 volt, right? So you got to be cognizant of that. Make sure these capacitors can take this input voltage from this input here, all right? And I usually double it, all right? So if you don't want to be that robust, it's going to go to 9 volts. But remember, it's a wall adapter, and it could float up to 12 volts or something. So if you say, oh, I'll just use the 10 volt capacitor, it'll probably work, but over time it will damage it, and then soon it will not work. So I always double it and then shoot for that. All right, so we've got a ferrite bead for high frequency noise, then we've got a couple input capacitors. This one's for smoothing, and this one's for noise. The 0.1's for noise. Then we have our regulator right here, and a ground, and we have our output. Then again, another 22 microfarad. Now a 10 nanofarad, a very small one. Then we have another ferrite bead. Then we have another output capacitor here for noise. This creates what's called a pi filter, and again the class kind of talks about this, and it looks like the symbol pi right there and there, and this just really traps and filters high frequency, low frequency noise. So we just get DC out. Then there's a little thing here. This is a current sense resistor. So this is a very small resistor. In this case, I believe this one is 50 milliohms. So it's like there's no resistor there at all. But what this will allow you to do is put a probe on here. Let's take a look here. So right here, you can plug in like one of these little headers here, and then you can connect that to your meter, and you'll get a voltage will be generated over this tiny resistor. That voltage, of course, is proportional to the current flowing through here. So you can monitor the current coming out of each one of your power supplies right here at the source, which is a nice feature. So that's another feature our design has, is you can measure current, right? Okay. And let's go take a look at that current sense resistor real quick. Where to go? Right there. And again, I'm going fast as always, and that's one thing, you know, if you're taking the course, I kind of talk fast, but we have to. We just have a lot of material to cover, right? We're not making grilled cheese sandwiches. I've said that before, and there's just a lot of stuff to do. All right, so this is 60 cents for 1 or 8 cents for 5,000. It's 10 milliohms and 1% tolerance. So basically, this is like not even there, 10 milliohms. So it's like nothing. So this would be a tiny voltage generated here as the current varies from 0 to 1 amp. So at 1 amp times 10 milliohms is going to be 10 millivolts. So we need to be able to measure down to a tiny little voltage with our meter, so we need a meter that accurate, or you can use a larger sense resistor. You could even use 1 ohm if you want, or 0.1 ohm, right, to get a kind of a bigger voltage, right? And that's fine, all right? And then you can turn it back to a very small one, or you can even make it a short if you don't want this feature. All right. So that's it. That's the 3.3 power supply. Then we've just got a power good indicator. I always like to make sure my power supplies are on with instrumentation. I'll talk about that in the class. Put LEDs on things. It's like printfs and C code, right? Now, here's the bad boy. Here's the 5 volt. So we're going to talk about this in a second, but it's a very similar design. We have the voltage in. We've got a ferrite bead for filtering. Then we've got, now in this case, I've got these 10 microfarad, 10 microfarad. So what I'm doing here is I'm saying, hey, I want 20 microfarad, but I'm going to use 2 of these in parallel, right? So I can make these voltages really high, right? Because I want really high voltages. Now over here, this one right here, this one's 22. So, you know, why couldn't I have just used this one? Well, this 22 is kind of, you know, our suggestion. If we can find a 22 that'll tolerate, you know, maybe 15 volts of input, we'll put that there. But if we can't, we're going to have to drop that down to like a 10 microfarad at like 16 volts. But on this one, we can't. We definitely need more capacitance. So I put 2 placeholders, and let's start with 10 microfarad at like 16 volts. If we can find 22 at 16 volts, we'll put those in there, right? And make it like 44, 47 microfarad. But so that's what you'll see a lot. A lot of times when you see surface mount design, a lot of capacitors, they can't tolerate high voltages as these capacitors get smaller. So you'll see people put these things in parallel so they sum up so that you can get that bulk capacitance that you want. And there's our 0.1 for noise filtering. This has got an enable here. This is a little input that needs to have a capacitor connected to it. And then we're going to take a look at this data sheet. Then somehow we get an output over here. And again, 22, 22, 22. But now, wait a minute, the voltage on the output is 5 volts. So it should be 5 volts and it should stay at 5 volts. So we can use a much smaller voltage on the output. I wouldn't use a 6.3, which is another common value. That doesn't make me feel safe because if voltage ever fluctuates or spikes or somehow doesn't deregulates, or this thing is these capacitors over time lose their voltage tolerance and derate, you're going to hit that, you know, 5 volts, 6 volts, and these things are going to be damaged. So I prefer to put a 10 volt here. So 10 volts here, and I'd prefer to put like 16 volt here to make myself feel good at, when I sleep. All right, but anyway, again, I want to put them in parallel because I want that bulk capacitance, because this is a switching power supply, which we're going to take a look at, and it's got noise in it because it's switching. I think this switches at a megahertz, so we want to, you know, really reduce the noise here, bulk capacitors, and then again, here's a small capacitor for filter, then here's a ferrite bead, going to filter high frequency noise. Another capacitor, we have different values here, creating that pi network. Again, we've got our current sense resistor port here, and then we've got our final V sub C out, and then we've got our power good indicator. We're going to swing back to this in 1 second. Now, how do we get the power out? Well, I just drew, here's the 3.3, the 5 volt, and then we have a couple switches here, and then we run those switches to each one of these output rails. These are just those connectors, these things, right here, right here. That's all those are, all right? And we just connect those out there so that we can control each, and then there's those terminal blocks, right, which are these things right here, right? And that's it. So that is the power supply. So it's not that complicated, all right? So now let's go take a look at this actual part here. So again, there's so many of these switching regulators, and some are very complex and require a lot of external parts, which we don't like. We want to keep it simple. This one only requires an inductor. All right, it doesn't require a field effect transistor or a switch or any kind of craziness. So let's take a look at that. Actually, I think I have it, but let's go look at its cost. All right, so there it is. And with Texas Instruments TI, the TPS series has a lot of really cool regulators. TPS, isn't that from Office Space? TPS report, TPS reports. If you are a fan of tech comedy, then you have seen Office Space, and you know what I'm talking about with TPS reports. If not, Google it. All right, so this is a little bit expensive. At quantity 1, you can see $277 and $250. It's $1.82. Switching regulators are not cheap because they're fairly complicated. All right, now let's take a look here. The maximum input is 12 volts, so we got to be careful. in the wall adapter mode, when we've got that wall adapter plugged in, if we do put over 12 volts, we're going to blow this thing up. So we definitely want to say only put a 9 volt wall adapter, and that's the max. All right, this is a 5 volt fixed output. Switch current is up to 2 amps, and this one switches at 2.4 megahertz. I said 1 megahertz, 2.4. All right, and again, we can go to the page. There it is. All right, you can see this right here. This package type, all right, which is called this WFD-FN exposed pad, or WSON, which I forgot the acronym. Bottom line is it's got this pad here for heatsink, and then these connect on it. So this is a fairly hard component to solder. You have to use hot air or reflow oven. You could solder this, maybe, if you're lucky. The way the pins wrap around, it's doable. I've done it before when I was much younger and I didn't have a hot air gun, 20 years ago. I've soldered these, but you want to have a hot air gun or a reflow oven to solder these kind of components. All right, let's take a look at the data sheet. Here it is here. It's a whole series. That's why there's an X here. Let's make this a little bit bigger. All right, so with these things, these are not simple. This is a 31-page data sheet. All right, and it's got some complicated stuff inside of it, some math in it and whatnot. All right, but at the end of the day, you could read all this, but at least just kind of skim through it. I've read hundreds of these, if not 1,000 of them in my lifetime. Probably over 1,000 actually, of different data sheets for these regulators, and made many power supplies. All right, so basically in a nutshell, here we go. So here's a simplified schematic. So the bottom line is VIN and enable are tied together here. We have a capacitor on the input, again, simplified, cheap, not really robust. That's why we have many capacitors. We need this Vaux through a capacitor to ground. This is this PS sync mode. This is power saving mode. This is the package ground, P ground. Here's this feedback. Here's the V out. And then again with the capacitor, and this is this power good. So, and this is with the, this is like an adjustable one that has a feedback loop. So it's kind of showing you that. And then you kind of go in here and read what all these pins do. All right. And then go down here and you kind of see the internal design of this. It's very complex. There's a feedback loop, and this thing adjusts and adapts. And I explain how buck and boost regulators work inside of the class, at least an introductory explanation of them. All right, then it kind of shows you what each pin does. All right, and then what we're looking for again is kind of these simplified designs. So here's like, this one's a 5 volt design here at 800 milliamps. So it needs this inductor, and then it's showing these components right here, and so forth. All right, so you kind of go through here and you figure out your design, and it says some suggestions for the components, right? Suggestions for the components, all right? Okay, so, and you can kind of read through. There's a lot of information in here, like I said. All right, so let's go back to the schematic. Okay, all right, so in this version of it, we basically read through that data sheet, and we set this thing up like this, and this is how it's set up so that it's at a fixed 5 volt output for this particular part, and that's all we need to do. And then we already talked about that. So now we have our electrical design, all right, and we're doing pretty good here. We're doing pretty good. I think we can go about 10 more minutes or ish. All right, so we have our electrical design. So now we go to layout. All right, so now and there are many lectures on layout and so forth, so we're not going to go through too much of this. But the bottom line is, step one was I placed all these components down here, and you're going to learn this tool, Circuit Maker. I placed these components down here, and again, I explained what's my thought process. Well, first, this has to go here, and this has to go here, right? And then I measured and designed the circuit board in this shape so that everything would fit. And if we look at, say this distance right here, so we go right from the center here, right bing there, and I just love the way things, so CAD tools, and I complain about it all the time in the course, these things are massive pieces of software, and they're very broken, even the best expensive ones, which this is based on one of the biggest tools in the universe, Altium Designer. All right, so if you look down at the bottom of the screen, if I move the mouse, you're not going to be able to see it, but if you look down at the bottom of the screen, it says the delta is 47.59 millimeters. 47.5, and that's about what I measured when I measured it with a caliper. So I made it 47.5. All right, and then within the tolerance of the tool, that's how close I was able to get. And then from here to here is 0.1 inch, and then from here to here is 0.1 inch. So that I kind of get for free because the connector itself. All right, so anyway, these had to be placed exactly there. Then it's kind of like, you know, the board's going to lay here. Then I said, you know, maybe I'll let this little lip come over the board a little bit. Then I want to put these switches here, and I don't want the board to collide with the switches too much, and I want to have 3 of these so you can put it into the board really good. So I'll put the switches here. Again, we'll go back to 3D. There's the switches, and on the other side, these switches are going to be sticking out a little bit as we solder them through there. So if the board was here, we don't want it pushing on the board too much, so the board maybe is going to come to here, I think. All right, and then again, then I do this in a block level design. So I pick where I want to put stuff. So I want to put the mechanicals here, and I kind of figure out where I want my mechanicals first. So I want the terminal blocks here. Here's the input switch. There's the USB connector. There's that big bulk capacitor, right? And then here's our 2.1 millimeter wall adapter port. So kind of here's all the mechanicals out of our way. There's our switches. There's our connectors for the solder spreadboard. Then I have to decide, let's put some electronics here. So I started with the 3.3 volt regulator, right? And then of course there's those 2 input diodes, right? And then you notice how these traces are thick. So all the power traces, there's a power trace, there's a power trace are thick, and then non-power traces are going to be thinner. Now, since this is a giant power supply, all the traces are thick. The only time you see a thin trace, here's a thin trace, that's an LED. So that's powering an LED, so I'll let that trace be thinner. But everything else, going to see fat traces because we're going to be pushing a lot of current. Now, we're going to talk about this in 1 second, but when we go to these surface mount chips, well, obviously I can't put this fat trace here, which short all this out, right? This fat trace. So you got to bring it down. No way around it. Just sucks, but you got to do it, and then you kind of make it big as it goes back out, right? But when you go to the surface mount parts, you got to make things back small again, all right? Okay, so there's my 3.3 volt regulator. Now again, I always design things, I want to make them functional, I want to make them cosmetic, I want to make them attractive, and I want to make them logical. And I like to think of things, and I also like things to connect so that I have the least amount of connections to make, or the length of the connections are the smallest as I'm routing. And this is an entire art form, and it may take you years, or some people decades, to get good at this, but it's definitely not something you're going to get good at quick. You're going to have to build boards. Like anything, you're going to have to do it to get good at it. All right. Anyway, you can see how I've got that ferrite B coming in, then we've got these couple capacitors on top of each other, and look, straight to each other, straight to each other, straight to each other, straight to each other. Then you see this one goes here, and this one goes here. Very clean, but also very organized and very pretty. And then, you know, the question, I could have put all these capacitors maybe longer this way, but it's kind of like I'm trying to get these to cluster in a nice small space, and so I can keep these lines large, these traces large. Then over here, here's our inductor. We go look at the inductor here, right? And then the inductor is going to sit right on there. Again, you know, these traces are small. These pins are small, right? These surface mount pads, not much I can do. So then I bring this stuff out here, and then I kind of fan it out. You know, I fan it out, make it big, and there's my inductor, all right? And then we just basically follow the circuit from the schematic and just place all these parts, make it real pretty, right? And here's my capacitors. They're all nice and grounded. Then something that we're going to learn, or you're going to learn when you do the course in Section 8 on PCB design, we're going to talk about this many times, is we're going to talk about noise and EMI and things like that at a basic level, right? You know, it would be a whole year course, again, on just PCB design with, you know, beginner, intermediate, advanced, talking about lots of these things with lots of experiments and simulation and analysis. But rules of thumb, we do what's called via stitching. And these little holes right here are vias, and these punch through the board to connect the different layers of the board for thermal conductivity, and also to make the grounds connect together. And again, if you don't know what that means, you'll learn about it. But you can see there's these holes, these vias, all the way around the perimeter of the board. All right, all the way around the perimeter, and then around the power supplies. So you can see they're just punched everywhere because I want the grounds around here, and I want these things to be thermally solid, and I want these grounds from both the top and the bottom to be connected. And let's take a look at the bottom plane here. So I'm going to go to single layer mode. So there's that layer, and there's our bottom layer. So we've only got a few traces on the bottom layer. Both layers are grounded, so we've got nice grounding, and then you can see these vias much better here. All right, and that's the board. And then again, you can see when I'm running these big power lines. Now normally we want these 45s whenever we take a turn. We want 45s on signals. So there's a signal, you know, kind of a signal, kind of put that 45. But on these big DC lines, these are slow moving lines, only when you get into, you know, many megahertz, hundreds of megahertz, gigahertz, does it really matter to put these 45s, right? So that's for your digital logic and all that. But for power, it's DC. You can go ahead and make these things all 90s, and they just look better when they're 90s, and it's a, you know, a power tree. So you can see kind of power tree, power tree. There's our power tree, power tree, power tree. All right, and then when we're trying to make all these connections here, we, you know, kind of put a little bit of a little turn on them, and just keep everything nice. And we want a nice fill everywhere. This is all ground filled, completely ground filled. Okay, so there's our board, right? And so let's go to the next step here. Let's go, and so we've got the board, and again, you know, you're going to learn this tool in painstaking detail, but let's go to design rule check. Let's go to reset error markers. Let's run the design rules. Okay, I'm going to run the design rule check. There it goes. And oh no, there's all kinds of stuff wrong. Well, let's see what's wrong. Let's just close this. And we look over here, and error 0, warning 0, rule violation 64. Those are rules set up by the PCB tool that I didn't feel like modifying, and they're all the rules are things like this. See, silk to solder mask clearance. This one here is minimum solder mask sliver gap. So all these things are okay for me. I don't care. They're just fine. And many of them are generated because this overlay, the text, is going on top of things. Like here. I don't care. It's just text. I don't care about it. Doing that, that's fine. Everything will be fine. And then some of the other ones are the spacing between here and here is less than 10 mils, and that's kind of the default that the tool's set at. It's probably at 8 mils or 6 mils. It's fine because I know it can tolerate 5. I could go into the tool and fix all of those things, but I still like it to kind of spit them out at me just to say, hey, look at all these things, and maybe there's something I want to change. But they're all warnings, and nothing's going to happen. Okay, so the board is good. So now we can generate the files. Okay, so let's take a look at a couple things that are important. And even though we're going to go over this a lot inside of the Section 8 and the entire sub-course on PCB design, I just want to show you this. So when you have the board, you have to make sure you have a board outline. When I drew this, I basically took lines and drew this thing and painstakingly did this. It's a pain. Then I selected all the lines. Then up here in board shape, I said define from selected objects. And that allowed me to make a board shape. But then at some point, I have to make an outline of the board. So what I did was there's a function here where, again, you can go up here and you can say create, let's see, where is it? Create primitives from board shape. I think that's it. Define from select. Yeah, create primitives from board shape. Create primitives from board shape. Is that the one I want? Let me see. Yeah. So create primitives from board shape. And again, Circuit Maker is not usually the tool that I use. I use another tool. This tool, I don't know everything about it. So some things I can't remember where they are. But these tools are very hard to remember because there's so much anyway. In any event, there's a step that you need to make. After you make a board and you have your PCB and all that, you want to use this function here that we just went through, and we want to create an outline. So basically we say, I want it 1 mil thick. Basically I want it 0 thick. It's just an outline so that the manufacturer knows how to cut the things, all right, cut the board away. And then where do you want to stuff it? You can put it in any of these things. So we say, I want to put it in the outline layer, this layer, that layer, whatever. So when I originally did this, I put it into like mechanical 4, I believe, and then you hit OK, and then it'll generate it. So if we go here and we look at mechanical 4, there's that outline. So when we generate our Gerber file, we need to make sure we copy this file and then put the word outline on it so that PCB manufacturers know that this is the outline. Now there's also this one here. This is another one, but this is one I just drew so I could see the thing better. But this one I'm not going to use because it's too thick. And when the PCB manufacturer decides to cut this, does he cut it on the right edge? Does he cut it on the left edge? Does he cut it on the center? I'm not sure, depending on the manufacturer. Probably should cut it in the center, but why chance it? So that's why I made this other one that's 1 mil thick whichever way he does this, 1 mil thick, worst case, it's going to be 1 mil off, and I can tolerate that, right? So anyway, again, you're going to hear a bunch about this when we do the PCB design part of the class. So just, extra reiteration of that information. Okay, so there it is. And then we go here and we go generate outputs. All right, let's save it. And it's going to save to the cloud. You see a little cloud there when we save things. Yeah, we've been messing with it and stuff. And a lot of times just opening the file and mucking with it causes this to happen. And you have to recommit it and resave it, which is very annoying. All right, and we're about an hour and 15 minutes, so we're good. All right, now what do we want here? Now you could have all these things, bill of materials, schematic print, blah, 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 blah. Don't care. All I want right now is I want the Gerber files, which are the manufacturing files. I want the drill files for the holes. The NC drill files are called, and NC stands for numerically controlled. And then I want, we don't need the pick and place because we're not having robots build this or whatever, but a lot of times I just like to generate that just for fun, but you don't have to, all right? So let's just turn that one off. And now let's go to the Gerber files and look at the configuration. And again, I go over this in detail in the course. So what layers do we want to output? The top overlay, the top paste, the top solder, the top layer, the bottom solder, all those. And then I output both of these outlines. And remember, this is the fat one. We don't really need that one, that GM3 layer. We don't need that layer. So you know what? Let's just turn that off like that. And we do need mechanical 4. All right. And then you can go through all these things, and I talk about all these things in inches, and this should be set for 2.5 and all that. All right. Anyway, so that's good. We go to the NC drill files. This doesn't have much. It's just inches, and it should be set for 2.5, and these should be the exact way you see them here, which we go over in painstaking detail in the course. And that's it. So we're ready to go. Now we say generate. And if we're lucky, it's going to say where to put this. So we're going to put this right here. And then we've got this manufacturing, and then this is the name of the file. I could change it to whatever I want, so I'm just going to save it here. All right, and then I'll close this. Okay, now we have our file here like this. So now what I'm going to do is I am going to extract all into a directory here. All right, and then of course you can find this file. I'm going to show you the name of it on Circuit Maker on their cloud, so you can just search for it. If you just search for my name, you can probably find it, but it's, Crash Course Electronics Power Supply version 001. We'll look at it in 1 second. It's literally this exact name right here. Crash Course Electronics _ Power Supply _ V1 _ 001. There's the Gerbers, and there's the NC drill file. Now, let's go here and look at the Gerbers. Okay, there's that GM4, that's that outline, right? So what I like to do is this. I like to rename this here, just so there's no confusion. All right, boom. Okay, so there it is. So there is the Gerber file, okay, and then there's the NC drill file. Then what we can also do here is we can put this all in one zip, but we can also just take this this file right here, this text file, and if we want, we can just dump it into this Gerber file as well, right? Because this TXT file, it'll open up. So you can kind of do it either way. All right. So what we're going to do is we're going to just take this text file. I'm just going to copy this, all right? And as a matter of fact, we can do this. And there's lots of ways to do this. In the course, I do a couple of different ways. So there's no harm. Put these. The manufacturing people will look through this stuff and figure out what it is, okay? Or their automation will. So we're just going to put this all in this Gerber. I'm going to copy this here. I'm just going to paste this here. And some of these files are not used. This APR, this library, a lot of these are not used, but we're just going to keep them all in here. Okay, now we've got all our files. Let's move this over here out of my way. And I'm pushing into 1:30 here, an hour and 30 minutes total video time. After I edit, it'll probably be 1:15. So we've got to wrap this up. And let's get this tool here. So this is ViewMate. I'm going to talk about this in the course, but right now all I'm going to do is show you. So basically I'm dragging the files in here. Guess what? There's that top layer. That looks good, right? The top overlay. That looks good. Let's see. Top paste. There's the solder paste. That looks good. Bottom overlay. There's that Raptor PSX. It's backwards, of course. Bottom layer is that bottom layer. Looks good. And let's see, anything else fun? Top solder, that's the solder mask on top, and then we should have bottom solder. There's that. And then let's see if the NC drill file will do what it's supposed to do. There's the drill file. And then here's our outline file. And sure enough, so now we have everything we need to do the manufacturing. So let's come back here. So we have all these files. So all I'm going to do is I'm going to literally select all these things, and I'm just going to send these to a compressed file. And I'm not going to call it 001. I'm going to call it power supply. We're going to call it test. We're just going to call it power supply test zip so we can remember. So that's the file right there. All right. Now, let's go build this thing. So we're going to go out here, and we are going to go to, let's go to Osh Park. Here it is. Osh Park. All right, we're here at Osh Park. I'm already logged in. Good. All right, so let's get started. So it just says browse for files, or just drag. I think you just drag it here. So we're going to literally, this is pretty cool, literally drag the zip file, and if everything works, it should find everything and generate our project. And it did. Now, one thing that's very important, I teach in the course and I do in the printed circuit board design, is we're going to go over all kinds of manufacturing, how to look, how to go to different manufacturing companies and all that. So anyway, so we got everything's green light, looks good. We detected a 2-layer board. Here's its size. 3 boards will cost you $1965. All right, and then we can just go ahead and say continue, and you can see them right here. The rendering is really amazing. It's even lit correctly. I mean, it looks real. It looks like a photo. And then it shows you every single layer. So we can see that this is correct. This is what it's going to look like. There's our text in the back. That's fine. You know, crash, the C in course is going to get a little jacked up, but I'm fine. You know, don't have to be completely perfect. This looks really, really pretty. Bottom solder mask, the board outline, bottom silk, top layer, top silk, bottom layer, etc. And then we just go to order. All right, we want PCBs. We want 3 of them. You could order more if you want. This right here, now I believe, let's see, does the price change if I do that? I don't think it does. Anyway, I want 2-ounce copper, so I think this allows me to make it from 1 ounce to 2 ounce, and there's no additional cost. Whenever you're doing a power supply or anything like that, you want heavier copper, so 2 ounce I definitely want. This doesn't do anything, and I definitely don't want super swift service. And then you just hit checkout, put in your address, put in this and that. I mean, these things are literally 20 bucks, and then depending where you live, you can get whatever, right? And then again, we can go to board preview, and we can look at this again just to make sure we're ordering the thing that we think we're ordering. And that's it. So that's an entire process of the schematic design, the board, the reason we're making it, comparing it to the other product that we saw on Amazon, why those products are flawed because of their 5-volt supply, kind of going through everything, generating the Gerber files, reviewing them in ViewMate or a Gerber file reviewer, and then taking those files and sending them to a manufacturer and build it. Of course, you got to order the parts and build everything. Let me talk about 1 minute about that. In the design here, so again, this thing is called Crash Course Electronics. Here's the name, Crash Course Electronics Power Supply version 1001. So if you go onto Circuit Maker and you search for projects in my account, Andre Lamoth, Crash Course Electronics _ Power Supply _ V1 _ 001, you're going to find this thing, and then you can fork it. You can fork it and build it and change it and do whatever you want. All right. Let's go back here. All right. But one thing I want to bring your attention to is these parts. If you go and look at the actual part inside of here, right, the footprint is correct, but I'm telling you I want it 22 microfarad, right? And we talked about the voltage, but look, watch what happens if I click on this. And it'll go here. Look, it says it's a 47 microfarad, 6.3. Why is this different? Well, this is just the description of the generic part that I used for the footprint. Then I went and manually changed it. So when you go and get parts, you're going to get 805 size parts, but you're going to find each one of these yourself. All right, you're going to find a 0805 22, 0805.1, etc. The only parts you know exactly what I want are the Macrel part. See the part, I put the part right there in these ferrite beads. All these capacitors and resistors, this is just generic. This I put the part number, I want you to use that one. This one I put the part number, I want you to use that one unless you want to change it. Look at the generic LED, it's just a generic 0805 and a 220 resistor. Everything's generic. these are very generic, right? These things right here, these headers, it's generic. This connector is pretty generic. The capacitor is generic. These terminal blocks, those are specific. Now, many of them will fit in the same thing. You could order a different, like here they are right here. But you could order different ones. They would probably fit in there. But anyway, use the part number I say, which is this one. So right here, it's this onshore technology, OSTT, whatever it is. And then these switches, I want you to use these EG1271. Again, these are micro switches and they're real small. So if you change the switch, it may not fit. Okay? But basically everything is generic except the chips, these ferrite beads, and this USB connector is very specific. You have to use this specific one. And then on the diodes here, you can use either this one or this one if they have either one in stock. All right, that's when you build your bill of materials. Okay, so I think that's it. And my time's up, and that was a long lecture, about an hour and 15 minutes. So that is all there is to it. So definitely, if you're up to it, go on to Circuit Maker Cloud, pull down this project, fork it, and take a look, see if I made any mistakes. I haven't built it. I actually sent it out for manufacturing, the PCB, but I haven't built one of it. And again, that's something I'd like you to do. Go ahead, build it, see if I made a mistake or whatever, but I think it's okay. And we went over to the design. But the whole idea is I just want to show you how you can take a look at a product that exists, improve it, find its flaws, and amazingly, tens of thousands of people, God, hundreds of thousands of people are probably using those solderless breadboards and they don't work. I guarantee they don't work. If you've got one, check that 5-volt supply. It's not working when you've got the USB port plugged in. Definitely not working. So you're all using broken supplies. And so you can just make something better and make a better version of it and then, of course, sell it. So, who knows? I might take this power supply and maybe add a couple things and manufacture it and sell it on my iConstructs website, right? And that's, just another product. All right, so I think that's it. I hope everyone liked this bonus lecture, and I'll think of something else cool to do on the next bonus lecture. We probably won't do another design. This is kind of big. This took, in the background here, I took a few days to kind of put this together and get it all ready. So I'll think of something maybe a little bit simpler that's not as long. All right. Well, anyway, I will see you in the course. Bye for now. Welcome to Crash Course Electronics, Halloween edition. Did you guys see that? The power's out. It's the week of Halloween, and all kinds of things are going wrong here inside of this lab. Power went out. We're on UPSs right now, powering everything up. That's why I'm in the dark. So I don't know. I've been hearing a lot of things. A lot of weird things are going on. So I don't know. Anyway, it's pretty scary. Now, what we're going to talk about is kind of scary also. H-bridges. And but we're going to try and make it not so scary. H-bridges are not half bridges, as opposed to half bridge and full bridge, which is kind of a bridge rectification for power. H-bridge is a motor driver, and it looks like an H, and that's where the name H-bridge comes from. So in this lecture, we're going to talk about how to build an H-bridge from the ground up. We're going to do it out of transistors, but you could do it out of MOSFETs, and typically that's what you would want to do is build it out of MOSFETs. You wouldn't want to use transistors because the transistors can't conduct enough power, and there's a number of other reasons. So, but it's easier to build it with transistors because a lot of people have those on hand, and we can kind of just grab a few parts and build something, whereas working with FETs, a lot of times newer FETs are surface mount. You might have to solder them together and so forth. So anyway, we're just going to do this with transistors to get the kind of basic idea. So first thing let's do is let's go ahead and let's take a look. As a matter of fact, let's just Google for H-bridge here, and we'll say motor driver. All right, a lot of things come up here, and that's kind of what we're talking about. And these are obviously off-the-shelf drivers here. But let's go to images, and any of these are kind of what we're talking about. So let's grab something. let's grab something. This is a FET-based one. This is that's a transistor-based one. There's kind of an abstract. Oh, this one's a good one. I like this one. All right, so let's go here and we'll say open image in new tab. All right, so what do we have here? So say you have a DC motor, right? So a DC motor, and we're not talking about brushless motors. That's kind of a different thing. But a normal DC motor, you apply DC voltage to it. It rotates clockwise or counterclockwise. You reverse the polarity, then it rotates in the opposite direction. Standard DC motor. Now, a lot of times you want to be able to do that electronically. So you want to be able to make the motor go clockwise and then counterclockwise. So the problem is you've got this motor and you've got to basically apply plus and minus, and then to switch the direction you've got to apply minus and plus. So how do you do that? Well, how you do it is with an H-bridge. And all an H-bridge is this kind of configuration. So each one of these is basically a switch, just a simple switch, and it could be a transistor or a FET, or it could be a switch even. All right, you could do this with switches if you wanted to make a simple circuit, kind of for a classroom demo or something. All right, so let's take a look at it. So say in one case, we want current to flow down here, through here, and down here. All right, these are NPN transistors. So these transistors are going to turn on when we apply a high to them. All right, and they're going to turn off when we apply a low to them. All right. Now in this configuration, what the designer has done is he's tied this input, to this input. All right, so we can turn these both on at the same time or both off, and then this B input he's tied over here to this input and tie that together. And that's kind of the two different ways that we want to turn this thing on. All right, so let's say that we apply a low to a B here. All right, so that means that Q2, all right, and Q3 are off. All right, now let's go and apply a high voltage to node A here. All right, so that means that Q1 and come around here, Q4 are both going to be on. So these are NPN transistors. We apply a high voltage to the base, right? We forward bias the transistor starts conducting, it turns on, it acts like a switch when it saturates, and this more or less becomes a short, right? Okay, same thing over here, Q4, this turns on, more or less becomes a short. So let's follow the current. So if we're up here, and say this was our positive supply, V sub CC, maybe it's 12 volts or 9 volts, something like that, something to drive a motor with a lot of current. So current's going to flow down here. It can't get through Q3 because that's off, right? Q3 is off, right? So current's going to flow down here. Forget this diode for a minute. It's going to flow down through here. Now, can it get down through Q2? Nope, Q2 is off because remember B is turning Q2 off. So current's going to come down here. Now it can go through the motor, and it's going to want to come down here. Can't go through this diode, and then Q4 is on. So it's going to go through Q4, back down to ground. So basically we've got this conduction path. So the motor is going to turn on and it's going to rotate in one direction. Now, if we turn A off and we turn B on, apply a high voltage to that, we're going to have the opposite thing happen. So now we're going to turn Q2 on and we're going to turn Q3 on. So we've got a plus voltage up here. Q1 is turned off, no current's going to flow there, but Q3 is turned on. So we're going to get current flowing through Q3, and Q4 is turned off. Nothing's going to happen there, so the current's going to have to go through the DC motor, come through here, and then it's going to flow through Q2 to ground, and boom, now the motor's going to rotate in the other direction. Now, the other cool thing that we can do is we can just turn these full blast on, right? Or we could apply a lower voltage, and that would cause less current to conduct inside of these branches. But that's a little bit hard to control because depending on the transistors or the FETs or this or that, what we really want to do is we really want to use these transistors or FETs in an on-off kind of switch fashion. So that means the best thing to do if we want to control how fast this motor rotates is use a PWM signal. Remember, a pulse width modulated signal, and put a pulse train on it, on-off, with a duty cycle, and then let that control it. So just turn it on, turn it off, turn it on, turn it off, and the duty cycle of that on and off would then change the rotation rate of the motor in either direction. All right, so this is kind of what an H-bridge is, and it looks like an H-bridge because here's kind of the H, and here's the vertical bar, and here's the other vertical bar. All right, so that's kind of what we're dealing with. All right, so now what we're going to do is we are going to do a number of things. We're going to design one of these. We're going to kind of draw it on paper real quick on the blackboard. Then we're going to create a simulation of it. So we're going to actually build this circuit up step by step inside of Proteus, Lab Center Proteus. And then we're going to go on the bench where I've already built one, and we're going to experiment with it so you can see it working. All right. So this is kind of what we're roughly going to make, very similar to what we're going to make actually. And then we're going to talk about what all these components are and why we're adding them, and some other features also. This is just a random, I just found this right now, and coincidentally, it's similar to what we're going to actually build, but we're going to have some more features. Okay. All right. So let's go ahead and we will. And another thing also, go ahead and if you search Wikipedia for H-bridge, now there's obviously countless references and white papers and explanations of H-bridges. Surprisingly, normally Wikipedia just has pages and pages of stuff, right? I'm really surprised. Wikipedia's H-bridge entry is pretty weak. There's probably a different way to spell it, maybe H-bridge or this or that. Something bigger will come up. But anyway, this is the very abstract, simplified version of the H-bridge. And there's our motor, and then there's just 4 switches. The switches can be anything. The problem is when you're building one of these H-bridges, you have these 4 switches, you have 4 different things you can turn on and off. So you could accidentally cause problems. What if you were to, so here's a power source, right? What if you were to turn on S1 and S2 simultaneously, leaving S3 and S4 off? Well, this would create a short right across the power supply. So whatever the internal impedance of S1 and S2 would be, you would get that kind of current flow. So you'd get the voltage divided by the impedance would give you the current. It could be a lot. It could actually burn these switches out. Same thing over here. You could short these two. You could turn S3 and turn S4 on and leave S1 and S2 off. And then in this case, you get another short here. All right. So you have to be careful shorting these, right? So this is why you'll see motor controllers or H-bridge controllers that are kind of intelligent, and they may have a command where you say, hey, turn the motor right, turn the motor left, and with an added PWM signal or some other analog signal, then it controls these switches so that you can't possibly short them together, because if you have individual control of them, then obviously you can short them together. Moreover, there's some things like, for example, say you're turning the motor clockwise, right? Let's just say, for example, if we have S1 and S4 closed, then the motor will sit and rotate clockwise. Now I want to change it and make it go counterclockwise. If we just immediately turn on S3 and S2, right? We open up S1 and S4 and then immediately hit S3 and S2. The motor's already has momentum. It's rotating in one direction. Then we're going to start rotating in another direction. So we're going to get kind of this inductive braking, and then it's going to start rotating the other direction. But there's going to be a huge surge of current, right? So these kinds of transitions going from one direction to another direction, slowing down, speeding up, all that, some of these intelligent motor controllers are aware of how these motors react, and they can look at the back EMF of the motor, right? So they can better control the motor so that it's smoother making these transitions. So motor control, very complicated subject, but we're just going to take a first whack at it for something fun. One of the students in the course had mentioned he wanted to see a motor driver, and of course I said I was going to do a motor driver, so here we are. So anyway, that's talking about the switches, and then here's the state space. So there's 4 possible switches. They can be on or off, right? So 2 to the 4th is 16. So here's your 16 combinations, and you can see here's all these short circuits, these braking states, coasting states, and then motor moves right, moves left, and all that. So kind of some interesting things that you can do, right? All right. And then just talks about some drivers and so forth, and then the use of N and P semiconductors or N-channel only semiconductors, why you might want to do that, and so forth. I'm not going to talk about that. I'll let you guys read all that. All right. Anyway, so let's go to our famous drawing program here. All right, here we go. And since it's Halloween time, let's do this in orange. All right, so let's start off with we'll come down here, and we're going to go across here. All right, and then we're going to draw our first transistor. And let's see, how do I want to draw these? How do I want to draw these? I want to draw, yeah, so let's draw in this direction here. All right. Okay, I'm going to try really hard to draw these nice, which is never easy with this drawing program. All right. And remember, NPN, the transistor, the emitter points away. Okay. And then here's kind of the center area where we're going to put the motor. There's the two bases. All right. So now what I'm going to do is I'm going to just kind of put a node here and a node here. Just kind of keep ourselves centered here. All right, let's try and draw the transistor this way this time. Go like this. There's our collector. And remember, current always is flowing in the same direction, kind of downward. All right, but then we either shift it to the left to right or right to left through the motor, right? And then that's what gives us the different direction changes of the motor here. All right, let's get our collector, get our emitters. Okay, and we got our bases. All right, that's looking good. Then let's maybe go down like this, and we'll go like this, and then down here is going to be ground. Okay, then up here is going to be V sub CC. Let's make this one green at least, and let's just say, you know, for fun, this is 9 to 12 volts. A lot of times those are kind of your motor voltages, 6 to 12 volts, 9 to 12 volts, and this is a DC supply, obviously, and can supply a lot of current. All right, so we have our 4 different switches here. All right, so let's go ahead and label them. And I'm just going to label that Q1, Q2, Q3, Q4. All right. Now, let's get our motor in here. So let's go ahead and let's make our motor, let's make our motor red. So here's our motor. And motors kind of have this symbol like this sometimes. And now here's the interesting thing. We are just literally going to short it right to here. And we're going to short it right to here, just like that. All right, so those are wires, just shorted straight across. So there's our DC motor. All right, so we'll call that M1. All right, so now we've got 4 bases. We've got this thing potentially powered up. All right, now let's go ahead and let's add some, we'll do these in orange here. Let's do these, let's actually do these in blue. So let's go ahead and make sure this thing is always off. So when we're not doing anything to it, let's make sure it's off. So since these are NPN transistors, we're just going to put a resistor to ground on each one of the bases. And that just makes sure we're all safe. So when we're not doing anything, remember to turn an NPN transistor, we're going to apply a high voltage to the base, right? But when we're not doing anything, I don't want any funny business. So we're going to go like that, okay? Okay, so we have our 4 resistors. And now, what kind of transistors are these? Maybe let's say the transistors, for the transistors, maybe these are, 2N3904, or maybe 2N2222As, or there's a multitude. We basically just want NPN transistors, and then we might want transistors that can handle a half an amp or an amp. So you just kind of Google or DigiKey or Mouser or Octopart and search. But these little simple kind of low-cost ones will do, and these will be able to pass anywhere from 200 to 400 milliamperes. So you can, play around with them with a small DC motor. Okay, so just real simple little 5-10 cent transistors will get it done for these transistors. Okay, now so we've got these bases set up. All right, and then again, if you're watching this bonus video, that may mean that you've watched the whole class. You haven't watched the whole class, you're just skipping, and that's great. And that's what the idea of the bonus videos are. You can just kind of watch these out of order, and it doesn't really matter, and just kind of have fun. If you don't know how a transistor works, there's a lot of lectures on it. But in a nutshell, real quick here, let's pick a color. Pick this color maybe. So you got this transistor, and it's kind of like a switch in the way that we're going to use it. You can use it as an amplifier or a switch, and how this works is like this. If we apply a positive voltage right here, right, to an NPN transistor, then what we do is we start forward biasing or turning this transistor on, and then if there's a positive to negative voltage here, then what happens is we get a current flowing like this, and then a little bit of current flows here, and then adds up to this current. They both sum together, and we get a current like that. So basically, it's like a switch. So it's a current-controlled switch, all right, current-controlled switch. Okay. Now, let's see here. All right, so everything is off right now, and now we want to be able to turn everything on. Okay, so let's go ahead and let's add some more stuff here. So why don't we, so let's do this passively. So we're just going to use resistors. So let's add a resistor here, and a resistor here. And then what value should these things be? We'll talk about that. And that's why we simulate and we build things, so we can kind of tune and figure out what we want to do here. All right. So I'm going to tell you right now, let's go ahead and make these pull downs. We could make them anywhere from 10K to 100K. We want to just make sure the transistors are not on, so they're kind of being held off. So we'll just call these 100K, 100K ohm. All right. And again, you got to play with these values. You got to see how the whole system works together and what kind of currents are being generated and so forth. All right, so those are 100K to ground, and that's going to kind of keep those things off. Now, we really want to turn these transistors on really hard, right? These are like switches. We want to use these transistors as switches. So we're going to turn these things on really hard. So for these resistors here, I want to go ahead and let's make these like 100 ohm to 220 ohms, so real small. All right, and so let's go. We'll call them 220s for now. 220 ohm, 220 ohm. All right, well, we're going to play with this, right? 220 ohm and 220 ohm. For example, again, if you don't know transistors, you'll kind of get lost a little bit here, but so if this is 220 ohm, and then let's go ahead and let's put some switches on the other end of these things. So we're going to put a switch here, we're going to put a switch here, we're going to put a switch here, a switch here that looks like this. So why don't we put a little momentary switch like that, and then the other end of this is going to go up to this V sub CC. So I'm just going to again just put V sub CC, the same voltage it's going to be. Whatever this is going to be the same. All right. So let's put another switch here, momentary switch to V sub CC, and momentary switch here. And this is kind of the symbol for a little push button momentary switch. All right, and right here. All right. So I got this kind of architecture. So that looks good. So you have these 4 switches. Let's name these a little bit. All right, let's name these switches. So this Q1, so we'll just call this S1, we'll call this S3, we'll call this S4, and we'll call this S2. The resistors, I don't care so much about naming them. All right, so as we close these, so if we were to close S1 and S4, we would turn the motor on and it would go in one direction. All right, now let's go back and talk about this a little bit. So this node right here, is equal to 0 volts. So this is equal to 0 volts right here. All right, now when this transistor is on, and it's on really, really hard, right? If you guys recall, for those that have done this, this voltage drop from the base to the emitter is going to be approximately 0.6 to 0.7 volts. 0.6 to 0.7 volts. All right, so that's 0.7 volts. So if this is at V sub CC, then the total voltage drop over this 220 ohm is going to be V sub CC minus 0.7, right? That would be the voltage drop. So if we wanted to find the current here, so if we want to find the current through here, let's use green. So we want to find the current through here. That's going to kind of come through here. And this current right here is called I sub B. I sub B going into the base, all right? So I sub B, roughly, is equal to what? V sub CC minus this 0.7 volts over this 220 ohms, right? And if we plug in real numbers, let's just say that we're using 12 volts here. So we plug in 12 volts minus 0.7 volts over 220 ohms, right, is going to give us 11.3 volts, 11.3 volts over 220 ohms. All right, let's get our calculator out and pray that we have enough photons to do this. All right, so we've got about 51 milliamperes. 51 milliamperes. So that's a lot of current, right? So we're really driving this thing really hard. We don't need that much current to turn it on, but we're just going to leave it at that. We can always make these resistors a little bit bigger. Okay, so the point is that when we close these switches, so let's do some closures. So if we say S1 plus S4, and by plus that means these are all the switches that are closed, right? So in this state, S1 plus S4, what's going to happen? Well, in that case, we're going to get a current, and again, I'm going to use green here. So we're going to close S1 and we're going to close S4, all right? So when we do that, what's going to happen is we're going to get this V sub CC here, right, giving us that base current. That's going to turn on that transistor. We're going to get this V sub CC here. We're going to turn on this transistor, right? And when we turn these transistors on, we're going to get a big current over here in the collector side, right? So we're going to get current that's going to flow down here, right? And it's going to go down here. And the little base current's going to add up with it, but we don't care about that right now. Then it's going to go here. It's going to go this direction. It's going to go right through the motor, turning the motor on. It's going to go down here. Again, it's going to go through here. It's going to sum up with this little base current here. And then it's going to go to ground. So that's what's going to happen when we turn on S1 and S4. All right, cool. So now let's back up and let's try another one. So now what happens if we do the other state, which is, say, let's turn on S3 and S2. So state S3 plus S2. What goes on in that situation, right? So let's go ahead and we'll pick a different color here. So S2, where's S2? S3 and S2, S2 and S3, these two right here. All right, so if we close this, we're basically going to get a current here. We're going to get a base current, right? That base current's going to turn on this transistor, and then it's going to end up going down here. Small base current, like 50 milliamperes. All right, then we're going to turn this transistor on also. We've already got that little line there, but just bear with me. And we're going to turn that on. So both transistors are going to be turned on. And both of those base currents are going to shoot out of those emitters, right? But we're going to turn these transistors on. So each one of these transistors is going to basically act like a closed switch. So now current's going to come from the source. It's going to come down this way. It's going to go through here. This time it's going to flow in this direction. Of course, the little base current here adds up into it. It's going to go through our motor here, down here. All right, keep going, keep going, keep going. We're going to pick up that base current right there, and we're going to go down to ground. And so that's the other state right there. So those are our two different motor states. Turning on 100% full is much power as this circuit can flow, as much current as the circuit can flow. The motors are going to turn on and then rotate. Now, how can we control this? Well, we could control how much we turn these bases on. We could control them with analog, but the problem is these are open loop circuits, right? And we've talked about this before. Each one of these transistors, if we just use it in this kind of switch configuration right here, depending on what the gain is of the transistor, could be 100, 200, 300, 400, you're going to get kind of a different amount of current flow. So we need feedback. We need to make an actual amplifier and have feedback so we have some control over it, so that whatever the gain is, the transistor gain is factored out, so we get a gain set by components, right? That's what we really want, so we could control the gain, right? But at this simple configuration, we can't do that. So what else can we do? Well, what we can do is, instead of having little mechanical switches here for our example, what we can do is we can use PWM, right? And if you don't know what this is, pulse width modulation. And the whole idea of this is, right, and of course in the course, we talk about this, and we have a waveform here. And let's say that we've got a signal, let's say a kilohertz, 1 kilohertz, all right? So we got, say, a 1 kilohertz signal, all right? So that means the period of each one of the waveforms of each one of the individual cycles is going to be 1 millisecond, 1 millisecond, all right? So that means from here, so say here's one of these waveforms, goes from here down to here, that would be one complete cycle right here. This is the high part and this is the low part. From here to here is 1 millisecond, okay, 1 millisecond, all right? That's one cycle. Then we have another cycle, goes up, goes down, and so forth. Now, this right here, if we look at this, here is when the waveform is high, and here is when the waveform is low. You can see they're equal, right? So it's 50-50 right now. The ratio of this, so as we change the ratio of the high to the low, so coming back here, we can start to make a waveform that looks like this. It can be long, 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 and then it can be off just a little bit, and then long, 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 and then off just a little bit, and on, and so forth, right? Or we could flip it around, and we could just turn it on just a little bit, and then it's off, 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 turn it on a little bit, and then it's off, 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 off. And the total cycle time is always the same. It's that 1 millisecond, but how long it's on or off, right? That's the modulation. So the pulse width modulation, we're modulating the width, how long this thing is on or off. So in essence, if we were to take these signals and then apply them to these switches, right? All right, and of course we'd have to apply them to the correct switches. So this switch and this switch, or this switch and this switch. We can turn these motors on just a little bit of time. All right, and so they're going to turn on just a little bit of time, and what that is going to result in is the energy transfer. Instead of being full blast on, it's going to be a percentage of full power, so the motor is going to rotate at a lower angular velocity. And that's kind of how you can control the motor's rotation rate digitally with a pulse width modulation. All right, so that is an H-bridge, and then of course we could just switch these, right? We could switch these guys, you know, for FETs, okay? And that's what you would do. So these are NPN transistors, all right? And then NPNs are recommended for, there's a number of reasons, but typically if you're going to do it with transistors, you'll use NPNs. But if you do it with FETs, then a lot of times what you'll see is on the high side here, you'll see a P-type FET, a P-type FET, then you'll see an N-type FET and an N-type FET. Because of the charge carriers, you want to put the P-types on the high side, the N-types on the low side, but then they turn on and off with different voltages, right? So that you kind of have to play around with these inputs a little bit more. But the reason why you like FETs is the on resistance is very low. You're talking about milliohms, right? So these things are nearly dead shorts. So you can create these H-bridges that can flow enormous amounts of current for very cheap, right? So you might be able to make a 10, 20, 50 amp H-bridge with very cheap parts as opposed to doing with transistors, which would be much more expensive. Okay, all right, so that's kind of what we're building, all right? And one other thing I want to talk about here, I want to add. We are driving motors here, all right? And one thing that we learned when we were doing our course lectures is when we're driving motors is that when this motor is, you know, we're driving the motor, and then when we turn the motor off, this is an inductor inside of here. And this inductor is going to want to maintain this current. And so what happens is the inductor creates a voltage, right? And in the opposite direction, it can damage the transistors, all right? So what we do is we're going to put these catch diodes here, and we're going to put them in this configuration right here. So just like this, over each one, we're going to put a diode, and this is for the, you know, the inductive kick. We've used a few different names to kind of identify these, but they're going to go in this configuration right here. Sorry if it's a little bit hard to see through things, but it's hard for me to erase this. So they're going to go, so normal current is going to flow down in this direction right here, all right? And when that happens, and let's use a different color for that. Let's use so many colors, this one. All right, so let's say that we got the motor and the motor is running like this, right? And let's do that a little bit better. The motor's running like this, like this, like this, like this, like this, and down like that, right? When we turn this motor off, what's going to happen is we're going to get a large positive voltage here, and it's going to want to drive current this direction, and instead of the current going back up here through this transistor, it's going to go through this diode. And then you can kind of follow that same pattern, and it'll work always the same. So the diodes always go in the same direction, the opposite of the normal current flow of the transistors or of the FETs. And then that will protect these semiconductor devices, and they won't get blown up, which can actually happen quite easily. All right, and the other thing is what kind of diodes. So when you guys do this, you can use a 1N4001, a simple little diode, or you can use a Schottky diode, which has a much lower on voltage. But 1N4001, 2, 3, 4, 5, 6, any of those will be fine. Just run of the mill when you're just building a fun circuit. If you're going to do real motor control, please do not build your own H-bridges. Companies spend years literally engineering these things and optimizing these things and doing a very deep analysis of them, testing them out with different motors and all that for all those different conditions I talked about, and thermal this, and being able to control the motor, break the motor, and so many different things, but this is just for fun so you can kind of see the process. Okay, now let's go to our simulation tool. Where is it? Where'd it go? Here it is here. Okay, now. Okay, so the first thing, you know what, let's move this and over right here. Okay, and we are always out of time. I do these big lectures. I do them unscripted, so they're honest, and we kind of talk about things as we go. And we just don't have a lot of time, especially with the bonus lecture, because I want it to be one lecture and not 2 or 3 or 4. So we can only do so much stuff. Now, if you haven't seen Proteus, this is Lab Center Proteus. If you go to labcenter.com, this is a simulation PCB layout, schematic design. This is an awesome tool. Like Circuit Maker, it's very cool. Like Circuit Studio, it's very cool. Except what this has is simulation, where a Circuit Maker, the PCB tool we're going to use in the course for free, does not have simulation. So this is not free, but you can use the simulator for free, but you just can't save. All right. So if again you're coming to this for the first time, you're like, what's this? This is Lab Center Proteus. Go to labcenter.com, download it. It's totally free. Install it, and then you can build these things. You can just kind of copy this, and but you can load simulations. So this is a simulation H-bridge 01. It'll be inside of the lecture materials for this lecture. So just look in the download section and just download the zip file. Boom, it'll be in there. All right. Okay. What are we doing? All right, so let's take a look at this. So this is basically what I just designed right here, right? This is that. Okay, let's take a look. All right, so we've got our motor here, which is just a standard motor device from Proteus. And we've got our transistors. And this is just some random transistor, ZTX450. That I looked up as one of the parts here that this tool had. Remember, if we want to run the simulator, we need models of things, and if we don't have a model, then a lot of times we'll just use a transistor or a FET or a device that's similar to it, and then we build our real devices on solderless breadboard or printed circuit boards. Then we kind of have to extrapolate or imagine with the real parts. It's going to work a little bit different, but we can kind of use models that are similar, right? Because we can't build all these models in here. Now with some tools you can give models for the devices, full complex models, but this company gives you these models and there's not much you can do. You can't create your own models, but a lot of times they're parameterized, so you can actually mess with them a little bit. For example, if we go to the motor, it says how many revolutions. I believe this is revolutions per minute. And then the load resistance. What's the motor's DC resistance? 5 ohms. But there's not a whole lot of other properties here. Nominal voltage, 12 volts. So there's not much else here you can mess with, right? If we go to the transistors, all right, again, not much else we can mess with, right? So again, depending on what, and here's these Schottky diodes. Again, the model is kind of intrinsic, so we can't mess with it. But sometimes you can mess with the models more if they expose some of the parameters. All right, so let's look at the circuit. So what do we have here? We have a voltage source, a DC source, this motor 12. So motor 12, and it's 12 volts. It's DC. Okay, cool. Down here we've got ground. All right, so we've got each one of our legs of our H-bridge. So we've got, again, these are NPN transistors. The emitter is pointing out, it's NPN, 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 NPN. Then we've got these Schottky diodes. Instead of using the 1N4001, we're just using Schottkys. In this case, these are pretty high current Schottkys, I believe, if we were to look them up, if we were to take that number, right? And if we were to go over here to our favorite little tool, DigiKey, and we were to look these up, well, let's see, what's the story with these? 38 cents, they can handle 30 volts and an amp of rectified current. Good enough, good enough. And their forward voltage is 560 millivolts at 1 amp. So that's pretty good. It's better than the 1N4001, which is going to be about 0.7, maybe even 0.8 volts. It'll drop. And remember, ideally, we want it to drop 0. We want it to be perfect. So we just want it to be a diode, but not drop any voltage, right? All right. Anyway, moving back. So here's our configuration, and then we've got our switches, 1, 2, 3, 4. These are interactive switches, so we can kind of turn them on and turn them off. All right, and these are not momentary because there's no way to press two things at once. So we turn them on and turn them off, so they're latching. All right, and let's see. Okay, now we also see there's some capacitors here. I want to talk about these. Whenever you're doing motor control, a lot of times the motors generate a lot of noise, electrical noise. So what you'll do is on the plus side and the minus side, and this motor here, there's no plus or minus, right? It goes either way, so there's no correct way to connect it. We can just arbitrarily say one side is plus, one is minus. In any case, some of the design tactics that you'll see designers do when they're putting motors in things is they'll put a small capacitor on the plus and minus to ground, and that gets rid of one kind of noise. And that capacitor typically is like 0.01 to a 0.1 microfarad in that kind of range. And then you'll put one right across the capacitor, the motor leads. You'll put a capacitor across that, and that might be a little bit smaller, 0.01 to 0.001 microfarads. All right. Then another thing you might even see is putting inductors, extra inductors to get rid of high frequency noise inside of the power lines as well. All right, but we don't have this. So we just have a few capacitors here for noise. All right, then we have our resistors here looking back at our design. You know, we've got our base resistors, right, 220 ohm, and then we've got our base pull-down resistors to keep the thing off, to keep each transistor off. And again, we used 100K, 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 and then these are 220, 220, 220, 220 for the base resistors that are going to be the injection path for the base. All right. And then you see I've got a bunch of instrumentation here for you, so you can kind of see what's going on, right? And then what's interesting is, will this match the circuit that we build on the bench, which we'll do in a little while. Okay, then up here, you see I've got a big capacitor, this big bulk capacitor. When we turn these motors on, right, there's going to be a lot of inrush current, a lot of currents, and we don't want to pull that from the power supply. So even though this is a simulation, we still want to have good design, and so you want to put big capacitance on these motors, 220, 470, 1,000 microfarads or more, all right? And that way, when you need that current, it'll pull from this capacitor and not from the power supply and dip down your power supply and potentially cause ripples and issues with your other power supplies that are pulling maybe from this 12 volt to get your digital supplies, right? Okay, we're always concerned about that. Okay, so I think, let me see if we can get this on the screen. So what I'm going to do is I'm going to kind of put it just like that. Proteus is this lab center. Lab Center Proteus is a United Kingdom company, and you know, here was the interesting thing. When they made this tool, they were kind of pushing the limits of Windows when they made this tool initially, and they kind of came up with their own things. And then Windows got really, really, really good. And now this tool, if you look at it, looks very dated. It looks like a 90s tool, right? And a lot of things are very 90s-ish. They're not like normal Windows or what you would expect on a Macintosh either. So, you know, you scroll the scrub wheel to kind of make things, you can't do this smoothly. There's just lots of issues that make navigation a little bit different than what you would expect just with any Windows app. So it's kind of like hard to get things centered and all that. Anyway, here we go. All right, so I'm going to run the simulation. And I've got 9 messages. I got 2 messages. Okay, we look good. So here's the two messages. Everything's working, simulation log, cool. And it's animating, and CPU load is 0%, which is completely incorrect, I'm sure. All right, so it's running, and we can see all these voltages and everything is going here. Now, the motor is just sitting there, all right? So now if we turn this switch on, right, nothing happens, right? If we turn this switch on, nothing happens. This switch, nothing happens. We got to turn two of these things on, right? All right, so let's go ahead and let's turn this transistor on and this transistor, and we'll get a current flowing through this guy like this. Here we go. So I turn this one on. Now look what's going on here. Right now in the collector circuit, we have a very little current because we haven't turned the emitter here has no ground right now. It's still floating because this is not turned on. All right, but now we're going to go ahead and turn this one on. Boom. And now in the video, you can't really see which way this is turning. As a matter of fact, let's go ahead. Let's modify that. Let's see if we can make that a little bit more. Instead of 10,000, let's make it just 5. Oops, 5. Maybe we'll be able to see it a little bit better. All right, and I'm going to save that. So here we go. We're going to run it. Okay, and now this is on and this is on. So now we can actually see it turning the correct way, and it's not doing any kind of crazy superimposing on our eyes. So it's turning counterclockwise right now, or excuse me, clockwise. Yes, it's late. I'm tired. I always do these really late, so it's real quiet when I'm recording. All right. So it's turning clockwise right now. Now let's take a look at some of these currents. So coming through this node right here, we have 483 microamperes, which is getting dragged through here. And then over here we have 546. So whoa, wait, what's going on? How can we be pulling only 483, but then we've got 546? Well, remember, we've got 43 right here. Then we have some base current. How much do we have here? 22 milliamperes. We're pushing through this base. That's going to add, right? So whatever this current is here, we're going to add to it. Then we've got that current coming through here, coming through here, coming through here, coming through here. Then here we go. Then what are we going to add to it again? We're going to add this current here, this 41 milliamperes, which is driving this base here. And so that 41 is going to add, when you add all those together, you get 546 milliamperes. Boom, going down to ground. All right, so this is working exactly as we would expect. Let's turn this off. All right, and then on these little switches, you got to hit them just right. And let's go in the other direction. Boom, and boom. And now we're going in the other direction. We're going counterclockwise. We're going backwards in time. Cool, so that's working. And again, we have almost a very symmetrical configuration. We have 483 on this leg now, and over here we have 546, the opposite way. So current is flowing down, down, down through Q12. And these numbers, because I did a lot of copy and pasting, these numbers are kind of crazy. Q12, then it comes through here, then it comes through M1, and then it goes through Q14, and then back down to ground. Okay, now let's have some fun because we can't blow this up. Let's short this thing out. So I'm going to short these two switches. So right now I'm getting no current through here, right? I'm only getting this base current here, just this right here, right? We're just getting this, but we're not getting a lot of collector current. So watch this, boom. Now we're getting currents coming from the source, 574 milliamperes are coming through here. Then we're getting our 70 milliamperes here, ouch, and that's adding up. And then we're getting our base current here, which it's splitting off in both directions here, and then they all sum up, and we get 644 milliamperes. The good thing about transistors is the impedance of the transistor itself, right? It's not going to flow, much more current than it can handle. It's going to kind of get stuck and kind of not be able to blow itself out. Now, if you keep running it, yeah, it's going to pop, it's going to overheat. But the nice thing is it's not going to instantaneously just explode. All right, so the simulation, we can't hurt that. Now, what happens if we turn them both on? Let's check. We turn this on now, and then we turn this on. So what's interesting here is we're shorting this side out, but what's happening is we're kind of creating this asymmetrical voltage situation so that we can get some rotation, some current flowing through the motor because it's an unbalanced circuit. All right, now let's rebalance it, and then let's unbalance it over here. All right, and unbalance it over here, see? So you can do that. That would be very bad. You don't want to do that, right? So you want to keep all these back open. Okay. And that one. There we go. So there is our H-bridge. And again, what you want to do now is these four things, since you want to make sure you don't ever turn this motor on and short things out, you would tie like switch 9 and switch 11 to one signal, then switch 10 and switch 8 to one signal, and then you would only turn one on or the other one on. And then even better yet, you would make sure that they're inversions of each other, so you can only turn, when you turn one on, the other one turns off, or when you turn one off, the other one turns on. That way you never ever hurt your motor. All right. Or your drivers, your transistors, or your FETs. Okay, so we are running out of time. Let's get over to the bench and let's go ahead and play with that. So I'll see you over there. Okay, so what do we have here is we've got a model of our H-bridge, almost identical to what we built. We've got our four switches, we've got our four transistors, we've got our motor plugged in right here, which is suspended on this device here. It's a little, so the focus is, we're focusing here, so we can't really see this. But anyway, the motor's over there. We'll get to that in a minute. All right, then we've got a little bit of instrumentation. Right here, I'm measuring current, and we're going to see that on a meter, which we'll bring in. All right, so we can see that once we back away from this. Everything is identical. We've got our capacitors there that we saw. We've got our diodes. We've got our kickback diodes on there. And now another interesting thing that we have is over here, down here. For one of the switches, I have a PWM signal from my signal generator that I can turn on and enable. So that signal's at 50 kilohertz, and unfortunately, the signal only goes up to 10 volts. All right, whereas we're powering this with a 12 volt supply. So those bases, so when we turn this base on, we can't turn it on super hard as we can with the switches, but hard enough. But we're not going to use that at first. All right. So what we're going to do is I'm going to back away here a little bit so we can get most of the stuff in here so we can kind of see. All right. So let's put this in here. All right. And this is, again, this is always very hard to film all this stuff and get everything on here so you can kind of see everything. Obviously, we don't have a film crew. All right. And I'm going to, how about I put this right here maybe? Okay. So here's the deal. Let's see if everything's on. So the power supply is on. The signal generator is off. So the signal that we're injecting into this one switch is off right now. So the switch will turn it on. All right. And then keep an eye on this current right here. So this is the amount of current that's going to be flowing. So if we want to turn the motor in one direction, we basically need to turn on two of these switches. So let's try these two right here. Let me get my hand out of the way. All right. So I'll press one and then press the other. And you can see we're doing about 300, 250, let it stabilize, about 247. Now, here's the interesting thing. All right, so first, what direction is that turning? All right, all right, so that's turning, so that's turning counterclockwise. Now watch that current. So see how the current is high? Because the motor, we're spinning the motor up and then it drops down. So there's two kinds of things happening here. Right when I turn this motor on, boom, boom, look at that, 0.4 amps, roughly 0.4. Then it drops down. So that's the initial start current. That's the start current, right? Then there's what's called stall current. And let me do this with my fingers here. I'm going to turn these both on. And I'm going to stop this motor. All right. And look at that, 0.4, and I'll let it go. So we got to be able to handle that stall current, okay, without blowing things up. All right. So then it's going that direction. All right. So now I'm going to, the current's going to be roughly the same, so I'm going to kind of cover this. You'll see my fingers cover this a little bit here. It's kind of hard to get in here. Let me see. All right, so I'm going to do these two switches here and do it the other way. Here we go. All right, I'll kind of put my fingers there, and then you can see it's going clockwise. Now look at the current. The current's the same. It starts off high, and then it drops back down to the same. Now, let's try a different experiment. So now if I let go of these, let's look how long it takes to coast down. Ready? 1, 2, 3, 4, 5. The switches are actually burning my fingers. These switches are not rated for this current. They're actually burning my fingers. Let's do that again. Rev it all the way up. And it's burning my fingers. 1, 2, 3, 4, 5. Ouch. Ah. Okay, so that switch is getting really hot. Here we go. We're going to do it again, but this time I'm going to stop it with the other two switches. So I'm going to reverse the direction. So forget the current. You're not going to watch that. Okay, so here we go. We're going to go in one direction. When we hear the motor, full blast, and then, do you see what I did? I used the other direction as a brake and then switched it really fast. So, boom. All right, so that's braking. Okay. Okay, so there is the H-bridge. The H-bridge works, and then we can change directions very quickly. Instead of letting it coast down, we can just flip directions, and of course that's going to cause more current draw. All right. Now, over here, we've got my, let me see if I can point my finger. Over here someplace, there's a signal generator, and that signal generator right now is at a 20% duty cycle. All right, so what I'm going to do is I'm going to turn the signal generator on. It's going to basically pulse this for us with a 20% duty cycle. And we're going to hold this one and just keep this one on. Okay, so what I'm going to do is I'm going to put my finger around here and I'm going to turn on the signal generator. Signal generator is on. Everyone's happy. I'm going to turn this one on and then notice it starts turning. But notice what the current is. It's less. See? Because we're PWMing it. All right. All right. Isn't that cool? Now, I'm going to turn it on, and now I'm going to adjust the duty cycle manually over here. So first, let's turn it up, and see didn't pull that 0.4 amps, and it's not hanging at almost 300 milliamps. It's only hanging at 200 milliamps, right? Okay, now here we go. It's at 20% duty cycle. Here comes 30. Look at that. Here comes 40, 50, 60, 70, 80. And with this tool, I can only go 20% to 80%. You can't go less than 20 and greater than 80. But look at it. Isn't that cool? And then now watch, slow it down. Isn't that cool? All right. That is PWMing that one leg, right? And of course, you could PWM both. You could overlap the PWMs. You do whatever you want. You can do all kinds of cool things. Okay. So that is the H-bridge. All right, so we've made a discrete H-bridge out of transistors, very cheap. It does work. This is not a tiny motor. Let me show this to you. This is a pretty big motor. I think this particular motor, you could probably put an amp through it. Big motor. We're just using little simple transistors. Stuff is definitely getting hot, but this is a good starting design to kind of get things going. And then you can kind of work from here. And then you could change these to FETs. You can control things with only one control signal. You could get rid of these switches and then connect these directly to a microcontroller so you could turn it on and so forth. And that's exactly what a H-bridge chip does, right? So let me see here. So let's move these out of the way just a little bit here. Move this out of the way for you. And then I've got a couple manufacturers here. So here are some H-bridges right here and that I bought just to check them out. One's really, really tiny and one's a little bit larger. So let's go ahead and let's take a look at these real quick on the computer. There's thousands of H-bridges and then motor controllers and so forth. So there's no limit to what you can do as far as cost and performance. But these are just a couple cheap ones and simpler ones to solder together. So let's take a quick look at the computer and take a look at these. All right, let's go back to the computer. Okay, so we're back here on the computer and we're taking a look at the first little motor driver. So this is this SIP 2100, and if we click on this, we look and we see at 1,000 it's about $1. And what I like about this is it'll go up to an amp, and it's pretty simple. And let's go ahead and let's grab the data sheet. And you can see it right here. So it's a very simple 8-pin package, and I believe it only is an SOIC package. I don't think there's a through-hole version of it. Yeah, it's only an SOIC 8. And very simple though. It's got power here, so there's your power, right? And then it's got ground, and then it's just got a few control signals. So here's NA, NB, out A, out B to your motor. So right here, here's out A and out B. This is a horrible PDF. This goes to your motor right here, all right? And then these S signals here, SA and SB, I believe these are for sensing. These might be sensing signals. And then, yeah, and then these ends, NA and NB, this is what controls the motor. So you only have 4 different combinations because they're tied together, so you can't really get in too much trouble. So 1, 0 turns the motor in one direction, on and off. 0, 1 turns the motor in the other direction. 0, 0 turns the motor completely off, both outputs, and then 1, 1 is interesting. That puts them into high Z. All right, so instead of grounding both outputs, it puts it into high Z. All right, and then these S signals, this SA and SV, are for feedback. So if we look through here, and this is a brand new product. Let me see, here it is right here. Driver output return A, driver output return B, so you can kind of see what's going on with those signals. So this is a nice little part, very simple and very easy to use. So I like this right here, and this will drive a pretty big motor. If you want to do something kind of, this isn't, you're not doing a discrete design now, right? But you're doing one that you're using an IC that doesn't have a whole lot of control logic, but it does have some control logic, right? It doesn't have a lot of super advanced features, but it does have some. Okay, so that's that one. Now let's take a look at the other one. Let's search for that. All right, and the other one is, all right, so the other one is this MP6513GJ-Z. And what I like about this is it's teeny tiny. It's one of these SOT 2.3 kind of packages, right? So this is really cool. And this one's a little less current. This one's 800 milliamperes, but it works at a wider voltage range, which is kind of cool. And let's take a look at that. Very cheap, again, under $1. So look how simple this one is. So you just put your motor there, your DC motor, or you could put a stepper motor too. All right, and then we've got power here, we've got ground here, and this one's only got 2 signals, so you don't have those feedback signals this time. You got in1 and in2, and then there should be a little truth table again. But this is a great way to control a motor and be safe with a nice FET driver, right? And let's see if there's a little truth table, and let's see, and then look at that, see those are pulled down, so there's no funny business on those inputs, right? And these are using FETs again, right? Like what you should use. And there's our truth table. There we go, right there. So there's a truth table kind of showing what's going on. If they're both low, it's in coast mode. Low, high, reverse. High, low, it's in forward. And then high, high, brake. So high, high, no matter which way it's turning, it will want to stop it, all right? Which is very cool. All right, so this has braking also, which is nice. So again, that's this part right here. And you know what I'll do? Is in the materials for this lecture. I'll throw the data sheets for both of these chips inside of that zip file, so you have the data sheets. The data sheets are public domain, you can get them, but just so you don't have to remember this number. But like I said, there's thousands of motor drivers and H-bridges, so kind of look around, see what you want, see what would help you out with whatever it is that you're doing. All right, so that is it. So that's kind of where we started from. All right, we kind of designed through this. We talked about it, how it works and so forth. We went and built our simulation. The simulation file will be inside of the lecture materials in the zip simulation, HBridge 01, 02, whatever I end up saving it as. So as a matter of fact, save right now, and I think, yeah, we'll just leave it like that. So that'll be inside of there. We did the bench work so you could see it actually work, and it does actually work. And that is motor control. So very cool. Now, these are brushed DC motors, and you're going to have to look up what that means, but there's brushes inside of it, and there's commutation that goes on, and then there's a permanent magnet, and there's a electromagnet, and it's a super ingenious. I mean, electric motors are fascinating. There's some really good YouTube videos. I didn't take time to find them for you, but there's, just a little segue here. Depending how old you are, if you're my age, about half a century old, back in the 50s, 40s, 50s, 60s, mostly I think the 40s or 50s, there were these educational videos. The world used to be a different place, especially in the United States. In the United States, like if you bought a radio, you got the schematics to the radio. It explained how it worked. People wanted to know how things work. Now they just could care less, right? Which is really sad. But there were these videos that they made which would show how things worked, and there were a whole series of them, and I think it maybe was for military so that people could understand, but like people wanted to know how a car worked. How does a differential, the rear end work, or brakes work, or this? And they had some motor videos that have amazing animation made in the 50s. And if you YouTube around and say, the operation of a DC motor. How does a DC motor work or whatever? You might even stumble upon it, and they're actually pretty amazing. I mean, these things are over half a century old, and it's showing electromagnetic induction, it's showing motors, it's just very amazing to me that we had this technology, 70 years ago, more, right? 100 years. TV was invented in 1898, roughly. First cathode ray tubes, right? Crazy, huh? Over 100 years ago. But anyway, we had this stuff, and so those videos show this, and they show it in a really clear way. Where some of the more modern stuff is kind of it's hard to see what's going on. But anyway, you can look and see how these motors work for these brushed motors, and then there's these brushless motors where we get rid of this mechanical aspect and we control it completely electronically. You need a different kind of control system for that, all right? Because the motors themselves need to be sensed, usually with a magnetic sensor, a Hall sensor, has to sense what's going on magnetically in the motor and then use that information to control the motor. But with standard, simple, brushed DC motors, these are the kind of controllers that you need. All right, so that's it for this lecture. I hope you liked it, and that's it. So good bonus lecture, and we'll see what we do next time. All right, so I'll see you in the next one. Bye. Destroying this platform, this ecosystem, all your customers and this and that. This is ridiculous because someone bought an Arduino and now it's not going to work with the other Arduino. So they even had two websites like Arduino. And this is where I can't remember exactly, but you can read about it. There was Arduino.org and Arduino.com, I believe. That's what they split into. And so customers would go to Arduino.com and think that they're Arduino.org, or they'd go to Arduino.org, but they thought they were at Arduino.com. And they even had two versions of the IDE, the Integrated Development Environment, which I'll talk about what that is also. That's like the thing that we talked about where you program. So these guys are fighting. The judge finally said, you know what, stop this. This is ridiculous. I'm forcing you to remerge the company. So this happened about a year ago, I think, or so, maybe a year and a half ago. They remerged the company, and now there's Arduino.cc, right? Another one of these domain names. Anyway, so now when you go there, it's one company again, and everything's hunky-dory. But it could be confusing to you if you look back and things from the past, you'll get confused. So check it out. So if I go to Arduino, let's go to Arduino.org. It says Arduino, but check this out. You're now going to be redirected to Arduino.cc. All right. And we'll give it 5, 4, 3, 2, 1. That's the longest redirect. Okay, there it goes. Now check it out. If I go to Arduino.com, if we go to Arduino.com, it's a resolving host. So, well, that's interesting right now. Okay, so I'm going to tell you right now, I can't believe someone doesn't own that. That's interesting. Huh. Okay, so that's a good little website to grab that domain, and I bet you somebody already has that. But anyway, that was the other one, I think. And then no matter what, now you need to go to Arduino.cc. Okay. So, but I just wanted everyone to know this because, I like the history of things, and it's kind of interesting to see what kind of goes on. And this caused a big upheaval because everyone's like, is Arduino going to be around? And should we keep messing with the software and building things with it, or should we just like throw it away, right? Okay. Now check it out. It gets even more crazy. So remember I told you there's lots of different Arduino hardware now that's kind of Arduino compatible. All right, so let's see. If we go to, I believe, I think if we go to Buy Arduino, yeah. All right, so there's all these different, t-shirts really shouldn't be in here. But if we go to, I think if we go to Arduino, yeah, boards and modules. All right, shields are things that plug into Arduinos. All right, so we'll go to boards and modules. And then you can look through here and you can see all the different Arduinos that there are. And like I said, there's all these different variants now and versions, right? Because it started off with this one. So this Uno right here that when I hover, it does this, which I don't like. So let's actually, there we go. All right, so this is the very first one. Now, this version here isn't the first one, right? This is Rev 3. So over the years, this has been updated and updated. It still uses the same processor, though, this ATmega 328P. is a very, very, very simple 8-bit processor, and I believe it has 16K of flash. It's 8-bit, 16K of flash, and I believe 2K of RAM or 1K of RAM. Let's see. It has 32K, 32K of flash, and then 2K of SRAM, and then 1K of EEPROM. So this is very, very limited, right? But this is with this microcontroller, you can do a lot with this, and clock speed is 16 megahertz. I'll tell you that you can definitely clock these things up to almost 30 megahertz if you actually want to. All right. And then if you go here and click the data sheet, right? Let's just real quick, let's go click this data sheet. You guys know how to read data sheets if you went through the class already. If not, this might, all right. And so what's interesting right now is, remember I said Microchip bought Atmel? Microchip bought Atmel. And because of that, Microchip is a massive corporation. Atmel was a massive corporation, billion-dollar corporation. A lot of the website is still broken. So if we just type in, we're just going to type in AT Mega 328P, and then we'll just put datasheet. All right. All right, we'll go here and see, this is on SparkFun, so this is on their local server, right? All right, so anyway, you read through here and you can see there's variants of this thing, and then here's the original one was the 168 that they use on the Arduino, and then now they're using the 328P. And then you can kind of go through here and look at it. So 20 MIPS of processing at 20 megahertz. It has a multiply, which is rare on little 8-bit microcontrollers. To have a multiplier, having a divider is even more rare. And then it talks about all the different peripherals, right? It's got 8-bit counters, 16-bit counters, it's got a real-time counter, PWM channels, pulse width modulation, ADC, analog digital converter, temperature measurement, it's got UARTs, it's got a SPI interface, it's got I2C compatible in the SPI interface, which is good. Lots of power features for sleeping and low power, and then different voltages that it can be ran at, and speed grades and all that. Anyway, obviously, if you're going to work with this, you're going to read this 452-page data sheet. And I've read this and many, many others, hundreds and hundreds of data sheets, but I've read this cover to cover before. All right, and it wouldn't hurt you to read it. But you don't need to. You can use this with the Arduino philosophy tool, all that, and not know anything about it really, just other than it's a black box. All right, so the whole idea is we can buy this one here, all right, and now there's knockoffs and clones. So there's legal and illegal knockoffs and clones, right? So that's another thing. And a lot of people, one of the things about Arduino is it's open hardware, so you can copy it and you can even sell it, right? But you just can't call it Arduino. If you want to call something Arduino, you have to contact the Arduino guys and say, hey, can I call this an Arduino blank? And usually they'll say, hey, sure, bro. So you can do that. Anyway, so there's the first one. And then you can see there's all these other ones. This one has Wi-Fi. This one has another, it has a module and a processor in it. Here's another one, This one's using another Atmel chip, the Mega 2560, which is more powerful. Little Arduino Nano. This one right here, as a matter of fact, this is the one that we based what did we do? We did the Simon game in the course, or you will, if you haven't seen it yet, when we do PCB stuff. And the design of just the Arduino Nano core, just this stuff right here, is what I used so that it would be compatible with Arduino when I made the little Simon game. And then I put a bunch of other stuff around it, right? But if you want something in this format, right, you can use it. But if you look at the tech specs, check it out. It uses the same AT Mega 328 processor, 8-bit processor, all right? Okay, so the whole idea, if you go through here, you can see they have a lot of versions that are Arduino. And all that really means is some of them are faster, slower, some are based on ARM, some are based on different processors, some are even based on Intel processors, or at least used to be. And yeah, like this one, I think this one's an Intel module, as a matter of fact. All kinds of crazy stuff. And there was even more when this war was going on, because the hardware Italian guy wanted way more. It's like, I just want tons and tons and tons of options for people. And then the other guy's like, no, it's too complicated. You're confusing everybody. Anyway, so whichever one of these you get, no matter which one you get, you can program it with the Arduino tool. And if you want to do simple things, it's always very, very similar. Now, obviously, an Arduino that doesn't have wireless can't do wireless things, right? So, like this Arduino, basically is an 8-bit microcontroller with GPIOs and a few peripherals. So if you want to blink LEDs, do serial communications, control motors, that's the one that you can use that'll do that. If you want to do wireless or Bluetooth, you're going to need one with wireless and Bluetooth features. If you try to run code for wireless and Bluetooth on this one, it's obviously not going to work because it doesn't have those features. So again, these interfaces insulate you from programming all that stuff. It's very simple lines of code, but the hardware has to support it. Okay, now, that all said, we can use one of these, but a lot of different companies create microcontrollers and other devices, and then what they do is they want people to use them. Hobbyists to start using them, as well as professional embedded engineers. So what they'll do is either the company itself or just individuals that are just like, I'd like to use this with the Arduino tool, will port the Arduino tool or create support or a plugin so that the Arduino tool will recognize and be able to use that other piece of hardware. So basically you make it Arduino compatible with software so that you can write an Arduino program to blink an LED, take that same program, run it on here, take the exact same program and run it on some other piece of hardware because they've made it compatible by adding software and creating the necessary files and so forth so that the Arduino tool itself can understand and build an executable for it. You're going to understand all this more as we go if this is all sounding crazy right now. Okay. All right. So what do we want to do? So I want to show you what we're going to use. So what we're going to use is there's a new wireless module called the ESP8266 and its big brother, the ESP32. The 8266 came out a couple years ago and the ESP32 came out about a year ago. These are price-wise, performance-wise, really almost an order of magnitude cheaper and better than anything you can get. They're Chinese made, and they're just so much better than anything else you can get from other vendors that cost just a lot more and are way more complicated to run. So the Chinese company called ExpressIF, which I think I have here, yeah, ExpressIF, and this company developed this, and they develop these other kinds of chips. So they developed the chip, and so I'm going to focus on the ESP32, the 32-bit version. So if you kind of go here to products, and you'll see they have these this big line of things right here. So here is the ESP32, and then there's some development kits and all that. So let's just talk about the ESP SoCs. We'll go here. All right, and the website is just expressif.com, and then it kind of explains, you know, what these things have. Now, so basically you can get these kind of chips, right, this ESP32 chip, and with very few parts, you can build an entire wireless Bluetooth transceiver with very few parts that's very small and very cheap. These things are like $1 a piece. They're crazy cheap and crazy powerful. So they have dual core processors. And just to give you a rundown of kind of the hardware, they're not ARM based, which is interesting. They're Extensa processors, 32-bit. They run up to 240 megahertz each, two of these cores, plus a third processor, the ultra low power processor that's on these chips. They have internal RAM here, 520 kilobytes SRAM, and then, you know, roughly the same of ROM, and then, you know, 16 kilobytes SRAM. And this is not actually real-time clock. I forget what this is called, but it is not real-time clock. I forget what that's called. Anyway, but you can see they have a lot of RAM and a lot of ROM. Then they add on a external flash and possibly an external RAM called PSRAM, and so that you can have 4 or 8 megabytes of flash, and then you can have 4 or 8 megabytes of RAM also. Then they have all these different names. Now I'm gonna apologize right now. The Chinese have crazy naming, and it drives me super nuts. And it's very hard to figure out what all these different things mean. So what you kind of have to do is go to Wikipedia, and here's like the ESP8266. And this is not too bad, right? If you read through here and you kind of look at this and you see all these kind of crazy names, the Vroom and just ridiculous names. And then there's ESP1 and the 2 and the 3 and the 4 and the 5 and this and the that. And which ones have FCC and which one's this and which one that. And then it's like, well, wait a minute. ExpressIF makes the chip. Do they make the module? Yeah, they do. And then there's another company, AI Thinker, that takes the chip and makes a module. Then there's other companies, and all these different companies actually make things with them, right? All right, so you got to kind of read through this, and it's crazy making. I'll agree. Then you go to the ESP32 on the Wikipedia, and again, same kind of thing. Shows you the architecture. Read through all this. All right. Then once you get down here, you kind of read all the different variants of it, right? So the variant that we are interested in is down here, and it's called the Rover B. Yeah, I know, Rover, W Rover. I don't even know where they came up with this. And there's two variants of it. One is called the one is called the B. The B is the newest version, and then there's the IB. The IB just means that it has the antenna socket on it also, a little micro antenna socket. So if you want that, it's called a U.FL connector, tiny little micro connector for antennas, but it has a built-in trace antenna also. The reason why we like this is it's the newest ESP32 chip built into a module, and it supports the external RAM to add more RAM. So we like that 8 megabytes of this PS RAM, it's called, all right, which is pseudo-static RAM. Okay, so this is what we want. So we want something that has this module, the ESP Rover B module on it, okay? All right. And then, like I said, there's other companies that then make things with the chips or the modules, and they sell them. So it's very confusing, all right? Okay. Now, so check it out. So then we go to a place like Mouser, and then we type in ESP32 Rover, right? All right, and then we see there's all these different modules. All right, and look how cheap they are, $4. So this is just the module, and the module has, let me make it larger so you can see it. Oh, that really helped. Not. Let me see if that helps. A little bit. It's got these castellated pins, so you could just put this on a board and it's completely self-contained and done. You look at the back of it. Here are the pinouts, right? Here's ground, power, and all the IOs. It's a complete system on a module. You don't have to do anything. But it's to program it and stuff, you need to add a couple little things, and to power it, obviously, you need to do that. So then people will then take these and put these on carrier boards to help you out a little bit, right? Okay, so see what that's all about. So if you scroll through here and look at some of these products, you can see here are some big boards that have the module on there. So check out like this, for example. So there's one of these with a Rover. It's called the ESP Rover Kit. And again, don't blame me about the names. I didn't invent all this. So you can see here's this kit, and it's just got a few extra things on here, some switches, some things like that, some headers. There's the module. On the other side, or I believe it's on the same side, not sure, because I don't have one of these. This one's got an LCD, so you can do things with LCDs, right? Okay, now that right there, what is that, 50 bucks, 40 bucks? Super cheap for what you get, all right? But you go a little farther, now here's what we're talking about. So now here, this one's the Rover B, and then this one is the Rover IB, which has the antenna on there. Okay, so let's just look at this one. And again, all these crazy names. So the manufacturer, ExpressIF, actually makes these, and they call these the ESP32 DevKit C-VB, all right? I know, crazy, huh? All right, so that's what it looks like. So the module has just been mounted on this little carrier board that's a DIP board, dual inline package, so that you can plug it into like a solderless breadboard or maybe another board to experiment with it. And here's a micro USB. Now, obviously, if you were building something, you wouldn't want this carrier. You would just want the module because you would have all this other extraneous stuff. But there's not much. Here's a power supply. There's a regulator. There's a couple transistors for booting it and flashing the memory. And then this right here is a USB to serial bridge, typically a FTDI chip or a Silicon Labs CP 2100, 2200 series USB UART, and then a couple little switches, couple LEDs, and that's really it. So really just a couple little things to talk to the thing from your PC, Linux, Mac, and then the pins are just pushed right out to these headers, which are just, if you look here, they're just standard pins to go into a solderless breadboard. That's what we want. So we want this right here, right? Okay, so you could buy this right here off of Mouser or DigiKey or someone similar that you can get access to, right? Or you can get it off Amazon, or if you're, depending on what country you're in, Banggood or Alibaba or Made in China. There's lots of different places. but we want something that looks like this, and it has the Rover B or IB with the extra little antenna connector on it, because we want kind of the latest chip with the external RAM. All right, so I know this is all crazy. Okay, so now if you go to Amazon, and I like showing Amazon because mostly the whole world can get to Amazon and it's easy to show examples. Okay, so if I type in ESP32 Rover into Amazon, a bunch of these things come up, and there's all these different companies that basically take the module and make a little carrier board, and this isn't the same one we just looked at on Mouser. These are all kinds of, like, this is High Let Go, and this is just this is Geekworm right here. This one's actually from ExpressIF, the manufacturer. You just kind of go through here, and the ExpressIF. Some are made from ExpressIF, some are made by different companies. Okay, the one we want, well, not the one we want, but the one I'm going to use in this demo that, we have maybe a half hour or more, is the Rover B module mounted on a board from Geekworm. And this is what we're going to use, but now we're looking for the one that's mounted on a board, which is down here someplace, I believe, or it's up here someplace. Let's see here. I think it's this one. I think it's this one. Yeah. And yes, it is this one. Okay, so, oh yeah, there you go. You purchased this item on November 14th. Good, thanks for that. So this is, and I could have got the ones off Mouser, but when I went to go try and order those on that day, they didn't have them. They ran out of stock that fast. So I said, okay, I'll just find something similar and then try and find this. Okay, so here it is right here. Now the cool thing is that the Arduino tool not only will let you program this, but it understands it. The only difference is that when someone makes one of these, when they run the pins out from the module, they typically run them out, pretty much out to each one of these pins, but they might put a power here, they might put a this here. So the pins are slightly different. So you need to pay attention between manufacturers of these boards, Geekworm, ExpressIF, Adafruit, SparkFun, High Let Go, you name it, where the pins are. So you got to kind of look up. So on this one right here, I can see all these IO pins. This is what goes on these pin headers. This is this pin header, and this pin header is this pin header, and this pin header. So you can see it's ground, B sub DD, IO34, blah, 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 blah. Then there's a couple peripherals on here, LEDs. Where are those LEDs? If you look right here, and I know it's hard to see, but the two LEDs are connected to IO27 and IO0. So if I somehow can talk to IO27 and 0, I can turn on the onboard LEDs, which is right here and right here, so I don't have to hook anything up. Otherwise, I can use all these IOs to do whatever I want. All right, now, okay, so the first thing that we got to get is we have to get one of these ESP Rover B, and you don't have to use that. You can use any ESP32 you really want, but I prefer if you use the Rover B because it'll be similar to what we're doing, and then it's, they're all the same cost, so I mean, you might as well get the latest, newest one. And this one has 4 megabytes of this extra RAM. All right, now, and then here's a pinout of it right there, which I already downloaded and copied onto my computer. Okay, now, all right, we're getting there. We're getting there. I want you to see everything. Okay, now, so, oops, you want to learn about the ESP. So you can go onto those websites, right? You can go to and I want to show you this, but you can go on to the Wikipedia page, right? And here we go. Here's an ESP32. So if you just go to Wikipedia ESP32, then you can read through here, all right? Which I suggest you kind of do, kind of peruse this, all right? Then you also go to the ExpressIF site here, and you can go here and kind of read their stuff, and all their documentation and support is in here. Now again, this is if you want to program it kind of natively and then really understand what's going on inside of there. But if you don't really care, you don't really need to do this, but I suggest you do, because if you're like me, you like to know how everything works from the atoms up. Okay, then there's another website, which is ESP, I'm going to find it for you. Yeah, ESP32.net. This is a really, really good website. This is like this big list of everything you could need. So if you really are into wireless and IoT, and you want to try out the Arduino and the ESP32, I highly recommend you read this page and scroll through it like all the documentation, and there's, tens of thousands of pages of stuff here, but it's got every piece of information you want, all right? And you can kind of go through here and see all these examples and this and that and development. And then there's what's down here, hardware, explaining to you. And this will really, really help you. This is really interesting and educational, so I really suggest you do this. It takes about a night or two or a weekend, but it's definitely worth it. You can see it just goes on and on. And this is just all the links. Then imagine going to all the links, right? All right, so I've done that, and at least once, and now, I've purged it out of my memory, but I did it so I know. Okay, after you go through all through this, there's a lot of different documents that you might want to read. One of them, so there's no book on the ESP32 from ExpressIF. They have documentation, which they've written, which is actually pretty good for Chinese documentation. I'm quite shocked, actually. But there's no like books on this. There's not anything big. If you go to Amazon, look for ESP32 books. I think there's one now maybe, and it's basically a copy of the documentation. Not very good. So there's this dude, this guy, and his name is Kolban. I forget his first name. He's actually from Texas, right? And I live here in Austin, Texas. He's from Texas. I haven't talked to him. But he started with the ESP8266, and then he read about it and figured it out and wrote a book about it called the ESP8266 book. Then he did the same thing with the ESP32, and it's totally free. This book is free, and if you just Google for it, Kolban's book on ESP32, you can get it off. I forget where it is. It's on one of these free booksellers that you can either give them money or give them nothing, and then just download the PDF. Neil Kolban, that's right. And anyway, so this covers the ESP32. I've read this entire thing, and the ESP8266 version that he wrote is much, much better. This one definitely needs work, and it reads, it's just like stream of consciousness. So let me get down to some of the actual text. All right, so there's Neil in Texas, and he starts talking. So the first few pages are pretty good. It's like showing you the pinouts of things, and this is important too. All these different kits that we're talking about, the Vroom and the this and the dev kit, and then showing with this kit, here's kind of the pinout. But remember, you might have a slightly different module. Here's the module, but then it's mounted a little bit different, so these GPIOs might be a little bit different. But a lot of times these numbers are always the same. So GPIO 36, depending on where they routed it out, is also ADC channel 0. So the multiple functions is the same because this is all from kind of a hardware perspective. So it's always the same. All right. And then there's the kit I just showed you, the schematics. All this stuff is all open. There's the rover kit we just talked about. And then all these different things explain how you communicate with them serially and this and that. So this is not bad. This really saves you a lot of time. Then what he does is he shows how to program with it with what's called the IDF, the IoT Development Framework from ExpressIF. This is a C++ library designed to be compiled with like GCC directly, or maybe you could do it with CLang, the other compiler. And forget about Arduino. That's for like, you're kind of a hardcore embedded guy, Linux guy, and you really like doing things with a command line. This will explain how to do it, and it's not easy setting it up, and he had to figure this out and get it all working, but he did, and he shows it, and you can do that. If you're really into Paine and Linux, I would give this a try. But if you just want to start playing with this thing, don't. But again, it doesn't hurt to just peruse through this, and then after a while, it turns into just basically a giant dump of the API that ExpressIF created with this IDF, IoT Development Framework, which gets boring. But thankfully, there is a index over here where you can kind of go to different things and see compiling code, building, audio, blah, 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 and kind of read about these different things. So this book right here is the best and only book, even though I really don't like it that much compared to his previous book, because this one just feels not done, rushed, could have been better, I don't know. And then, of course, here's the rover data sheet, which you get from the vendor. All right, this is a pretty good data sheet, and it's not too long. It's only 26 pages, so just read this. I would advise you read this so that you kind of know what's going on. ESP32 rover. You always read the data sheet. This is just about Bluetooth. This is something I'm interested in, the ESP32 Bluetooth architecture. Again, it's pretty short, just kind of talking about how the Bluetooth works on the chip. Okay, then what's this thing here? This is the ESP chip data sheet, not the rover, which is the module with the chip. This is the chip, and so this is kind of talking about the chip at data sheet, just electrically, very high level. Now here's the nasty technical reference. This is where things get ugly. So here is the ESP32 technical reference. Again, I've read this, and this talks about the programmer's model. It's 666 pages, you know, the perfect number to put for anything. And so read through this if you want. You don't have to, again, you don't have to read any of this stuff, but I'm saying if you really want to know, I would read it. And then whenever, you know, and people always ask me, Andre, how do you build computers? How do you design single board computers? How do you, build an ARM computer? This is how I do it. I read everything. Then I read what's called the hardware design guidelines. This is for hardware engineers. How do you build something? So I got to read this, and it's only 29 pages, pretty short. This typically shows us how to power it up, how to do reset, how to sequence the power systems, how to maybe connect antennas. There's reference schematics, and gives us something to start with so we don't have to do everything ourselves and figure it all out, right? Very, very short actually, and then maybe a possible layout and all that kind of stuff. Anyway, that is the hardware design. So these are all the things that a hardware engineer will read end to end, cover to cover, if I want to build something and program it hardcore and really, really know what I'm doing. For you guys, if you don't care about it, you don't need to do any of that. I might read maybe the rover data sheet, the 29-page thing, right? And I think that's it. Yeah, so that's it. So those are just some things. You can get them all from ExpressIF. Okay, now, all right. And again, I didn't even know what's going to happen with this, right? I really need a lot of time to do this, because this is really a whole course, and I'm just trying to do it in one lecture. So I'm going to tell you one thing I'm going to do. I think I'm going to make this into like 3 lectures, where we're going to try and get some stuff done this time, and then I'm going to do a couple more lectures. We're still going to use the ESP and do some more advanced things. Let's just see how far I can get. Okay, what are we doing? All right, so we want to program this with the Arduino tool. All right, I'm a Windows person, so I will use Windows. If you have a Mac or Linux, it's very similar. And there's a million tutorials online that can show you. So step 1, let's go get the Arduino tool, which unfortunately I already have. But how would we do that? We would just go to Arduino, go to software. Now they also have a new online tool which works from your web browser. I don't like anything online, so I like the real download. So you go to downloads, all right, and then we download the Arduino IDE. So it's up to version 1.87. All right, and then you can see you got the Windows installer, the Windows zip, the Windows app, and then Mac OS, and then Linux, all the different variants of it. All right, so download whichever one you want. All right, and then and simply install it. All right, and I'm just going to assume that you can do that. All right, now once you've installed it, now we need to do a couple things so that it understands the new ESP32. When you install the tool, so after you get done installing it, let's look here at my desktop and try and find any semblance of anything. All right, here we go. So here is the Arduino tool, and it'll create an icon like this infinity icon. And then if you go and launch it, let's go do that, double click. And then this will come up. All right. This actually is not the fastest thing in the world. I almost think like it's just sitting there purposely. All right, and forget this right here for now. Forget this right here for now. What's inside. Let's just pretend that's blank. It just loads the previous thing that I was working on. This is the Arduino IDE. So if you're used to Visual C++ or Xcode or even Eclipse, you're like, wow, that's super simple. It is super simple. And because it's so simple, you can't do a lot with it. You can basically compile and download, and that's it. You can't debug, you can't do anything. All right, that's it. Very, very simple. All right, and then as a matter of fact, let me just open up something real simple here. And every time, and another thing is, as far as I know, you cannot, there's no tabbing at all. It literally opens up another window, and that's life, right? Very crude, but a lot of people like this, and they're fine with it, so whatever. Okay, here's like a little Blink program, and we're going to get to that in a minute. Okay, let's go through kind of all of the things here. So obviously I can click that and make this bigger if I want, all right? So we can do that. Let's, as a matter of fact, let's do that. All right, so you go to File, And we've just got the standard things up here, open, open, recent. And then we have this thing called the sketchbook, all right? And the sketchbook is basically a directory on the computer with your programs. Now, normally, if you were in a big idea, big professional one, these would be your projects or your workspaces. They would have tons and tons of files for each thing, right? There'd be a gazillion files. In Arduino universe, there's not. There's like one file, your C file, and then if you need any other libraries or header files, maybe you put those in there if you understand what those things are, if you're that advanced. But if not, it's like literally a C file. Then all the other stuff, the tool brings in to build it. So it really, really, really simplifies this, okay? Then there's a thing called examples. This is interesting. What this is a list of everything that people have contributed, whatever, and there's all kinds of crazy stuff. And depending on what you've got loaded or not, you'll see more or less of these things. So for example, up top, there's 1, 2, 3, 4, up to like 11 here, right? And then there's examples for any board. Then there's examples for the ESP32. Now, the only reason we're seeing these is because I installed this, right? But if we go to built-in examples like basics and we say blink here, what'll happen is it's going to open up another window. Check this out. There's our other window. And we can close this one now, which drives me insane. And then here is the blink program. That's it. So now, if we look at this program, there's setup and loop. Now, if you're a C++ programmer, what's really going on here, the main in C++ is somewhere else, and then the main first calls setup here. And again, there's one thing I have to assume is that you know how to program in C or C++ a little bit. If you don't, you're going to be completely bewildered. But if you're okay to follow this, I think you can still get a lot from it. And then after setup is called, main just calls this loop, and then you can sit inside this loop. This loop function keeps getting called inside of main, excuse me. The loop function keeps getting called inside of main with a infinite while. And then also in that infinite while, there's a couple calls to some interrupt stuff and this and that because the system may have to process other things. So this, you don't want to stay in here and put an infinite while. You can, but you'll break stuff, anything else that needs to operate asynchronously. So for those of you that are C++ programmers, you put everything in this little loop, kind of like silly, and then just make sure you exit out of here and it'll come back really quick after it does a couple little things, and then you get control back again. All right, but don't stay in here. Don't block in this function. All right, you'll break some things. All right, so we see we have this little tiny program here, and if you look at it, it has this one thing that just says pin mode, LED built-in output, all right? And then it has loop, digital write, LED built-in high, delay 1000, digital write, LED built-in low, delay 1000. So all this thing does is it turns one of the GPIO pins into an output mode, and this is defined elsewhere. This LED built-in is defined elsewhere, and it's one of these, it's just a number, and in Arduino, you know, each one of the GPIOs has a number, and it's setting it to an output, and then we just drop into this next function, which then just basically asserts a high, it delays 1000, and wait for a second. Each one of these is a millisecond, I believe. And again, with Arduino, you have to look up these APIs and make sure what you think they're doing and all that, and you can do that on the Arduino site. Anyway, digital write, then it writes a low, and then it delays again. So basically, it's going to blink an LED. That's what that would do, right? And we're going to play with that. All right, and then you can go read about it right here. Okay, now let's keep looking. What else is here? So that's what all the examples are. And then close, open, save, and then preferences. Now this is important. Okay, first, network settings here. If you want to mess around with anything that's advanced stuff for proxies and all that, you don't really need to worry about that. What you do need to worry about is this. So sketchbook location. So you see in my computer, D development, NTV projects, ESP32 sketches. So I know where this stuff is going, right? So just put yours on C or D dev or whatever, wherever you like to put things, and create a directory. Typically, I just call it ESP or whatever the project processor is, and then sketches, and then it'll dump everything inside here. Then there's just some editor stuff, some things like this, verify code after upload, etc., 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 etc. Just some optimization things. You can play around with these, check for updates on startup, all that kind of stuff. Then this is important, all right? This is where you go to find additional boards. So when this thing loads up, you are not going to have ESP8266 or ESP32. the only way you're going to get these extra packages is someone's got to give these things to you. They have to be in a format that this tool, Arduino, understands, can parse, and bring all in. And there's a whole series of tutorials and documentation on if you're a vendor and you have your own microcontroller, your own project, your own whatever, and you want Arduino to be compatible with it, you have to build a file, which is a zip file, etc., that has a bunch of other files and INI files and JSON files and XML files, all kinds of stuff that describe everything and then contains everything, all the library files for the particular processor. Given that, that's what this is all about here. So for the ESP8266, here it is here. This is the ESP8266. All right, and then if you look at it, it says http arduino.esp8266.com/stable/package underscore ESP8266com_index.json. Okay, I will put this in the documentation, and then, but that is not important. We're going to put that because we want that also just in case. But here's the important one. This is the 32-bit ESP. So this one is https://dl.expressif. So this is coming right from the ExpressIf site. .com/dl package underscore ESP32 underscore index.json. This bad boy is the one that's important. So you have to add this to this preferences under the additional boards, okay? When you do that and click OK, cool. Now, it may need a restart to be able to find this, so we're just going to restart this just in case. And this is not like this hardened, awesome tool. It is a Java program, and it is buggy, and it is slow and all that, but you know what? Millions of people use it, and they get around it, so I mean, whatever. Okay, now, so now here we go. So we already did that in preferences, and it's sitting there. That's cool. All right, now what we need to do is we need to go to Tools, and there's a number of things we're going to do here. But one of those things is, and the order we do things in can change, but we're going to go to Board here, and it's saying what the board is right now. I don't really like this. Pretend it doesn't. It says the wrong board. All we want to get to is this thing called Board Manager. We double click that, and then it shows all the different boards installed. All right, so what we do is when you first install this, I want you to type in ESP32. All right, once you do that, then boom, here it is. Here's the ESP32 stuff it just found, which is going to give you all the ESP32 libraries, examples, sketches, and all that. It's already installed, so I don't need to install it. If it wasn't, it would say install here or install here, and then I would install it and then say close. So it's already installed. Now I'm going to say close. Cool. Okay. Now, what's the next thing? So when I go here, now it says pick your, so now the whole idea is we're going to pick our actual product that we have. So I have the ESP Rover B module, right? I don't have the Rover, I have the Rover B. Now the good thing about these Arduino things is a lot of times, even if you don't have the exact one, close enough is close enough. So now, if you hadn't done what we just did, you wouldn't even have any of this stuff down here. All this stuff just populated after we put in that information. And you scroll down, and these are all the different companies that are listed now because of that installation. All right, and there's hundreds of these boards, so obviously they're not all here. All right, but here's one right here, ESP32 Rover module. I have the Rover B, which just has more RAM and this and that. But as far as the Arduino tool is concerned, the compiler, the libraries, it'll compile for it and build an executable and be able to upload it. It'll work. And then there might be some little tweaks. But that one right there seems to work. You could try another one. You could say, what about the ES32 Pico Kit or the Node 32S? Lots of them will still work, right? They're almost identical as far as the profiles and the software's all been loaded. Anyway, so I select this one right here. Good. And then it goes back. Okay. Don't worry about any of this stuff. This is just speed for doing things, but upload as fast as possible, which is this 921600. The flash frequency, you set it. All these will default, but you can tweak them if you want. Don't mess with this QIO mode. That's the mode that you want to use. Leave this as default. There's other things you can do here. Core debug level, leave that at none. Now, the port, when you plug in the Arduino to your computer, which we're going to actually do. I'm going to unplug it and plug it in so you can kind of see what happens. it's going to create a serial port because there's a serial USB to serial chip on the Arduino. That's going to come up as a serial port, so you got to select which one, COM135. That'll give you a lot of trouble if you don't do that. So we got COM35, okay, cool. We don't need to get the board info. That'll pull information from the board. Now, down here is some extra stuff. To make the any Arduino an Arduino, it kind of has a bootloader on it, and that bootloader helps the Arduino tool talk to it. We don't need to mess with that right now. And if we were to do that, we would have to program the bootloader, chicken and the egg problem, onto the board. How would we do that? Well, we could use one of these tools here. These are like big tools, like this. So this right here is like an Arduino. This just happens that this is not an Arduino. This is an Avar programmer. So this is used to program, and I've got maybe 100 different programmers in my lab of all kinds of different things. So that's like a $50 programmer. That's one of these. It's this one here, the AVR ISP MK2. So if I wanted to burn a bootloader onto a chip that I made and I want to make it Arduino compatible so this tool could talk to it, first I'd have to use that, then get the bootloader on it, then I could talk to it with the tool. I know, crazy, huh? But you don't need to worry about that, and then that just burns the bootloader. So forget about that. So once you select the board from the boards manager and load in the ESP32 support, you scroll down, you'll be able to have all these different ESP32 things. Pick the board you have, but I want you to get the ESP Rover B or IB, okay? All right, now once you do that, now we can start grabbing things out of the examples and trying them. All right. Now what I want to do is I want to go look at this hardware and I want to plug this in and kind of show you what's going to happen here. All right. So let's go over to the bench and just take a look here. All right. Okay. So in front of me here we have the module plugged into a solderless breadboard. All right. And then here's another one right here. I always get 2 or 3 of everything. So if I blow something up, I'm okay. So on the back here, you see it says Geekworm, and let me zoom in just a little bit for you. Help you out. There we go. Okay. So it says this KE32-Rover-C10, and then the whole idea is it's got 4 megabytes of PS RAM. There's another version with 8 megabytes. I think there might even be a 1 megabyte or a 2 megabyte version. But anyway, Geekworm is the manufacturer, and then the Express If module is right there, right? And you can see it says ESP32 Rover. It doesn't say the B on it, and that's just more or less the company gets sick of stamping every little version of everything on these metal cans, so they just kind of leave it off. And then, like I said, if I was going to build a computer or build a product, I would just have the module. I don't need all this stuff right here. Now, this one has this extra UFL connector, and then here's the antenna. Right there's the antenna right on the PCB, but then if you wanted to add an external antenna with more gain, boom, you can just plug it right in there. Then here is our, this is our serial UART, USB serial UART. There's our regulator to regulate the USB 5 volts to 3.3, couple switches, and then a couple LEDs, okay? And then I just like this so I can look at it and then see what these I/O pins are as I'm messing with it, even though I can do it on the computer, all right? Okay. Now, so what did I do here? So what I like to do is mount this thing on here so I can play with it and experiment and do whatever I want to do. All right. Now, problem is this thing is so wide. If you try to put it in just one of these solderless breadboards, you're going to have no room on either side to do anything. So you need a bigger one, or you need 2, and then you straddle the power supplies rails. When you straddle it, then you have 3 on this side and 3 on this side. Okay, so what I did was, and this is all plugged in right now. So as a matter of fact, what I'm going to do is I'm going to unplug this because I want you to see what happens. I'll unplug it, and then under here, there's nothing magical. All I did was I looked at the module itself, all right, and I looked at it and I said, you know, where is ground? Where is ground? Where is, you know, the 5 volt? Where is this ground? Where's 3 volt? Where's all this? Then I labeled them like this, all right? And then this is a 5 volt. So if you want to put 5 volt in, you could put it in there, and that's red. This is actually orange. And this is 3.3 volt. So now the board itself is going to generate the 3.3. When you put the USB in here, we get 5 volts roughly, right? 4.2, 4.5 to 5, 5.2. It regulates it down to 3.3, powers the module, and then outputs it right there. That output then goes, and then I use it to power this entire board. Now, I don't want to put a lot of things on here because it'll all be powered off USB, but as long as we don't go crazy, we have 500 milliamps to work with. Okay, then I looked at all the grounds on here and then I connected them all to these ground. And then again, once you take the class, you're going to know that we have power rails here. We bypass capacitor and we use it like a 10 microfarad, a 0.1, 10.1, 10.1, 10.1, and then just connect all the power rails up. So everything is 3 in ground, nice and clean. And then we can put this back in here like this. And we don't want to blow up anything. There we go. So that's it. All right. And then we'll just wiggle it in. Wiggle, wiggle, wiggle. All right. Now we'll plug this in a second so you can see what happens again. So that's it. So now all of our projects we want to build, we basically just look at the back of this and we say, here's all these IOs. Now each one of these IOs can be a GPIO, but it could do PWM, it could do a UART, it could do Ethernet, it can do all kinds of crazy stuff, right? SPI, this and that. So it's all multiplexed. And the Arduino IDE knows about this. And so most things, like if you want to do something on one particular IO, you can tell that IO to be different things, and the libraries and so forth will help that happen. But knowing what is potential or possible on each pin really helps, and that's why having Kolbon's book or another reference that shows, every one of these IOs, and it says this can also be I2C, this can also be this can also be that. That'll help you so you don't try and put something on a pin that it just physically can't do, right? Okay, so anyway, that's that. So what we're going to do is we're going to start off with just blinking an LED. We're just going to keep this super simple, all right? So what I'm going to do is I'm just going to pull this stuff out. I've got all my stuff here as usual. And again, if you just jump into this bonus lecture for fun, then you will learn that I like to keep things super clean so I don't go crazy. Now, we can wire things together with separate wires like this, and I've got them all color-coded here, all my different colors, or we can do these, right? And you can get these off Amazon, all right? So just for fun here, I'll just pull a few of these out and split them up here. And I've got hundreds of these already split, but I like you to see the process, so who cares? It doesn't cost that much money. All right, it's not going to put me into the poorhouse. All right, so we got some wires right there. So we can use those, and those go real quick. Why don't I like these, though? You guys know that. Because whenever we do anything like this is very noisy. I hate that, right? But if we're doing low-speed stuff, it's not going to kill us, right? If we're doing high-speed stuff, if we want to make something real, we take a nice piece of wire, we bend it at each end, boom, and maybe we go, here, and then maybe we need to go over here, right? And we keep it low to the board as possible for noise and so forth, right? But the stuff we're going to do right now is not that big of a deal. Okay, so now what we need to do is we want to do like the Blink demo and see how would you download this on here. The first thing I want to do is I want to show you what happens when we plug this in. So what I'm going to do is I'm going to plug this in and we're going to watch back on the computer what happens, all right? So here we go. I'm going to plug it in and then we're going to watch the computer. Here we go. Let's plug this bad boy in. All right, so now we're back here on the computer, and let me just close that tool. And then if we go look here, so nothing's happening. So what's happened here is that the USB to UART bridge that's on that device has already been installed in this computer, and then it just gave it back to me. All right, so check this out. If we go up to the device manager in Windows, you can do this in any operating system, and we look under COM ports, check it out. There it is right there. It's COM135. All right. So COM135. But if I were to take that other module and plug it in, it'll actually hook it up as another COM port. Let's do that for fun. All right, so let's go back over. All right, so we're back over here. So I'm just going to unplug this. And then what I'm going to do is I'm just going to get this other module. And I'm just going to I don't really want to mess with this too much. Maybe we can put it here. I'm just going to kind of put it here a little bit. And we're just going to plug it in here. Here we go. So this is a different module, so it's going to come up with a different ID. All right, so cool, that's going. Now, when we plug that one in, now the driver's already been installed because whatever USB to serial chip that's on there, which I believe is a Silicon Labs, it's definitely not an FTDI chip. The driver's already in my computer, so it doesn't reinstall the driver, but what it does do is go here. Now, both of them are coming up as the same COM port. That'll happen sometimes, okay? And that's okay. So the bottom line is when you do this, you are going to potentially have to sit for a minute while it installs the driver for that USB to serial. So this is all done as pure serial. There's no complicated program. It's just pure serial. That's why that bootloader is important for the Arduino, but it's already the Arduino toolchain support within for the ESP32 already knows how to talk ESP32, so you don't have to worry about doing any bootloader stuff. Okay, so we know it's on COM 135, so let's go ahead and minimize that. Let's go back to the bench here and let's switch it back. All right, so now what I want to do is we're going to do this blinking LED demo, okay? And to do that, we need to blink an LED. Now there's two LEDs that are on the board, right here and right here. And they're at IO, I believe, 0 and 27. So first I'm going to do it there so you can see it. And then right after we get done with that, then we're going to use one of the IOs. Let me put this back here. We're going to use one of the other IOs here. So if I turn this over, like right here is here, and then of course over here is this bottom row. So we're going to use maybe one over here. And I think IO15, 1, 2, 3, 4, 5. IO15 is the 5th pin from here. So if I go here, 1, 2, 3, 4, 5, there's IO15, okay? So if I take that and I plug that in there, all right, let's get this nice and centered for you. And maybe you guys want to zoom in a little bit, help you out. Okay. Not too much because we won't be able to see. There we go. All right, so there's IO15, and then let's take an LED. Now, remember our LEDs? Usually the big side is the ground. Well, check it out. In this one, the big side is not the ground. It is the opposite. It's the anode. It's not the cathode. So this one is tricky. So the small side is cathode. All right, so there it is right there. We're good to go. Just to check that that works, let's take plus. So here's my +3 rail, and let me scoot this up just a little bit. There's my +3 rail, and 3.3 volts not going to blow this thing out, so good. All right, so this is grounded, so if I get a positive there, I'm going to be good to go. I'm just going to put a little current limiting resistor in here, 100 ohm, brown, black, brown, just because I like to do that, and it's good practice for you too. Okay. So there it is. So now we got this LED in here, but we don't need this one because we got two built on here, but those are boring to use. We want to build something, right? So let's see if we can get these LEDs to blink. So I'm going to kind of keep this right here. So we have this screen, and then we're going to work on the computer so that you can see what's happening in real time. All right, so let's go to the computer. Okay, so we're back here on the computer, and let's load our Arduino tool. Where did it go? Where did it go? There it is. Cool. Okay, so this is the blink, and this will work just like this. We need to define this and change what it is. So what I'm going to do is I've already made a version of this. So I'm going to say open recent, and I'm going to say blink ESP32, and I'm going to give you these. So here's my version of it. And what you will see is I haven't really done anything. And you know what? As a matter of fact, let's also help you guys out. Let's go to preferences again. There's a font in here. There it is. Let's make this size 16. And cool, so that helped, all right? So hopefully you can see that a little bit better. Okay, so if you look here, I said lead pin is 15. Now also, let's go here. Here is that chart that shows what's going on here. So on these pins here, we see that on the board itself, remember I said IO27 and IO0 actually connected to those two onboard LEDs through, looks like, what, 2K resistors? So we can actually turn these LEDs on without using anything. So let's give that a try first, all right? So we're going to make lead pin, we're going to say, what is it, 27? So 27. All right, then we go to setup, and it says lead pin output, then serial begin. This, I'll show you what this does. This turns on the serial port, the same serial port we're going to use for programming. After this is programmed, we're going to use for communicating for debugging, real crude debugging. So it'll put it 115K. Then we go down to our main loop, and in our main loop we say hello program. So that's going to print out on the serial terminal. At the same time, it's going to turn on this LED pin high, then delay for 10 milliseconds, then turn it on low and delay for 10 milliseconds. Okay, let's make that a little bit longer. Let's make it 100 milliseconds. Okay, cool. All right, so I'm going to save that. Now, let's learn what else do we have on this interface. Not much, people. Okay, so first let's go to Tools. We got our ESP32 selected. We got COM135 selected. That's correct. We know that. That's about all there is to it. Now, we got only a few buttons here. This is it. So what's this? Verify. Verify, and it comes up right here and says what it is. This means compile. This means compile and link and build, basically. This means compile, link, build, and upload. So it's going to upload it over the serial port. And then these three right here, this is just a new file, and then this one is open file, and this one's save file, which is, of all the things to put here, you know, they just put those few little things from the file menu. That's it. This is the entire Arduino experience, and it's basically C, all right, C++. All right, so let's go. So let's go ahead and let's just verify. Now, down here, I want to say, I can make this, yes, okay, I grab that. So I want you to see what goes on down here. All right, so let's go ahead, let's just compile it and link it. And compiling means converting it from C code, obviously, into machine code. And then linking means linking with any external libraries or references and then building a final executable. So it's compiling it right now, and it's compiling it with GCC or CLang. And I'm not sure, like I said, I don't use Arduino, you know, because it's a kind of a hobby technology, but the two compilers, GCC and CLang, CLang's been replacing everything. I prefer it. I believe now it kind of defaults to CLang, but I might use GCC. Not sure. Something to figure out if you're into it. Done compiling. Sketch uses 214,092 bytes, 16% of program storage. Maximum is 1.3 megabytes, it looks like, and then global variables, yada, 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 and all this. Okay, now remember, we're on the big ESP32. If we had been on a Arduino Uno, the little 32K, right, this right here, look at this, 214,000 bytes, right? The little Arduino Uno only has 32K bytes. Of course, the program would be smaller because it wouldn't have all the complicated libraries that go along with the ESP32, all right? Okay, so that's done. So it worked, great. So let's go ahead and upload it. So we'll go ahead and hit upload, and we'll be taking a look at the ESP32. So hopefully I'm doing a split screen kind of thing right now because I'm not going to go back to the bench. I'm going to sit here with you. And there's verbose modes also here. And you can see now we went into the programming thing, and the programmer is written in Python. And so it's called PyTool, I think, something like that. And then now let's take a look at this here. All right, let's back up. All right, so it's called ESP PyTool, and it's this programmer. And then it says, hey, the chip is this, the revision code, it's saying what it's doing, blah, blah, blah. It's saying, hey, I'm going to 921/600 baud rate, and then auto-detected a flash size of 4 megabytes, compressed 8192 bytes to 47, because there's probably a bunch of zeros in it. And then it starts writing all these different memories that the ESP32 has. And then it's saying, you know, all the different percentages done, and then doing a verification. Remember, we had that in the preferences, do a verify, so it checks the memory. All right, and then lastly, we see this hard reset via RTS pin. So the programming interface on many of the Arduinos is done completely serially and through a USB to serial UART, like the FTDI chip or the Silicon Labs chip. And so to be able to control various things on these microcontrollers, they have to do it serially, just with, you know, a serial interface. So there's not much that you can do there. However, most serial interfaces have a modem interface. So they have DTR, data terminal ready, clear to send, request to send. They have a few extra pins. And then what they do is they take those pins from the USB to serial UART, and then kind of decided, hey, on the Arduinos, we'll use a couple of these pins, DTR and RTS, I believe, on some of the different Arduino hardware to be able to talk to the control pins on the microcontroller or on the module that control reset, boot, flash mode, etc., or what are called the strapping pins on there. And then therefore through the tool can control remotely to put the chip or the module into program mode or boot mode or this or that, so that we don't have to do it by pressing buttons. So anyway, that's what this hard reset is. All right, so anyway, you can see hopefully that the thing is blinking, and it's blinking on the correct LED. Let's go real quick and let's change this to, as a matter of fact, let's go ahead and add the other LED. All right, so there's two LEDs. One was at IO pin 0 and the other one was at IO pin 27. So we're just going to copy the code. All right, and we'll just call this 2. And this is what's cool about, and this is why people like Arduino so much. The funny thing is they think they're programming in processing, and they're not. They're programming in C. This is C. I hate to tell everybody. C++ actually. All right, and then here we're going to turn this pin high. We're going to turn the other one. Matter of fact, let's do opposite. So we'll do this low, and then here we'll turn this one, make sure we got the right pins here. Of course, it's always, I'm always in a rush, and time is always against us. So I'm always trying to go as fast as possible to give you as much cool stuff as quickly as possible. All right, I just Control S and save that. Let's just go hit upload. And give it a minute here. And this is never a fast process under Arduino. If you use the GCC or CLang compiler with the IDF, the IoT Development Framework, it's definitely faster. All right, and now we did the hard reset, and there we go. And again, I have to look over there because you're seeing the edited version. So you can see it's blinking both LEDs just as it should. So how cool is that? Now, let's get that last LED, the one that we have the wire to, we know that's on IO pin 15. So let's go ahead and let's just undo what we just did. We'll just undo this code, and then let's make this 15. And we'll speed it up just a little bit. We'll make it 50. All right, and let's go ahead and upload. And I'll give you all these programs in a zip file. They're almost identical to the examples. All right, again, we're compiling, then we'll do the upload. And then I'm just going to show you a couple more so you kind of get a feel for this. And you can go through all the different examples and see what works and what doesn't. You have to change these GPIOs and you have to understand what's available on each GPIO. But many of the basic ones work. And then you can see our LED is blinking. So we've talked to the pins on the board and an external pin. Let's do something else. So now I've also done a PWM. So let's go here. And as usual, it opens up another window. Let's close this. Okay, so here we go. Oh, that's interesting. The preferences are per file. Huh. All right. Let's just go there and hit OK. Is that 16? I guess it is 16, huh? Okay. Yeah, there's a small font right there. All right. So what this one does is it uses the PWM software or API from the Arduino to talk to the PWM hardware on the ESP. Now, if you were to do real PWM and you were programming low-level embedded C, C++ code, I assure you it would take more than 2 lines of code. This is literally 2 lines of code. LED setup, LED attached pin, and then LED write. It's like too simple. That's why people like Arduino. All right, with this particular API that someone made, so I just found this little program, and it looks like you set the frequency. You can set it to kind of whatever to make the whole PWM. And remember, pulse width modulation is a bunch of different pulses. Each one of the pulses has a duty cycle. As you change the duty cycle, that one pulse gets averaged, and then we can control the brightness and generate an analog signal. So we can change its frequency. This LED channel, there's different LED channels. And I haven't looked at the API to see exactly how many and how these would map to the hardware, but it seems to work right now as is, so we're just going to leave that. LED pin 15, which is the pin it's already connected to. So then we say, okay, LED channel, the frequency and the resolution. This is just how much resolution we have to control the PWM. So in this case, it's 8-bit, and the hardware might have 16-bit PWM or 8-bit PWM. Right? So it's saying use the 8-bit so that gets mapped to the 8-bit hardware, even if it's 16-bit. And then this basically sets it up, couple setup things, attach the pin, and then you can always look at these inside of the documentation for this particular API, which is either made by Arduino or a third party. And then we just run a little for loop here. We go from 0 to 255, and then basically swipe the duty cycle so that we'll get this brightness kind of thing going on. And that's it, and put a little delay in there so we can see it. So I didn't really change anything other than changing this LED pin. Let's go ahead and go for it. So let's compile and upload, see what happens. And there's at least this little progress bar over here, although it does not show a percentage. I wish it did. It'd make the time seem like it goes a little bit faster, but I'm always trying to be entertaining. All right, and it's amazing how long it takes for such a little thing, right? And is this multi-threaded enough to do that at the same time? All right, And if you look at it, I've got to look at the camera. Yep, it's working. It's going up, right? And now, so now if we wanted to add to this, what if we wanted to go up and go down and kind of strobe? Well, we could do that. We could put, so this, so what happens here is we're going from 0 to 255, and then we have this loop function always gets called over and over and over. Even though it exits out here, it gets called again by the real C main, right? So what we can do is, and one thing you'll learn is I like brackets on the same column here. I like to do this, and we haven't really gotten into any programming. Now, normally there's better ways to do this, but we're just going to do this like this. So we're going to say duty cycle equals 255 to duty cycle greater than, we're going to start at 255 and the duty cycle greater than or equal to 0. And then we're going to say duty cycle minus minus. That's it. And then we'll put the same delay here. And matter of fact, let's speed it up a little bit. We'll say 10. So it'll do an up and a down, and it'll exit out of the loop, right? Let's go ahead and give that a try. While it's compiling and doing all that, the program, of course, is still running. It hasn't told the processor to reset. It does it at the very end. All right, compiling, and now we're uploading with a little PyTool, and now it's done doing the hard reset. And you see it goes up, and then it goes down. Up and down. There we go. Perfectly, just like we would expect it to. All right, so there's PWM. And then I've got one last program I want to do. So the whole idea of using a wireless module is to do wireless stuff, right? So let me show you this. Now there's lots of wireless demos inside of the ESP examples and so forth, but many of them don't work right and whatnot. There's a cool website, and this is called Random Nerd Tutorials, and this guy has got classes and ebooks and all that kind of stuff, specifically on ESP32 and other things. And he's got this example here where he made some code, and he shows it to you, and you can just copy it here and just copy and paste this entire thing into there, and he kind of shows you how to do this. So Random Nerd Tutorials, ESP32 Web Server Arduino IDE, to kind of show you how you do this with the Arduino. So this is a good working little program. So what we need is, we need 2 LEDs, and what it's going to do is, from your phone or from your browser, you can control 2 LEDs remotely over Wi-Fi, which is really, really cool. So the first thing that we need to do is we just need to hook up 2 LEDs to a couple of GPIOs. Now, his code, I took his code and modified it a little bit because it's a little bit hard-coded, and I cleaned it up a teeny tiny bit. And let me go here and show it to you. So we'll say open recent, and it is called not Hello Server, Red Green Server. Okay, so here is the program, and if we look, it's not very long. All right, so this is an entire web server. How crazy is that? All right, so it'll respond to HTTP requests for the page and then print the page out. So I'm not going to go through how this works. You'll have to read this, but the one thing is you're going to put your SSID and your password inside of SSID and password. You'll put that yours inside there. It's going to run this thing called web server on port 80. And then what we care about is I changed this because he was calling it, using the numbers 26 and 27 like pins, and so I just generalized and called it red LED and green LED, and then we can set these to any pins we want. So we're going to use pins 22 and 23. Here's the interesting thing. When you start messing around with Wi-Fi and Bluetooth, some of these pins on the ESP won't work right anymore, and you got to be careful. So as I tried a couple different pins, they didn't work, and how I would find that out is I would look at the data sheet and the ExpressIF documentation and make sure, oh, this pin can only do this, or this pin can only be input, and so forth. So anyway, pin 22 and pin 23, which are, if we look over here, let me move this, pin 22 and 23, right here. So they're on one of the rows, the 2 last pins right next to ground, and we'll look at that. We'll go over to the board and we'll actually put this together. Pin 22 and 23, we're just going to hook up to a red and green LED, and we'll put 22 to the red and 23 to the green. All right, again, we have our serial begin, and so we can see what's happening in the serial port, and then down here we have this while Wi-Fi status, so it's trying to connect. And again, we're talking about a few lines of code. Wi-Fi takes like 1,000 lines of code to get something going if you're doing low-level stuff. And then we go to the main loop here, and basically it checks if you're connected, and then it sends out the HTTP response and so forth, and the proper uh, content headers and so forth. And then basically you've got two controls, and we can click these on the screen, and then as we do that, then it sends back to this little web server, which then controls the LEDs. Super cool. All right. So anyway, you should study this and figure out. Again, I'll put this inside of the materials. All right. So first thing let's do is let's go hook an LED, a red one to 22 and a green one to 23. So I'll meet you over on the bench. All right, so we're over here on the bench, and now we need to know where 22 and 23 is. So yeah, 22 and 23 are right there, the last two before ground. So 22 is the third one. All right, so all I'm going to do is I'm going to undo this, and this one's our red one. So I'm going to put this here, and that's going to go there. How easy is that? And that'll be our red one, and then let's get another 100 ohm. Here's another 100 ohm. Boom. Put that right there. We'll put this right here. Super simple. And then here's our green LED, and let's make sure which way this one works. So it works like that. So the ground is the ground the big one in this one, the cathode? Looking at it, yep, cathode is that one. The cathode is the big pedestal in this one. There, that is it. So we should be able to turn these on and off. Let's go back to the bench. All right, we're back here on the bench, and so now what I'm going to do is I'm going to put in my SSID and my password here. So close your eyes. Okay, so I put in my password and stuff, and now we're going to upload this. Now, in this example, we're going to look at the serial terminal, which has been running the entire time. We haven't, we didn't really look at it with the other ones, but it was actually running. I'm going to show you how to do that. I kind of forgot to show you that, but I'll show you in this. And that serial terminal is good. It was just printing hello programs or whatever, and it's a good way to be able to send information back and forth so that at least to serial terminal, and you could type in it too, and we could send information back to the ESP or any Arduino. All right, so now we're connecting and we're uploading, and this program, of course, is bigger, and it's not scrolling. All right, and it did the reset, so now it should be working. Okay, so check this out. So now, watch what happens here. So we go up to Tools, and then we say Serial Monitor. All right, so now this is monitoring. So the serial port 135 is now still connected to the PC, and now the programming hardware is not talking to it anymore in that mode. So we can look at it. All right, I'm going to go manually reset it. I'm going to press the reset button. All right, and then we see the ESP do some crazy stuff, and now here's our program running. So now it says Wi-Fi connected, IP address 192.168.1.203. So if we get a web browser or a phone and we connect to this IP address, we should see this little web server, all right? So what I'm going to do here is I'm going to type that in, all right? And then I'm going to open this back up, all right? And then I'm going to put it right there. Ready? There it is. Okay, so here it is right here, and now I'm going to press these buttons and let's see what happens. So it says red state is off and green state is off, and I'm looking at it and it looks like it. So I'm going to press on. The red one turned on, red one turned off, the green one turned on, green one turned off. So how crazy is that? So we basically just built a web app that's running. Here's the code for it right here. There it is. There's a little serial monitor. We can see that. And then, of course, here's what our little web interface looks like. And let me just make this small so we can kind of put everything on the screen at once. And there we go. So how cool is that? That is pretty cool as far as I'm concerned. And here's the program. Okay. So that is it. That is what I wanted to show you with the Arduino stuff, how to install the tool and get it all to work, and do a couple simple programs. And then, like I said, you just kind of go here to File, and go to examples, and then you can just try loading these different things. Many of them will work, some of them won't, and then there's specific ESP examples, more advanced, that have wireless and Bluetooth. You can play with those, load them in, and try and get them to work. All right, so that's it. Now, maybe in another video we'll do some other stuff, and then what I wanted to show you was this tool here. I'm going to close this real quick. I'm just going to give you a preview. And this is VS Code. Where'd it go? So Visual Studio Code is a kind of an editor that Microsoft made. And then it's very powerful. And then you can see here's that blinking LED program again, right? And then what you do is there's a piece of technology called Platform IO, and it's a plugin to this. And then it allows us to program, well, you can make it program all kinds of things. Arduino is one of them, right? So it's got support for that, or other processors, all kinds of things. So this is a much more advanced tool than the Arduino tool, as you can see. So the next step will be, maybe we'll do in another video, we will install Visual Studio Code, then we will install the what's called Platform IO plugin, which is a whole series of libraries and technologies to be able to program all kinds of microcontrollers and boards. And then we'll see how do we build projects with Platform IO and use that to program the Arduino and do debugging and all kinds of crazy stuff. All right, so that's what we'll play with next, and we'll kind of see what this thing is, maybe in another bonus video. Like I said, I'd maybe like to do 3 videos with Arduino and kind of have some fun with this, all right? But this will be the next thing to kind of take it to the next level, all right? So I hope you guys like that, and sorry for the long video. You know how it is with me. I like to do these long videos to kind of go through all this stuff, all right? So I'll see you in the next one. Bye. Hey everybody, you know, I've had a couple students that have been searching for parts and having a little bit of trouble. Now, even though during the lectures we go over, you know, looking for parts at DigiKey, Mouser, Amazon, Adafruit, SparkFun, looking at their prices and how to search for them, but that information, of course, is in the lecture. So as you watch the course, you're going to see those lectures and learn how to best find parts and get them for a good price. However, those of you that are kind of skipping around and maybe trying to do stuff, you might get into a situation where you're spending too much money or whatever. So I just want to take a couple of minutes and show you. So this is it's a bonus lecture, but it's not really a bonus lecture. This is just a quick little anecdotal piece of information so that people aren't wasting time and money. So one customer was looking for like capacitors, another one was looking for LEDs. And so, you know, the first thing is, let's start with DigiKey. So there's DigiKey and Mouser. Those are the 2 sites I recommend use as a search engine. Now, depending on what region you live in, you may have to use Newark or Element 14 or another local distributor. But DigiKey and Mouser ship worldwide, #1, so you can always use them if you want. Anyway, so let's say that we wanted to find like a 0.1 microfarad ceramic capacitor, all right? And we'll just say cap. So we type, you know, something roughly like what we're looking for into the search engine. Now, the thing about the search engine is you have to be careful. If you get real narrow, sometimes you won't get anything and you'll think that it's not in the search engine. So you got to be real loose with these search terms. And then also the order that you change the search parameters makes a difference in this. All right, so we see there's ceramic capacitors, 11,780 devices. All right, that's what we want. Now, when you get to this screen here, you see it says more filters, and we can get more stuff down here if we want, or over here we can say scrolling. And I'm kind of I like it to be scrolling. All right, so now I just want, there are lots of capacitors. And again, this is what the course is about. There's 140 lectures that explain all this stuff, right? So I'm not going to explain it in 5 minutes. But if we're just looking for, you know, a real basic 0.1 microfarad capacitor, we're going to say in stock. I want it RoHS compliant. I want it, obviously, the part to be active. Let's say we want it cut tape. All right, now, what kind of voltage rating do we want? When we're talking about small capacitors, typically I want like 25 volts or more. So I'm going to say 25, and I'll just say up to 2,000. All right, we'll apply filters, and apply your filters really slow when you're looking for things. Don't set up too many filters at once. So the order that you do things is really weird with a lot of these search engines. So say you had 3 filters. If you do all 3 at the same time, nothing comes up. But if you do the first one, then you do the second one, then you do the third one, then all of a sudden things come up. So you got to be real careful just with order. All right, so we've got all these different voltage ratings, and we can scroll over here, and we want, let's just say we went through hole. All right, so we'll do that. That'll get rid of all these surface mount packages. Then we can say automotive or general purpose. Just leave that alone. All right, then we can say axial or radial. All right, so we'll say axial. All right, and then, excuse me, I wanted radial. I can clear that. Where is that? Package case. Let's go there. And let's see if we can get this back. That's not what I wanted to do. So you have to click to the right of it, of the selection, I think. All right, so let me do that. Let me clear that. Let me put radial. Okay. All right, so here we go. Now what I do, so now I've got some parts here. How many do I have? 107. All right, right now, again, there's all these different things. There's the temperature coefficient, all these ratings, the size, all this. I don't really care. First thing I want to do is just sort on the price. So let's just get the prices down. All right, so now it looks like these things are maybe 20, 20, 20, 20. They're all about 23 cents, 24 cents. So they're going up pretty smooth. There's no big jump. All right, now let's talk about temperature coefficient. We're going to talk about this in detail in the course. I'm not going to go over it here. But what I can tell you is this temperature coefficient, this X7 and R, has to do with the lowest temperature, the highest temperature, and then the tolerance and a percentage. So you can look this up. So you can go to a table and you can look up capacitor temperature tolerance. So you can say capacitor temperature coefficients. All right, and here we go right here. And this is just some random, and let's make it a little bit big here. And it's actually on DigiKey's site. Okay, so now we look down here. So there's that X, that Y, and that Z. So you see here, we see X, here's a Y, here's an X, here's an X. If we go far enough, there's a Z, all right? So that's what that first letter is. So the first letter means it's good to minus 55 or minus 30 or only plus 10. So typically we want things with the minus 55 or the X. Y will do, but start with X, that's pretty good. Then the next number is the high range, right? So the next number is what the high range is. So typically we like 5 or 7, 5, 6, or 7, kind of gets it done. Ideally 7. So now we got X and 7. And then we want to know the changing capacitance over the temperature range, this tolerance here. So you can see there's P, R, S, and then TUV, and then V is horrid. 22 to minus 82%. That's just terrible. So what we want is R and S. Those are kind of realistic. So what we want is X or Y, 5, 6, or 7, R or S. So like X7R would be great. X5R would be great. X7S would be okay, right? Gets a little bit worse. But that's where we want to be. So the R and the S is where we want to be, and the 5, 6, and 7 is where we want to be, and the X and the Y is where we want to be. We never want to be at Z. Z is just terrible, okay? Useless. All right, now that you know that, so up here we see we've got this X7R, which is good. This is at 10%. So let's just take everything X7R. Let's just only mess around with X7R. All right, and where can I find that? Right here. Here it is right here. All right, so we're just going to take X7R. Good enough. All right, and then there's even more accurate capacitors called COG or NPO, which we're not going to play with right now. Okay, so now we have a lot of these different choices. So now I want to see, well, they're 23 cents at quantity 1. I'm not going to buy 1. I'm going to buy 100 of them probably, or 10 of them at least. So here's Vishay, here's AVX, here's Vishay, AVX. So let's just look at Vishay and AVX, all right? So if we go here to Vishay, we see at 100 it's 8 cents. That's pretty cheap. So at 100 it's 8 cents. And then we go here to the AVX part. Where are you? And then at 100 it's 7 cents, all right? And then we look at the width, all right? So we look at this pin width right here. spacing, and you can see it's about, there's the height, and there's the size, and there's the lead spacing, 5 millimeters, right? So that's 5 millimeters on that one. And then on this one, I believe it's 5 millimeters as well. All right, and where did it go? 5 millimeters as well. Okay, so these are almost identical. So now really at this point, it's just taste, right? What company do you like better? So if we look at them, their specs are almost identical, right? Maybe their sizes are a little bit different. So if you look, this one is a little bit smaller, all right? A little bit smaller than the other one. So maybe you're going to go with this one right here. So let's just go with this one. So we go with this one, we look at the price and say, hey, I'm going to use these a lot. So here's the thing. If you buy 10 of them, you're going to pay $2.30. If you buy 100 of them, right, you're only going to pay $8 or $9. I'm going to buy the 100 because this is one of the most common values of 0.1 microfarad. 0.1 microfarad, it's good to 50 volts. It's X7R. That's what I'm going to buy. All right. Now, let's say that you want to get a bunch of different, say, electrolytic capacitors, right? Electrolytics. Now, electrolytics can be fairly expensive, right? So now I could buy them on here, and I could search for them. So let's say we want to find 100 microfarad electrolytic, all right, capacitor. And that should be enough to find a capacitor. All right, so we go on here. Okay, great. Aluminum electrolytic capacitors, 6,800 of them. Okay, again, let's start slow. Active, 100 microfarad, bulk or cut tape sometimes are loose in a bag. I want it stock. I always like everything RoHS compliant. All right. Now there's even more things to deal with this. All right. But again, let's just see what's coming up here. All right. So we're getting these surface mount guys. So let's at least get rid of that. That I know I don't want, right? So we're going to go over here and we're going to find packaging someplace. Here it is. And we want through hole. Now let's apply that filter. Okay, now there's 1,100 of them, and now they're all through hole. Okay, great. Now let's go and sort by price. Okay, so now look, we've got some really cheap devices here at 12 cents for one. So that's really good. Worth Electronics, excellent. But now look at our voltage rating. So let's say that we wanted to use this 100 microfarad capacitor in a power supply. Let's say we wanted to use it right where the power came in, and say we were regulating the power, or at least turning it to DC from, say, a 9 or 12 volt power supply. That 9 or 12 volts could sit at maybe 12 to 16 volts with no load on it. So at least 16 volts. So this 10 volts is not going to get it done. So what we really want is 16 and up. All right, so let's just say 16 to 50 volts. That'll get it done. Now we do that, and we come back through here, and again, now, okay, there's 16, 25, 35, and then we see the price doesn't really change much here. So I like this 25, and this one's at 20%. All right, it's polarized, general purpose. We look at the lead spacing here, radial can, and where's our lead spacing? 2.5 millimeters. It's very small. And then another thing is lifetime 2,000 hours at 105. So if you cook it, it'll last 2,000 hours. These things, ripple current, I talk about these in the course. I don't want to talk about this right now. Let's see, is there anything else I want to talk about? Not really. And the tolerance of these are always going to be about 20% for a good one. And as they get bad, you'll see like 30, 40, 50. You don't want anything like that. So it looks like I can find a capacitor that has a 25 volt rating, 100 microfarad. That's a pretty big capacitor for 14 cents. And now at 100, it's only 10 cents. So there we go. I'm going to buy maybe 100 of those, or maybe I'll buy 50 of those for $10. But what if I want like 20 different values? Maybe I want 10 microfarad, I want 47, I want 22, I want 100, I want 220, I want 470, I want 1,000. I want a bunch of different values. This could get kind of expensive. Maybe I'd spend like 50 or 60 or 70 bucks. So another thing you can do is get kits. Now you can look for kits on here, but let's just go to Amazon. And in Amazon, we're going to say resistor. Let's start with the resistor kit, okay? And we really want a through-hole resistor kit. So we'll see what comes up, and what's coming up are the through-hole ones. All right, so great, we'll just stick with that. And then we look here, and I'll just sort it on Prime because I want everything to be sent for free. All right, so this one right here, it's got 17 different value, 1%, 0 ohm to 1 meg ohm, and 103 positive reviews. That looks pretty good. Looks like this one's the same. Is there something that has even more? 134, so this one's got 134 values, what do we have here? 17 values, 134 values, 25 pieces each, so 0 to 4.7 megohm, 1/4 watt metal film resistor. So I really like this one. All right, this is more what I'm looking for. So here's a nice kit. And then here will be all, yeah, there's all the values. So 0, 1, 2, there's a lot of values in there, and I can see it's all the way up to 4.7. You've got 25 of each, and they're all 1%. These are really, really good resistors, and they're 1/4 watt. So I'm done. So right here for $17, I've got all my resistors that I'll ever probably need. As I'm prototyping, I would just get that and be done with it. All right, let's do a capacitor kit. If I can spell. My hands are, so it's like 40, 50 degrees here, even though I'm in my lab and it's hot and it's warm. You know, I just went outside for something and it's like your hands are just, the heat is taken out of them. Of course, now some people who live in Russia, for example, I think, you know, let's say 40 degrees Fahrenheit is like they could go swimming in it. All right, capacitor kit. Okay, so capacitor kit, and again, now we've got electrolytic, we've got tantalum, we've got ceramic. So, you know, again, we could drill this down a little bit, but let's see what kind of comes up here. So ceramic, so let's just get a capacitor kit of, say, ceramics, all right? Capacitor, let's say ceramic capacitor kit. And ceramic capacitors are going to be really good. They're more precise, they're more stable, they're better for filters and amplifiers, all that kind of stuff. Your electrolytics are going to be for smoothing and bulk capacitors. I typically don't use them for anything other than those applications, but it's hard to get a 100, a 200, 1,000 microfarad ceramic capacitor. It would be very, very, very expensive. So anyway, let's take a look here. And let's see, 100 nanofarad to 10 microfarad, not enough values. There's only, what, 10 values there? I don't like that. Here's 15 values, 550 pieces from 0.1 to 10. This 15 doesn't look too bad. Let's see, 30 values from 10 puff to 10 microfarad. That's not bad. And let's see, set of 600 from da-da-da. Okay, so maybe, you know, maybe I'm looking at this one right here. All right, and I might have to get a couple different kits, right? And if you look at these are not bad. They've got good long leads, long enough to get to your solder spreadboard. And then, of course, it says what the values are here: 10 puff, 330 puff, 47 nanofarad, and so on and so forth. And then up here, we've got our 1 microfarad. They're kind of out of order here. 10 microfarad. Anyway, so maybe you're going to get that one, and then maybe you look at, you know, this one and see what the values here are. So these are higher voltage. So these can withstand high voltage. We don't need these, right? These are high voltage, 3 kilovolt ceramic capacitors. We don't need these. All right, so maybe we get that ceramic kit for our smaller stuff. Now we want some bigger value capacitors. So then we go electrolytic capacitor kit. All right, so because we want some bigger capacitors. So now we go here. We've got 15 values. Now here's a 24, here's a 25 value. I'm liking that better, 24. And again, I'm just looking at this for a few seconds. You guys can do a lot better. 13 values. Okay, let's go back up here. And I think I like this 24, 500. And this one has 1, 2, 3. This one's got 24 also. Where was that 25? It's just kind of showing it. Here's a 24 right here. This looks pretty nice too. All right, and I'll go here and hover. Yeah, so we can see 0.1, 0.22, you know, all these good values here, 10 microfarad, 100 microfarad. So this is a great kit right here, up to 1,000 microfarad right there. So I'm pretty happy with that. And then you can take a look and grab some of the voltages off here. So I can see, for example, I can see there's a 50 volt right there. So these are all pretty good voltages also, so they're going to be useful. So maybe I'm going to get that kit as well, right? So this kit is what, $17. So I get a couple capacitor kits, I get a resistor kit, I'm done. I don't need to go buying things one by one off of DigiKey. Now, the other thing to remember is when you're designing and doing electrical engineering, there's a reason, and again, you won't know this unless you've taken the class, but we use these common values, 100 ohm, 220 ohm, 330 ohm, 1K ohm, 10K ohm. The reason why is because those are just made in bulk and mass since, I don't know, probably the 50s. Electrical engineers use those common values. So these kits are always going to have those values. So if you don't use a 220 ohm and you use a 207 ohm resistor for some bizarre reason, you're not going to be able to find it unless you buy it specifically. But if you just kind of say 220 will get it done, that way you can use common parts, and that way you can kind of buy things that are in kits and save yourself a lot of money. All right, so anyway, just wanted to show you that nobody should be spending a lot of money. The stuff is really, 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 really cheap. You just have to know how to shop. All right, and so I suggest that, whatever country you're in, if you don't have Amazon, use your version of Amazon, whatever that may be, Alibaba, made in China, whatever. And if you can get to DigiKey and Mouser, they're great for searching, and of course for purchasing, and of course for your ICs and all that, you're going to need DigiKey or Mouser. Let's see. Is there anything else? I think that was about it. So I just want to make sure people aren't having trouble with that, all right? So anyway, a real bonus lecture will be coming in a while, but this one was just to help people out that are, trying to shop early and get some parts to build some stuff, all right? So I'll see you in the next lecture. Bye. Welcome everybody. This is another bonus lecture, and it's Christmas, well, almost Christmas as I'm recording this, so Merry Christmas if you celebrate that. If you don't and you live in the United States, at least it's usually a day or a week off, so that's a good thing, no matter what. So I've been thinking about what to do for this bonus lecture. Now I was going to do another ESP32, some more programming stuff. However, two things happened. A new student mentioned how he was, in the field of electronics, and he was talking about a test he did one time, and he had to kind of reverse engineer a schematic. So he thought that kind of learning how to read schematics would be something interesting. All right, now, right before I read that email, a couple days beforehand, a friend of mine, who's another kind of game developer, he used to be like at Sun Microsystems. They, Sun Java and so forth, the inventors of Java. They had a kind of gaming division. He was one of the evangelists or directors there of the gaming division. So anyway, he's big into games and retro games. And to play some of these game systems on your LCD monitor makes them look really, really, really bad, right? So remember, most of these game consoles from the 80s and 70s and 80s, these retro game consoles, they were played on CRTs, right? Cathode ray tubes, like up here on Wikipedia. And the cathode ray tube works in a completely different fashion than an LCD. Now, depending on your age, you may have never seen a cathode ray tube, right? So if you're fairly young, you may have never actually seen one working, right? You may have seen pictures of them. A cathode ray tube or a CRT, how it operates is it generates electrons, it boils electrons off a filament, and then these electrons are accelerated, all right, with these various coils towards the screen, and the screen is covered with phosphor coating that when the electron strikes it, it gives off light. And there's three different phosphors, red, green, and blue, in various patterns depending on the TV manufacturer. There's three different electron guns that are generating these electrons and then firing these electrons, being accelerated, and the electron gun sweeps from left to right, top to bottom, and generates the image on the screen. The phosphor screens look really, really, really good. They look really rich, and they have a nice look to them. And then when you try to play these games from the 80s on a new LCD, the signals coming out of the game systems are NTSC signals. NTSC, they're not VGA signals, they're not HDMI, they're not digital, they're analog in nature, and they're encoded as an analog signal. So the LCD TV has to decode this, extract it, this analog signal, and then render it on the LCD. It just looks really bad. All right. That said, so a lot of people, my friend included, what they would like to do is use a CRT to play their old video game systems, but instead of using an NTSC signal, and of course, if you've never, again, if you have no context, you're not even going to know what I'm talking about, but I'll get to it. If you have one of these old consoles and it puts out a composite NTSC signal, that signal is still analog in nature and it's encoded and it's not digital, so it means it has to be decoded. The pixels, the color, the sync, all has to be decoded, and it's noisy. So the image is still not that good. because of the NTSC encoding. However, some of these game consoles, some of these older ones, and even some of the newer ones, have direct red, green, and blue output, like a VGA, right? Like a standard VGA output or monitor. That red, green, and blue is pure data, so it's not encoded, it's not mixed. And then there's maybe some sync signals. And again, I'll tell you how this stuff works in a second. There's some sync signals. So now if you could take that RGB signal and get it into one of these CRTs, get around the NTSC built-in hardware, the decoding, then you get a much better picture. So the point is, my friend said, hey, can you look at, I have this TV, I want to convert it from a normal CRT that takes NTSC signals, right, composite NTSC signals, and can you convert it so that it would work with an RGB signal, or tell me how to convert it and tell me what I need to do. And then he showed me some videos of other people doing it on the internet, and I've done this for many years myself. I've converted these CRTs so they take RGB signals directly because it's a much better picture. All right, so anyway, in doing that, I had to start looking at the schematics for this particular TV set. So let me go here, and I'm going to show you. So here is my friend's TV. So it's this Sharp TV, and you can see it's a normal CRT TV. It's got a cathode ray tube in there. All right, and if you start scrolling through here, what I'm looking for is the schematic. So this is the service manual, so for engineers. So if you scroll through here, and you can see it's got all these kind of technical pieces of information, really, really cool. And this is what the service guys would get. All right, and then here's, the chassis layout, kind of showing from a top view. There's these different PCVs, PWBA, PWBH, PWBB, etc. These are showing these different things. Now, when you when you're looking at schematics, now again, so the whole idea of this lecture is we're just going to kind of look at a schematic. And there's lots of different kinds of schematics. For example, the schematics that we have been generating in the course, right, are kind of electrical engineering embedded schematics, embedded engineering schematics. So we have a certain way of drawing things and doing things. If you look at schematics from engineers that design television sets, the way they draw some things are a little bit different. They use, some different kind of techniques, and the way that their assumptions and their conventions are a little bit different, but more or less you can kind of figure it out. If you look at schematics, electrical schematics, say from a power engineer, right, who builds power plants, those will start to be a little bit confusing. Or if you look at even electrical schematics from electricians, they'll be kind of harder because they'll have symbols in them you just won't be familiar with. And for example, my air conditioning, I don't know if I mentioned this, maybe in a couple of videos, I mentioned my air conditioners, I've got two of them, and one of them blew out. And I was looking at it and looking at the schematic, and you're looking at the schematic trying to figure out what these different symbols are, right? And you stare at it, and after a while you start to figure out this thing's supposed to be like a capacitor, this thing's supposed to be like a coil, this thing's supposed to be ground, this is a switch, this is a relay, but they've got their own way of doing things. That said, as we look at the schematic, this is a really good experience because it kind of gets you to be able to follow signals and then kind of drill down from kind of a block level, a high level, to a schematic level. So that said, when you get like a TV schematic or kind of an appliance schematic, a lot of times you'll see a block diagram. All right, so and that's what we see right here. All right, I'm going to zoom in just a little bit. So here's the block diagram of this TV, and it's showing different things right here. So what is this, for example? Well, that's a speaker. So that's a little coil, and that little symbol, that is a speaker. And you can see sound output. So this is the built-in speaker in the TV set, one of them. And there's probably another one someplace else. All right. So we would look through this schematic. And so my friend, his whole goal is he basically says, hey, I've got this TV, and it's got a video input, right? And that video input takes NTSC. And I'm going to talk about that in a minute, signal. And I want to figure out, can I somehow connect red, green, and blue, an RGB signal, into this TV, because I know you can do it because I've seen other people do it on YouTube.
Can you show me how to do that and show me where to connect it and all that kind of stuff? So that's what we're trying to figure out here. So this is a big project, not something we're going to do in an hour, right? But I'm just going to kind of show you some of my thought process. And this is what engineers do. So this might be a job. So he's my friend, right? I'm just going to kind of show him where to kind of put this and tell him some things to watch out for and all that. But if someone were to say, hey, Andre, I want you to do this project for me, I'd say, well, it's going to take maybe 20 hours or 40 hours or 60 hours or 80 hours or 100 hours, whatever it's going to take. I would come up with a proposal, then this would be a job, and I would sit here, figure it out, I would design it, make a prototype, build it, test it, verify it, and deliver it. Okay, if someone wanted this, maybe they want to make a product out of it, I don't know. But in this case, we're just looking. Okay, so here's the block diagram. And so, the first thing you do is just kind of look at it. At first, it's kind of confusing. So we know that this PWB-H and this PWB-B, these are boards. And then there's this PWB-A board. So this is the big main board, and these are two smaller boards. And we know that because here is kind of these representations of these mechanically. So there's these three boards. This is a pretty simple board, this PWB-H board. And this means absolutely nothing. This is probably an acronym for something. Printed circuit, printed something. It's probably printed something board with these different letters, H and A. But a lot of times things just are made up. But you can see this just has two connectors and it has this HA here, which I'm not sure what this is, okay? And a lot of things you're not sure what they are. HA, I don't know, maybe heat sink, I'm not sure, have no idea. I'd have to look at it, and this is what we got to do. All right, so there's a speaker. This is where the inputs are. So on a TV set, again, I'm sure you've seen audio and video inputs. Here they are, and this is the composite input that takes NTSC video. All right, and then if we were in Europe and whatnot, then those TVs work on PAL, right? There's NTSC, PAL, and SECOM were the old analog standards, right? And so here in the United States, obviously we have NTSC signals and NTSC TVs. And most TVs will still take these signals, even the modern ones with HDMI. All right. Then we've got this other board right here, which, so to CRT cathodes. So this is like a driver board. This is the actual board that's connected to the yoke of the CRT. And let's kind of go back here. So this whole thing is called the yoke. And this is the whole CRT assembly. These are the deflection plates, accelerator plates. And so one of these boards connects right here. All right, so one of those boards connects right there. That's this board, I believe. All right. Okay, now we're looking down through here. So now we're getting stuff that looks more familiar to us, right? We've got, this is a chip, and you can see, let me zoom in here a little bit. Excuse me, I'm going to be coughing and this and that a little bit. I've got horrible allergies right now. My face probably looks all puffy and my eyes may be watering. So I've got allergies like cedar fever. Here in Austin, Texas, we have these cedar trees, and this stuff is hugely allergic. I am hugely allergic to it. So it's just stopped right now. That's why I sound stuffed up and all that. So I will try and edit out most of my allergy attacks, but we'll see what happens. All right. So we see this IC right here, and this is IC201, and it's saying PIF, SIF, chroma, video deflection. So these are obviously abbreviations of something. So PIF stands for something, SIF, chroma means color, video deflection, that's the video deflection circuitry. So this chip drives the display. This drives the actual CRT part, okay? So this is good. So we know that, and then this, all these various signals here in these kind of block diagrams, they represent either a chip or chips or analog components. So this, for example, Q201 IF preamp, this stands for intermediate frequency preamp. SF201, this is a SAW means sawtooth, so this is some kind of sawtooth generator IC. Q401, it's probably a transistor, could be a transistor or FET. And you just kind of look through these things. Now, of course, this is TV technology, so I don't expect you to understand it, but you're just looking through these blocks and trying to figure these things out and see what's going where. So here's the driver chip that drives this. And then over here, let me see if I can get my little hand here. Yeah. Then over here, there's another IC, IC2001. Now, this is interesting. And this says system control. And it's connected to, let me back out a little. It's connected to this chip here. It's got RGB coming out of it, going into this chip, so that we're going to swing back to that. It's got this mute control here, which is kind of going up. So we've got this mute. going up here to this sound chip. So wait a minute, this is the speaker. This thing right here, so IC352, this says R sound, probably means right sound, right channel sound. All right, and then there's a signal here, which I bet you this one right here is sound. See, it's audio out. So there it is, audio out right there. So this is the right speaker. Now, I said there's probably a left speaker, but on this one there may not be. Nope, so there's a single speaker. Here's the output, and then one of these is a mute control to turn the speaker off, and then the other one is this line right here that I'm following, is a delay driver. So this is relay driver, and then there's a relay regulator. This looks like it's power. Yeah, this looks like it's power going into this chip. So anyway, that's what you do. You kind of just start tracing things for what you're kind of interested in. So again, a lot of these things, and I don't even know what they stand for because I'd have to look and figure out what these guys mean by these abbreviations. A lot of times you have to figure it out, right? Now I do a lot of video hardware. I've built a lot of video systems, a lot of video hardware, graphics chips, all those kinds of things, and obviously game consoles. So I do a lot of NTSC, PAL, VGA, RGB, all those kind of things. I mess with many, countless TV sets. So I've gone through this, but every single one of them has some different things in it so that you're not quite sure what these little symbols mean, like ATT. Okay, this is a switch right here. So there's an audio here, there's an external audio in, there's a TV audio in. This is a switch, and so this ATT right here, okay, have no idea what that means. But this is some kind of switch here, so it allows you to switch between these two things. ATT could mean attenuation, right? And right here, YN, so in TV parlance, Y means luma, or the brightness signal, right? And that's what Y means. So this means YN, luma in, luminosity in, and C is the chroma or color signal, CN. So, you kind of figure out what you know, and you got to kind of figure this stuff out, right? All right, but again, we don't really care about that. We're going to come back and figure out how we would convert this into an RGB monitor. But I just want you to kind of look at it just for a minute here. So this chip here kind of is this controller chip. This is this video driver chip. And then we can see things here. Now in this schematic, again, it's a block diagram, so you're not going to really see many parts. But we can see, hey, there's a transformer, right? There's some kind of transformer. These are coils, right? These are inductor coils. There's some stuff going on here, right? So this is another transformer. So it's got multiple primaries and multiple secondaries, right? And these two lines, that means the core of the transformer. So it's got a common core and there's primaries and secondaries. So that's interesting. Some more, these are relays. So there's a coil, right? There's the core, and then here's the armature. So these are relays, right? There's our line coming in. There's our power coming in right there. There's a fuse symbol. So you kind of can make your way through this thing, right? Just slowly and surely, kind of what's the whole, global view of things, right? Now, after you've kind of figured that out, and I'm going to tell you, the only thing we're going to care about are these two chips for what we're going to try and figure out. Then we go down and we start looking at the actual schematics. All right, and then if you're a TV service guy, these waveforms right here represent what things should be doing at different test points. So if you're testing the TV and you're trying to debug it, you're trying to fix the thing, that's what this manual is for, you need to be able to see, hey, this horizontal signal is number 1 and it should be 0.96 volts peak to peak. This is signal 12, it should be 5.4 and it should look like this, etc. All these should look like this. So if something says at this test point you should see a number 19, it better look like this one. And it better be 260 volts peak to peak, okay? All right, now here is the schematic. So here's where things get fun. Let's just close that. That doesn't help us any. So here's the schematic, and I'm going to zoom out a little bit. And yeah, there it is. Okay, so that's the whole of it. And let's go back in. So there's that IC201. There's that video driver chip that we were looking at up in the other one, right? That's the top chip, the video driver. Now someplace there's going to be that video controller chip, and it may be it's probably going to be on another page. I'm going to zoom out. So here it is right here. So there's that video controller chip. So there it is right there. So you can see it's very complicated. But now we know every single one of these parts, right? What's that? There's a transistor right there. What kind of transistor is that? That's an NPN transistor. These are capacitors. This is a capacitor. These are resistors, right? Here's another capacitor. So this symbol right here, this is an electrolytic capacitor, and this is the way they do it with these little lines, but they put the plus and minus to let you know it's electrolytic. There's resistors, we know all that. That's easy. More resistors, more capacitors. What's this thing right here look like? So we look here, and it's got an input, it's got a ground, it's got an output. This says KIA 7045A reset. Not sure what that is. We'd have to look that up. It's a 3-terminal device. It could be some kind of regulator or something else, but we would just look that part up, and we're going to see how to do that also. Here's an IC. So this is IC 2101, and then so it's telling us this is an EEPROM. And then you can see here's the I2C inputs. So I've talked about that a little bit maybe. You know, again, this is not a embedded course. This is not a course about microprocessor, microcontroller design. It's about electronics, basic analog digital. So we haven't talked about protocols like I2C or SPI or UARTs and all that. But anyway, this is a I2C EEPROM, electrically erasable programmable read-only memory. So that's a memory. And then this right here, I'll tell you, is a processing chip. I've looked this up, and we'll go look this up. This is a processing chip. This is a processor right here. All right. And let's see, is there anything else interesting? Over here, we can see some of this nastiness, all this analog, a lot of analog electronics. But again, we know what all this stuff is. There are diodes, right? So this is a kind of bridge rectifier situation going on here. There's that multi-tap transformer we saw. Let's see, right here, FB702. This might be a ferrite bead. This might be how they draw a ferrite bead. And again, you know, we have to look at the parts list and say, what is FB702? Is that a ferrite bead? But that may be how they draw it. So FB702, for example. And there's a Schottky diode, right? Zener diode. There's a Zener diode, right? And this is it looks like it's an 18.5 volt Zener diode to keep that clamp, this overvoltage protection signal at 18.5. That's what that must be. Let's see. And anyway, and then here's our little ground symbol, right? These little ground symbols. So this is us going through this schematic and kind of looking at things, all right? And then, and let's see. And then here's another one showing what's connected to that actual CRT. This is all these signals that are connected to it for red, green, and blue. And this is the actual driver section. You can see red, green, and blue, ground, 9 volt. This is 9 volt. B means usually bias, 9 volt bias. And this kind of is what's driving these drivers here. So we're not going to mess with red, green, and blue there. I'm going to actually show you a different place we're going to do it at. All right. So before we dive into this, we've been talking about 20 minutes. Before we dive into this completely and kind of look how we would want to do this, what I want to do is I want to just talk briefly about the whole idea of CRTs. And let's close this. So definitely go on Wikipedia and look up cathode ray tube. I'd like you to do that and just parse through this and kind of read this a little bit. You know, it's very interesting. And so you just get an idea of what's going on here, right? So go through there and kind of see that the first CRTs were actually invented in the late 1800s, believe that or not. I think it was 1898 or something like that. If you look through here, I bet you it'll say it. But yeah, unbelievably old technology. Yeah, cathode rays were discovered by John Wilhelm Hittorf in 1869, and then yeah, Crookes showed that it could be deflected by a magnetic field in 1890. Electric Crookes showed they could be deflected by magnetic fields. 1897. Yeah, so you got to read this, but that's just crazy to think about. These people were doing things in the late 1800s. How nutty is that? This is advanced technology. You're talking about subatomic particles. You know, crazy, crazy. So take a look at that. Then the other thing I want to talk about, NTSC signal spec. And again, if you're not interested in CRTs and NTSC and video signals and all that, you know, you can just not care about this too much. But the whole idea, engineering is about a lot of times learning something new because a client wants you to do something. So you may have a situation where someone wants you to make a video converter from NTSC or VGA or RGB or this or that to HDMI to whatever. And so you're going to have to go read this stuff. So it's good experience to learn how to look this stuff up and understand it. So NTSC stands for the National Television System Committee. And yeah, in like 1950, it was formed Yeah, the first standard was developed in 1941, and then the second in 1953. So the standard's very, very old. And so here's the whole thing. NTSC is, basically was developed in 41. The kind of one that we use is 1953. So this is 50, 70 years roughly old. 70 years old, and it's still not bad. I mean, it's amazing that it was invented that long ago. All right, so you can kind of read through here, but the technical details that I want to get to, and like I said, there's NTSC, and then over in Europe there's PAL, which is a French word. It stands for something French, which I can never remember. And then there's SECOM, which is sequential color and memory, I believe. And then PAL, we'll look that up in a second because I can't remember it. Even though I'm half French, I should know what it stands for. But what I want to show you is, let's see if we can see a signal here. I'm sorry for scrolling. And there's versions. There's version of it. Let's see. Do they say what PAL is here? What the acronym is? No. Yeah, phase alternating line. I feel like there's another something French. I can't remember. Anyway, phase alternating line. Yeah, so PAL is similar to NTSC. It's maybe a little bit better in some ways. All right, but I want to show you the signal, and no. Okay, so let's go here. NTSC signal, no spec, and let's go to images. Yeah. So this is, and you'll see this if you read my book, my Black Art of Video Game Console book, or my Design Your Own Video Game Console book that comes with this course, which is basically just the e-copy version of it. You'll see figures like this inside of my book here. And let's go here and open this up. And of course it did that because it's a transparent image. All right, let's go grab another one. Let's see. This one's not bad. Okay, and so what are you even looking at here? Now, this is an analog signal, so again, I don't expect you to understand this. This took a long time for me to understand and study and all that, so I don't expect you to understand it in 5 minutes. But this right here, what this represents is a video line. So this is the signal of one single line of video in an NTSC signal. All right, and what's called a baseband signal. Now NTSC is modulated, so you've got channel 2, channel 3, channel 4, channel 5, and then the base signal is modulated on a carrier. Forget about all that. This is just the base signal. So this is the base signal before modulation. So this represents one single line of pixels across the screen. Then in addition to this, there's line. So it draws all these lines on the screen, and then there's a vertical sync signal that tells the electron gun to go back up to the top and do it all again. Now, in each horizontal line, there's different portions of it. So this right here is the horizontal sync, and at the beginning of every line, there's a sync, and a signal happens that goes in the negative direction. This tells the TV receiver, hey, I want you to take that electron gun and bring it back to the left point of the screen because we're going to draw a new line. All right, so this electron beams, red, green, and blue, are scanning across the screen constantly. This says, bring it back and synchronize to the left side of the screen, and I want to draw a line. All right, then it says, okay, great. Then how did they encode color? Now this is one of the most interesting things, NTSC. It's also laughingly called never the same color twice. How color is encoded, it's not red, green, and blue. How color is encoded is as a phase angle. All right, so basically what happens here is there's this thing called the color burst, and this little oval really looks like this. So this is a zoomed in version here. And what it is, it's 8 to 10 little pulses of a certain frequency, right? And that certain frequency is the color burst frequency, right? And the color burst frequency is what, let's look that up, get the actual, 3.45 megahertz color burst. And you can see it's been a while since I've done old-fashioned NTSC, even though I've done an enormous amount of it. 3.579545 megahertz is the color burst frequency. Okay. So you create a sine wave of 3.57, right, megahertz, and you put out 8 to 10 pulses of that. Then you put that on top of this signal, right? what's going to happen is that TV receiver is looking, it's got a filter looking for this 3.57 megahertz signal. The second it sees that signal, it tries to lock onto it. And it's got 8 to 10 different waves, right? 8 to 10 different samples to lock onto it. So it starts trying to lock onto it, and finally it locks onto it. So now it's in synchronicity with the signal. All right, now, here's the interesting part. Then we come over here a little bit more. This whole thing happens in 63.5 microseconds. So we'll talk about that in a second. Now we start drawing pixels. So this is where the pixels get drawn. You got 52.6 microseconds to draw pixels. In this time, you're going to draw the pixels on the screen. And there's about, depending on what you want to do, about 160 pixels or color clocks that you can control the color of. So on a normal SD TV, old school CRT, you only had about 160 pixels across that screen, believe it or not, that you could control the color of. You could change the luminosity at a much higher frequency, but or much higher pixel rate, but the color was only about 160 pixels. That's it. Now, how the color is encoded is like this, is as you are drawing the Luma signal, so this is basically this Luma signal, as you're drawing each one of these pixels here, the phase angle of that Luma signal compared to the phase angle of this color burst, depending on the phase of it, relative to this reference frequency, depending on the phase of it, that'll be the color. And then as you go around 360 degrees, you would get different colors. I know this is super crazy, isn't it? So if we say color burst circle, maybe. Let's see. That didn't help us. Let's see. NTSC color burst circle. Yeah. Here we go. And so what this is showing is at phase angle 0, right, you get kind of a blue. And then as you rotate around and change the phase angle, so from your reference color burst, as you shift it to create different colors in that pixel stream, here's magenta, there's red, there's yellow, there's green, there's cyan, etc., right? That's how you encode the color in the signal. So it's encoded in phase. Super brilliant to encode it in phase, but kind of hard to extract out because you have to have filters and phase lock loops and extract this information. So the whole point of it is, this is a really nasty analog signal. The sync is in the signal. The color is in the signal. The luminosity is in the signal. Horizontal, vertical sync, all in the signal. So basically everything is in one single signal line. So you can encode this in a signal line and ground, and then you have your video signal. That's what your component video, or excuse me, composite video on your TV set, the composite, the old school composite, when you plug that in, it's looking for this signal and a ground, and that's it. It's all encoded in here and has to be extracted. So during the encoding and decoding, it just gets really messy and yucky, and then the signal doesn't look good. That's why we like red, green, and blue, because it's like red, green, and blue. So I want the pixel, this pixel to be red, green, and blue. Then the next time frame, I want this one to be this red, green, and blue. Then typically a RGB monitor has a separate signal for sync. So it'll have an H sync and a V sync separately. Or it could have them mixed together, called composite sync, right? Or sometimes even if they want to save signals, they'll take the sync signal and actually embed it in like the green. So it'll be sync on green. So you see red, green, and blue, and there's only 3 signals. You're like, where's sync? Well, it's in the green. So you'll see red, sync on green, and blue. And sometimes they actually put it in the other channels also, but the majority it's in green. So anyway, the whole point is that's what NTSC is all about. It's an analog signal invented in the 40s and 50s, and that's what all our TVs have been using, or a variant of, and European TVs that use PAL and SECAM are very similar. All right, now, if you want to know more about this, in the book for the course, let me go grab that, the Design Your Own Video Game Console manual here, my book. If you go to chapter 9, and go to the graphics section 9.9, I'd like you to read the graphics section 9.9, just kind of go through here. And it'll show you, and you know, when I wrote this, I have all the details here much better than I have off the top of my head now. So here's the distribution of NTSC, PAL, and SECAM, all right? And then here's how the raster works. So You know, like I said, I've done a lot of work with NTSC signals and generating them with hardware and software. And this is you know, a very, very good explanation of this at a practical level. So, you know, I would highly suggest you read what I wrote here. It took me a while to generate all this for you and for readers. So try reading this and you'll really understand what's going on. And let's see if there's anything else here. Oh, there's that video signal that we just saw with some more details, and then getting some more nitty-gritty here, what these signals need to be looking like. And then I talk about, you know, how to generate them, how to generate this stuff in software and hardware, and then talk about it in the abstract. So read through that. That'll kind of give you an idea of, you know, how to do this stuff. All right, now let's go back over here to our schematic, and this one here. Okay, so we want, you know, to basically say where inside of this TV schematic, this TV set, if we had a red, green, and blue signal, and if we had red, green, and blue, we're going to need sync also. Where would we put it? So I have a game console or a computer that puts out red, green, blue, and sync, and I know this TV can do it because it's an RGB, you know, CRT. At the end of the day, red, green, and blue. The hardware is here to do it. But where on earth what do I do? How do I do this? Okay, so again, this is a big project, but I just want to kind of show you my thought process and how I get into this. So the first thing is, if you're interested, let me go back here and let's see here. If we just type in, let's go CRT to RGB, we'll just do that, and then we'll go back here. And then, oh, well, this is interesting. So what this is showing is in these pictures, these are people who have done this and then showing the different video quality. So you can see right here, even though he's got this on this image right here, and then you compare this image, it's much cleaner. And then again, this image right here, and then you got this image right here. It's showing these, you know, all these different monitors. So this is a composite video, and it's horrible. Then you've got this RGB monitor one. You can see his eyes. Everything is just so much clearer. Here's another picture. And RF composite. This is actually a good one. Let's see. Can we open this in a new tab and make it big? And of course not. It opens up the whole thing. This is probably a good good page right here too. Yeah. So again, this is hard for you to see, but you're looking at a monitor of a monitor and video of video. But you can see here's RF. So this is the modulated NTSC video, RF, radio frequency. There's the modulated video. And that's up at some high frequency. And then now the composite signal has been extracted through demodulation. So this has been extracted, but it's still an NTSC signal. So they both look, you know, the same. They both look bad, right? What's interesting here is this anomaly, which I'm not sure, it looks like the pillows were there in that picture and then not here, but they're almost identical. Then we go to S video, which is super video. And the difference between S video and composite video, in composite video, the luma signal, the brightness, and the color are mashed together in that single signal that I showed you, right? But in S video, super video, luma and chroma are separate. So this is actually a pretty good video standard, an old video standard. And you can see this looks much better. Again, you can't see it that well, but if you look at the character here, it's blurry. Everything is not very clear, but here it's much clearer. All right. Then here's an RGB. So forget the YUV part. Just this is an RGB signal. So this is extremely clear. And then here's another RGB. Look how clear this is. This looks like a computer display, right? So that's why people like RGB. It's, you know, extremely clear. Even on, if you take an old CRT from the 70s or 80s and you forget about all the NTSC hardware and jump over and plug directly into the RGB driver and then inject an RGB signal from a game console or computer, it's crazy how good it looks. You're just like, oh wow, I cannot believe how good this looks. Like, you know, here's another example. Sonic the Hedgehog. There's composite. Look how horrid that looks. Just a train wreck. I can't even see Sonic, right? Look at that. You can actually see everything perfectly, just like a computer display, like an LCD or a modern display. All right. Now let's go back here and let's go back here and then go to all. And again, this is a process, you know, guys and gals, I don't like editing everything out. I like you to see how this goes because the stuff doesn't take 2 minutes. It takes 22 hours to do, right? It takes a long time